Welcome to the second day of Real World Crypto. I just have one announcement that there is lost and found at registration. There is one lost iPad and a blue jacket. So if you lost anything, please go and try to recover it. And then we will proceed with the session.
Awesome. Hello, welcome to the Anonymous Credential session. I am your session chair, Kathy. I want to welcome to the stage Anya Lehman from the University of Potsdam. She's also a co-author of the Cryptographer's Feedback on the EU Digital Identities Architecture and Reference Framework, and she'll be talking about her work there and also the, that Cryptographer's Feedback.
Thanks for the introduction. So the European digital identity is a very ambitious project going on in Europe at the moment. And at the core of it is what's called an identity wallet. That is an app that is supposed to be fully mobile, secure, and user-friendly, and should enable users to authenticate and identify in online and offline scenarios. And at the beginning, this will mainly be an appified version of your national EID. So you can use that then to access public and private services that really need to verify your identity, for instance, if you want to open a bank account. But in the long run, this is supposed to contain all sorts of attested attributes, starting from a driver license to educational certificates, insurance, travel, payment, and so on. And then the idea is that this enables you to transmit verifiable attributes to relying parties that need them for their services. And in order to ensure that this thing is getting traction, major services that want to operate in the US, in Europe, in particular, major gatekeepers such as Google and Apple will be mandated to accept the sign-in with the EUIDI wallet as a means to authenticate and access their services. And that is not kind of a bold vision that Europe has. This is under actual development right now, because the EU regulation EIDAS that describes all that already entered into force in May last year. And this also sets a very ambitious timeline that now says that all EU member states must provide such a wallet to all their citizens by the end of next year. And this EIDAS regulation doesn't only set the timeline and the functionality, but it also describes what the security and privacy guarantees of such a wallet should be. And while we were not really happy with the first version of it, so I think many of us here signed the first open letter a while ago, you will, I think, be quite surprised how much privacy is actually written in there. So let's look at that. So what they kind of say is that if you want to authenticate to relying parties, you should do that in a way that allows you to selectively disclose exactly the minimal amount of information that you need there. You must be able to authenticate service in a pseudonymous way, and everything should be unlinkable and unobservable if you're not identifying yourself. And if we look a bit closer, they really mean that serious. It really says that the technical framework shall, which is essentially a must requirement, not allow providers of this attestation to obtain any information that allow user behavior to be tracked or linked. There is an annoying typo though in there. Let's see, can you see it at the bottom? In the very last version, they changed unlinkability to unlikability. I really hope that this is just a typo and not kind of an evil master plan. But I think overall, this is really great news. It really says we have a law in Europe that mandates that identity must have had really high privacy standards. But that is also just the law. And the law just says what should be done, but not how. And this is now kind of developed in these architecture reference framework in the ARF and in the implementing acts. And this is now where the good story ends. Because instead of using any of the technology that we have developed exactly for that use case, they decide to build everything from ECDSA. So maybe they did mean unlikability after all. Okay, but let's look how they try to get selective disclosure and unlinkability in there. So overall, the setup is not surprising. A credential is a signed list of attributes from a trusted authority, the identity provider, that signs the attributes and the user public key. And in order to get selective disclosure in there, the identity provider isn't signing all attributes at once, but with individually salted hashes. So then if the user forwards the credential, she can decide whether she wants to forward just the hash of an attribute or the salt and the attribute. And that gives you selective disclosure. It's not the most beautiful solution, but it does the job for selective disclosure. One thing you always have to reveal, though, is your user public key, because what you also have to do on top is to do a proof of possession that you know the underlying secret key, which is, again, yet another ECDSA signature of a session nonce with your secret key. And that tells you immediately that there's no unlinkability at the moment, right? If you use the same credential and the same public key in different presentations, you will be linkable by your own public key and by the credential of the issuer. The good thing is people are aware that this is not a good solution yet. What they propose and what is going to be rolled out probably in the first version is to use batch issuance. So instead of getting only a single credential with these salted hashes, you get 10 or hundreds of one-time credentials, all bound to different public keys of the user. And then when the user authenticates, she sends every time a fresh key and a fresh credential and throws it away afterwards. And if she's running out of credentials, she's going back again. And that does give you RP to RP unlinkability, but clearly we still do not have any unlinkability if the issuer and the relying party collude, because they still can track you with the issuer that the issuer has seen during presentation and the signature and public key you show at presentation. So what that now means is that we are building a solution in Europe at the moment that is not satisfying the unlinkability requirement as required by the EIDAS regulation. And that was also the feedback that we gave with a couple of cryptographers when we invited in an ad hoc expert group last year. And we say, but don't worry, the current solution isn't going to work, but we actually have invented something that has all the privacy and unlinkability features built in. And these are called anonymous credentials. And in a nutshell, anonymous credentials kind of work just as classical certificates. So the user gets a signed list of her attributes and public key. But instead of sending over that exact credential at presentation, the user only makes a zero knowledge proof. So she proves that she really has a credential and that she has the necessary underlying key material. And because it's a zero knowledge proof, it doesn't reveal anything beyond that, its validity. So in that particular case, it doesn't reveal anything about the signature of the issuer or the user public or secret key. And apart from also having selective disclosure already built in, the great thing is that we can now really bootstrap multi-show unlinkability from a single credential. And we finally get the unlinkability or untraceability between issuance and presentation, because also you cannot link the zero knowledge proof back to the issued credential. And if you want to make different presentations, you just make a fresh zero knowledge proof every time from the same base credential that you have and the same public key and secret key you have. All right, and the way to build these signatures or these anonymous credentials is to use a signature scheme that allows for efficient zero knowledge proofs of them. And one way to do that is to use a signature scheme that has these capabilities already built in. These are then the CL, BBS, and PS signatures. Or to use a more powerful tool like generic circuit-based zero knowledge proof compilers, and then you can actually use any signature scheme, in particular also legacy ECDSA. So that's kind of the main advantage of the second approach, but it comes with significantly more complexity and less efficiency compared to a solution that is built for that purpose. So in our cryptographer's feedback last year, we then recommended explicitly BBS because that at the time was the most mature, kind of complete and efficient solution for the problem at hand. All right, but if we have a solution that is kind of the perfect answer to what they're kind of looking for, and it was not particularly old, kind of the question is, why wasn't it used? And how can we change that? And the answer to that is, as usual, that the real world and cryptography are not as well aligned as we hope them to be. But first, remember that this wallet needs to be available for 500 million users by the end of next year, which means it has to be built now from what is available today. And there are two main constraints that come into play here, because it's a digital identity, it's a national document. The cryptography in there has to be approved in the SOGIS catalog, which is a catalog that gives all algorithms approved by security bodies in Europe, and that immediately boils it down to ECDSA, SNOR, and RSA. And that list gets even shorter if we look at the second constraint, which says that the credential must also be device-bound. So device-bound means that it should be bound to a hardware factor of the user, which makes cloning and sharing of credentials harder. And the EIDAS regulation even requires that has to be on level of assurance high, which really means you have to have a secure element where your secret key lives and can never be exposed. And these secure elements basically only give you an ECDSA signing API. And that's where the limitation comes from. So what it also means, if we want to change something on the status quo, we have to address both problems. We have to find a way to do device binding with secure elements on the markets and get the crypto in the SOGIS catalog. And in order to do that, we basically have kind of two main paths we can approach now. The one is to say, let's use the cryptography that is the most established, the most mature, and try to push it through the entire deployment stack. The other one is to say, okay, let's go the path of least resistance in terms of deployment and start what's already out there with the devices that we have. We will not change that and build the entire stack on top of that. And I'll actually not talk too much about the second option because that is what the next 4 talks will exactly be about. But it also shows that this is still a field of ongoing research. There are kind of tons of different protocols and approaches. And the question is also, how can we actually choose what the best protocol is? Do we need some sort of competition here? And do we have the time to do such a competition? But in most cases, as I said, we then have to get it into the SOGIS approval. I'm not sure if you could see that on the previous slide, but SOGIS basically references mainly standards. It doesn't have to be a NIST standard, ISO and IETF are good enough. And there, if we look at the BBS side of things, we are actually in a reasonably good state. There are a couple of BBS IETF drafts at the moment for the core signature, for pseudonyms, and for blind issuance. And also an update of an old ISO standard from 2014 that already had BBS in there is currently planned. And while this is kind of great progress, I think it also shows kind of a challenge that we will always have when we try to standardize powerful cryptographic primitives, namely, how do we do that? If we build a standard, for every use case and variation, we end up with dozens of standards that redo a lot of work and kind of risk to be inconsistent with each other. But the other extreme, I think, is not an option either. A standard that is so powerful that it will enable all use cases is a standard that nobody wants to write or use either. So we might have to rethink the way we standardize these cryptographic primitives and rather have a standard for the kind of minimal core primitive and have a standard light process for all these use case and application-specific variants on top of that. And this is going to be an even kind of bigger question, I think, for the SNARK approach. But at least there's progress, because that is something we cannot say about the pairing curve standard. BBS, just like any other full-fledged anonymous credential system, requires pairing-friendly curves. And there was a standard out there by the IETF, but that expired in 2022, and it's dormant since. And this is already kind of a showstopper if we get that not revived soon. All right, but then if we look at the CK-SNARK side of things, there they already have a head start because obviously ECDSA is well standardized and approved. But as I said, we also need to get standards for all the circuits, CK-SNARKs, into a standard and into kind of security body approval. And depending on the CK-SNARK that we're using, we might also need a pairing curve standard. But then we are done with the right side of things because I said there we started with a device binding kind of solved solution as a design. We still would have to solve that with BBS. So what we need is to get the crypto in order to get a BBS proof of possession kind of binding in there, which cryptographically is not hard at all. So everything that the secure element has to do is simply to compute a Schnorr signature over G1 of a pairing friendly curve. Trivial, but apparently this is a multi-year endeavor to get that into the real world. So also if anyone has any ideas kind of how we can kind of speed up that process or kind of do the process at all, this would be very helpful. Another option is kind of now to throw more crypto at that sub-problem and just say, okay, maybe we just need a ZK-SNARK that bridges the ECDSA proof of possession with a BBASM attribute credential on top, because that would kind of allow us to work immediately with the devices on the market. Another option is always try to circumvent the problem and go for a cloud HSM solution. So also, for instance, Germany is doing that in the first version of their wallet for different reasons. But that basically means you don't rely on the secure element on your phone for the proof of possession, but you rely on a cloud HSM service for that extra. And that would give us way more flexibility in terms of crypto we can deploy there. And trying to circumvent the problem is also an option for pairing. So if we think this is kind of a main bottleneck, we could also go for pairing-free variants. There was a proposal from Orange out there since a year, and there's also a very recent ePrint that gives it a more formal verification, which is called server-aided anonymous credentials. And they basically trade the pairing equation with interaction that the user has to do with the issuer. So there isn't a trade of that kind of price we have to pay in terms of deployment, and a pairing-friendly version of it is still going to be the best in terms of security, privacy, and deployment. So that brings me to the question whether anyone here is actually interested in picking the standard up. And it's not only needed for BBS and identity, but for all sorts of advanced signature schemes or for Grow16. And if you want to have any serious deployment of them, and serious meaning outside of a blockchain, you will need a standard that you can reference. And when you're doing that, it would also be great to figure out if you actually have any consensus on a 192-bit curve, because that was a question that immediately came up when people were thinking about the midterm perspective of that. And talking about the midterm perspective, I think it's now also time to address the quantum elephant in the room. Because does it even make sense to deploy a new crypto that is discrete logarithm based, given that post-quantum transition is on everyone's mind? And if this would be about encryption, I think the clear answer would be no. But this is not about encryption, it's about authentication. And there we don't have the threat of store now, decrypt later. And even the NIST report from last year that says ECDSA has to be deprecated by 2035 said that for authentication systems, it's actually okay to continue to use classical quantum vulnerable algorithms until quantum computers that are capable of breaking them become actually available. And I mean, we heard yesterday from one of the Lepton Prize winners that this might take longer than some people might believe at the moment. So this raises again the question to us also as a community, how do we want to make use of that leeway that we have for authentication systems? So do we want to use it to also push the deployment of systems that are not quantum safe but have other advantages, in particular in terms of privacy? are really saying we stop that now, and everything that we deploy now in the real world has to be quantum safe. And I think if we do that, we are giving up too much in terms of privacy. Because this identity infrastructure is built now and not in 10 years. And it's being built with an ECDSA mindset. And if we don't change that, it means that this mindset with all the inherent privacy limitations will just manifest in the entire infrastructure that we are building now on top of that. So my proposal is still to go for a short midterm solution that is not quantum safe and really push it out now, just to show the feasibility and the benefits of that approach and make sure the entire infrastructure is built on top of that. Also to help to shape the requirements and use cases in a meaningful way. Because we can already see now that there's not a good understanding of how security and privacy can coexist and can coexist in different shapes. Because when we look at the use cases that are kind of targeted with the first version of the wallet, yeah, we see that there's room for improvement. So they target two main things. The one is the know your customer use case, where I want to identify myself and I show all my identity. And another use case that they're aiming at are age proofs, where I just want to prove that I'm over 16 or 18, but I want to remain anonymous beyond that. And the solution that they have for both is batch issuance with one-time credentials and one-time signatures. But why do I need to be private when I open a bank account and send my identity kind of over anyway? And why does my age proof has to have the same strong level of assurance as the credential that I'm using to open my bank account? And this discussion of what are the actual security requirements for kind of a set of representative use cases is exactly what we have to do now and with the right technology in mind. And this becomes even more important if we look at all the use cases that are in between revealing my full identity and being fully anonymous, because that is where anonymous credentials can have the most impact. And starting to build that now, as I said, also enables to make sure that the entire infrastructure that we build on top actually is enabled or is powerful enough to take advantage of all the cryptographic features that we can build below. And it starts with something as benign as not requiring that the presentation that you send over is a copy of your credential, which is kind of currently the case in some of the protocols. And if we think ahead that we wanted to support something such as the conditional disclosure, blind issuance of pseudonyms, which is impossible to do with ECDSA, we can, I think, imagine that this will not be supported by any upper layer protocol unless it's really also there and there are use cases that make use of it. And finally, it also provides kind of a real concrete target for post-quantum research, because we have invented dozens of variations on properties and we don't really know which are the most important one in practice, and rolling it out as soon as possible will also give the post-quantum researchers a very concrete target, what they have to focus first. And last but not least, and there's kind of really the attention of the European Commission on this at the moment. So our open letter from last year actually had an impact. So the European Commission opens the discussion on zero knowledge proofs again. It just ended yesterday, unfortunately, but now the technical specification is on their agenda. So they want to consider zero knowledge proofs for the next version of the ARF, and the technical specifications are drafted until end of August. So we really have to get something in there with the technology and what we can build today. And there's kind of links all over my presentation. There's the GitHub, so all of that is actually kind of public. You can engage there and shape the discussion. You can also reach out to your national identity teams, because the wallets are still built by the different member states. So you can also reach out to them and try to shape the discussion through them. And there's not only the kind of explicit zero knowledge proof discussion that could be interesting, but also other places. For instance, the wallet attestation that you have to do in order to prove that not only your credential is valid, but you're using a valid wallet also has to be unlinkable, because otherwise we're going to lose privacy already at that level. And there are also many more interesting problems to cryptographers. So for instance, the first version for batch issuance still tries to figure a way out how can we best derive many unlinkable ECDSA public keys from a single secret key, because that would help with the storage of one secret key and also the complexity of batch issuance. Yeah, so there's a lot of interesting problems to be solved where you can do cool research and have a real world impact. And if someone is interested in doing that in a postdoc in our group, please reach out. Thanks.
I think we have time for one, maybe two questions, but I want to say whom amongst us has not had unlinkability auto-corrected to unlikability? Please.
Oh yeah, so read device binding with, is this on? Yeah, device binding with Schnorr and the pairing group G1. I kind of vaguely remember there was a sort of DAA light thing that Li Quin Chen proposed that I think went through ISO. So isn't there already something in ISO about a Schnorr G1 for some sort of DAA light thing? Or am I just remembering wrong?
Yeah, so for DAA, so Yeah, there is DAA out there that basically runs only the device binding on the secure element, which is just a Schnorr signature, but it has to be in G1 on the pairing friendly curve. Are you kind of saying that there is already something out there that takes a P256 and bridges it to G1? Because that would be perfect.
Not
But we-
P256, but,
Yeah, so
I think there is a standard which does Schnorr on G1.
Exactly. So
And-
that,
Okay,
yeah, that is DAA kind of over again.
yeah, but that should already be on a device, yeah? It should already.
No,
have
it's on the
TPM.
TPMs, but not in secure elements.
Oh,
So-
Hi.
so,
Sorry, that's all the time we have a really tight session today. Sorry, we have five speakers. And so next up, I guess for all anonymous credentials, we need some kind of zero knowledge proofs. And Muthu is an associate professor at Georgetown and co-founder of Ligero, and he'll be talking about how we can use Ligero or Ligatron to compose zero knowledge proofs in the browser. So thank you. Welcome, Muthu.
Thanks, Kathy. Hi, I'm Muthu. I'm co-founder of Ligero and associate professor at Georgetown University. I'm going to talk a little bit about ZK today and what we are trying to do at Ligero. So this is where it all began, in the work of Goldwasser, Micali, and Rakoff, where they introduced the notion of interactive proofs and zero-knowledge interactive proofs. These are proofs that convey no additional knowledge beyond the validity of the statement. I will say that if you haven't seen either Shafi or Silvio explain zero knowledge, I'd encourage you, I'd excuse you even to leave my talk and go find some YouTube video to watch them talk about zero knowledge. And I'll challenge you that it is impossible to not fall in love with zero knowledge. Today, with the advent of blockchains, I want to say there are so many companies, so much research that is going into zero knowledge. This is just sort of a slice of what's happening in the blockchain space. And there have been billions of dollars invested in developing these proof systems. And our company is also one of these that have been received investment in the space. So let me talk a little bit about taxonomy of proof systems and how this, how I look at this landscape. So when it comes to proof systems, there's the traditional interactive version, which is more designated verifier, and the ones that are snarks, non-interactive. Some of them, or most of them that are used, are publicly verifiable, meaning that you can generate the proof once and any number of people can verify it. There are the kinds that require a trusted setup, like a common reference string, and the ones that are like hash-based that are called transparent, that don't need trusted setup. There are proof systems that offer only soundness or integrity, but offer some efficiency, while there are others that also give the zero-knowledge privacy property. And again, you can classify them as succinct or not succinct, depending on, again, proof length, verification time. And another classification is what kind of crypto they need. Do they need public key cryptography or symmetric key? Again, this choice can influence whether you want post-quantum or not, as well as there are also efficiency reasons to go from one to another. I want to say that the ones that I've marked green here are, in some sense, more desirable. And in a spectrum of these kind of proof systems, I want to say that what has emerged is ZK snarks, starks, or snarks. They provide a very useful property of being non-interactive succinct verification, and indeed has found a lot of applications. What can you do with zero-knowledge proofs? I know I'm kind of preaching to the choir. You all know what you can do with zero knowledge. When it was first discovered, one of the first applications was about amplifying security from semi-honest to malicious. It was about proving honest execution of protocols. Soon they found identification, eCache, and what can you prove? Well, everything provable is provable in zero knowledge. But today, all of these applications are really coming to reality. A lot of the proof systems, the ZK landscape actually are focusing on scaling blockchain, which I'll tell a little bit more. And the talk you saw before and the next 3 talks, you're going to hear a lot about anonymous credentials. And of course, in the blockchain space, you want confidential transaction, anonymous transactions. Again, a lot of work in using zero-knowledge proofs to enable this is coming up. Zcash, Alio, Aztec, some of these companies that are trying to do this. And of course, there are many new interesting applications that are coming. Image transformation, expiring proofs. This is a very interesting example. Come and ask me later. I don't want to spend time right now. Fog of war gaming. This is also another thing that you can enable, like peer-to-peer gaming using zero-knowledge proofs. Now, I want to classify these applications in a slightly different way. I want to say that there are applications that you want to prove something about sensitive information. These are the ones that are privacy related, run client side. And there are ones that are proof systems, which focus on verifiable computation and can run server side. And again, just listing some of these applications that fall in either of these categories. And I want to say, again, anonymous credentials being one of the big applications client side, and blockchain scalability being the ones on server side. And clearly, for the ones that require privacy, you want the zero-knowledge feature. And for the delegation, you want succinct verification and snarks are sufficient. So where do modern zero-knowledge fall short in the ones that require privacy? I want to kind of focus more on the ones that require privacy in this space. So most companies that actually build, they're doing blockchain scalability. They don't need zero knowledge. They are focusing on snarks and starks. They are not zero knowledge. The ones that are ZK snarks, the ones like Groth16, et cetera, they require a huge memory because they need a huge proving key for the trusted setup. And the ones that also deliver ZK, they're not yet scaling enough on the client side. I can't do very large computations fast from the client side. And finally, the ones that also do these things, they require developers to learn sort of a new language, like a new DSL to program in these things. So Vitalik, one of the thought leaders in the blockchain space, of course, just recently or last year mentioned that privacy use cases haven't come to client-side proving yet because client-side proving haven't scaled enough. So what are the challenges in building and deploying these zero-knowledge applications? First, data needs to be attested. Second, you need standard toolchain for developers, not new languages. And finally, I kind of want to say one of the technical bottlenecks is that zero-knowledge proofs, at least the way they are designed, are inherently memory inefficient. So I want to talk just maybe 1 minute about this data, like each of these points. Data attestation is about, hey, I need data to be attested. Otherwise, what kind of sensitive information am I proving if I don't have authentication on the data? And there have been like really novel mechanisms to get attestation, even though we don't have trusted institutions that are willing to digitally sign your data. Here are a list of them. ZK email that allows that you can actually prove receipt of any email or even properties of your email. ZK login, again, another mechanism that actually is trying to revolutionize how you have digital wallets by changing your wallet address to your email address. And ZKTLS, finally, I think this is a really interesting new idea that can help get all of like sort of Web 2 information or the ones that you do in TLS communication authenticated. I'm going to talk about ZKTLS a little more. I want to point out that all of these have been deployed in production in some form. So what is ZKTLS? It's about trying to enable attesting a TLS payload. How does TLS work? Well, there is a browser and a server. You have a handshake where some information is signed by the web server, including its identity. And then there is a session key that is generated with which there is encrypted information. Now, as it is, of course, even by design, the browser cannot prove information about the information received in this TLS payload. And the answer is simple, because both the parties have the session key. You can forge any message post-communication. I cannot prove that a communication occurred with authenticity. So here are two mechanisms in which you can do it. One is using a proxy. You have a person in the middle that is willing to sign all the information. Now a browser can prove that, hey, look, I did do this communication. I have a signature of the handshake, and that I have signatures on all the encrypted communication, and then I can show that the decrypted payload is something. For example, your back statement has greater than X dollars. But this is not that desirable. There is an easy attack. If this proxy is not looking at anything, I could get fake encrypted messages. I could get incorrect encrypted messages signed. A second approach is something called a trusted notary, where you can imagine that the trusted notary and the browser act actually as a two-party computation to emulate a single party in this TLS communication. In this way, the session key is not stored at just the browser. It's secret shared between the notary and the browser, and every time you have to do encryption or decryption, it becomes a two-party computation protocol. And now the browser can generate a ZK proof of, again, first that the handshake was signed by the bank, and then all the transcript. In addition to being a 2PC, the notary also signs the payload, and you can prove that this decrypted payload, in fact, has whatever you want to talk about, the data you received from the server. So this is how zkTLS enables doing this, getting this data on to get attested. So I'm running a little slow on time, so I'm going to tell you the second thing I've talked to you about, like representing these things. Today, actually, there are ZK systems that can prove standard VMs like RISC-V and WebAssembly. And these enable now you to develop applications in a high-level language. The last thing I want to tell is about the bottleneck in designing ZK systems running client-side. This is memory efficiency. And on a high level, again, the two things is that ZK snarks that require trusted setup, again, huge prover key that you need on the client's device, and the hash-based systems, which are really in practice much faster than the others, have a space-time trade-offs because they require error-correcting codes. And there are some lower bounds in why this is indeed the case. So what I want to do in the last couple of minutes is to talk about this platform that we have designed. This platform will enable you to develop and deploy zero-knowledge applications straight from the browser. You can enter a C program in the browser, compile, deploy, and make it available for anyone. So here is a short video, and I'll try to talk through this video while we're doing it. This is open for everyone. You can log in with your Google credentials. Once you log in, you'll get into this marketplace where we have tested a few applications over here. I'll show one of them in this video. But first, I want to point there is a speed test which you can run. It will tell you how fast your device can prove zero-knowledge applications using the Ligero proof system. Here, I have run it. It reveals some number. Roughly, if you want to get a measure of this number, it says that you can do about 20,000 Poseidon hash functions per second. And the number really is about how many constraints per second you can prove from your browser, if you know what that means. So now I'm going to walk through designing an application. You can create a new application in C or Rust. And what you have to do is you have to write a C code straight in the browser. There's a little bit of plumbing in terms of assertions you have to do. Here, I've coded an edit distance applications that measures the edit distance between two strings and shows that a private string is close to a public string. So you hit compile, and when you hit compile, it actually goes to a backend server. This is the only thing that goes to the backend server, compiles to WebAssembly using a standard LLVM compiler like Emscripten, and the WebAssembly program is brought back to the browser. Then you provide inputs to your program. Here I'm giving the two strings that go as input to this program, and I'm showing that the first string is close to the second string. I need to, and the second two strings, just the second two inputs is about the length of these things. And once I give these inputs, I have to mark which one is private, and I can prove. And this runs completely from within the browser. And if I have a little bit of time, I'm going to talk about benchmarks about this system. You can deploy this thing, and it will go to the marketplace. And I can tell you a little more. I'm going to actually skip to the benchmarks. So right now, I want to say that One of the first ones that got designed in this space is CIRCOM, which designed a front end to prove using Groth16. This has a limitation in terms of its prover key. If you want to run this on an iOS device, you won't be able to run beyond 1 million constraints. And you actually saw that in my demo, I ran more than 4 million constraints. NOAR is, again, another system that's getting around these lower bounds using this new concept of incrementally verifiable computation. Our system currently, again, there are different trade-offs between these two things that we are we are 10 to 20x faster, but there are different trade-offs between our system and the NOAR system designed by Aztec. So finally, I want to say what we are trying to do is that we want to make developing these ZK applications easy. We want to, all you have to do, you can run everything from the browser. You can do it in any languages. We are trying to provide support for more and more languages, and we want to be able to deploy it on any device. We want to make this toolchain easier. We hopefully, we will include all the cryptographic primitives you want, ECDSA, EDDSA, SHA. Our system is post-quantum, so we hope that this can power sort of the next generation of ZK applications. Thank you.
Awesome. Thank you so much. Unfortunately, we don't have time for questions. We do have to keep moving. Thank you, Muthu. So for the next 3 talks, we have sort of a through line where they all have similar goals to make anonymous credentials from existing credentials, so legacy compatible anonymous credentials, but they all take pretty different approaches, have different constraints and assumptions. And so to kick us off, we have Avi Shalat, who's a professor at Northeastern and a researcher at Google. And this transitions pretty well from the last talk because we just heard about Ligatron, and Avi's going to talk about how they use Ligero, which is shared in common with the previous talk.
Thank you, Kathy, but it's Northeastern. I know in Western Eastern, it's like a hard thing, but anyway, thank you for the introduction. So the romance of zero knowledge. I'm going to ground it with a very practical problem, which is many websites today, they actually require you to take your driver's license, take a photo of it and upload it to basically get past that one step in that website. That's a really terrible thing right now, because you know that once that website has been breached, which most websites gets breached, your data is basically gone, and it's somewhere on the web allowed for someone to basically download. We need to essentially fix that problem. Fortunately, there are at least five states, and all 45 the others are going to do this. They're going to issue you digital signatures on your driver's license. Now, what can you do with that? You can actually make zero-knowledge proofs about documents that are issued by states like DMVs. This talk is about grounding ZK for identity. And the first thing is that ZK for identity actually has a different constraint than all of the academic literature. Most of the literature on ZK for the last 15 years is talking about this notion of succinctness. But actually in this problem, ZK for identity, it's the opposite. You actually have a very small phone that has to prove a statement about a small statement to a very large web server. So actually all of the literature on succinctness is not really relevant. We actually just need a NARC for this particular application. And the most relevant factor is the prover time. And of course, the proof has to be small enough to be practical for this type of thing. The second major constraint is that it would be very arrogant for cryptographers to essentially ignore all of the other people working on identity. There's actually been a huge community of people who standardize identity formats. And there are a lot of essentially corner cases and little sort of very complex situations that they have worked through already by formalizing things like MDoc and JSON web tokens, et cetera. And we should actually sort of build on top of that. Additionally, human coordination is probably one of the hardest things to achieve, as Europe and US is like sort of showing right now on CNN. So if we want to minimize coordination, we should probably not rely on the existence of trusted setup parameters that essentially all 27 European nations and all 50 states essentially agree upon. Finally, we should acknowledge the limitation that issuers are very limited here. We should not put the DMV in the middle of every internet login. And that means they shouldn't be online for every login. They shouldn't also be required to do the work that's proportional to every internet login. So I think that's a mistake for large-scale deployment of this type of thing. So we should look for solutions that have none of these particular problems. And fortunately, the right ZK system can actually solve all of these type of things. And in fact, the rest of this session is going to give you 3 different approaches. I want to give you my particular approach and my opinion on what I think are the important relevant factors. So we're actually going to use the second oldest recipe for zero knowledge. So this predates many of these type of things. This very famous paper essentially says if you have an IP, you run the IP to get a transcript for that, you commit to that transcript, and then you use a special zero-knowledge system just to prove that the commitment contains a transcript and the IP verifier on that transcript would accept. That is the oldest recipe for proving zero knowledge. It's everything provable is provable in zero knowledge. And the only thing that remains is picking these three primitives. And our approach has made an opinionated selection. The first one is sum check or layered sum check or GKR. And importantly, the prover in that proof system runs in linear time. And I'll show you with the receipts with data about how fast our system works. This is a very important critical factor for making this work on phones. The second choice I made was Ligero for the commitment and ZK system. Ligero is very easy to implement, and it also follows from the MPC in the head paradigm, which is also older than many of the other Sigma protocol-based systems. So both of these things are well tested. There's, in fact, a formalized proof of sum check in Isabel. So the approach that we're planning to use is, again, to run Ligero on the output of a layered sum check protocol. And my point is that doing this way, actually, for problems of this particular size, in this case, actually is faster than running just pure Ligero. And the next two talks are going to use a different type of approach. All of them are going to use Spartan ZK, which is also another sum check-based system, but it's based on R1CS, and I want to argue that essentially a layered sum check actually has an advantage over an R1CS, which is actually a flattened version of a circuit. So why is that? Let me try to give you a picture proof in this short time here. Ligero and every other system which doesn't use this trick of first committing to an IP actually has to commit to every wire of the output of a circuit. Now that's a little bit of a lie. You actually only commit to the multiplications, but for the multiplications you have to commit to the two inputs and the output, which is roughly this. That's why this diagram is roughly accurate. In contrast, if you do my recipe, which is Ligero on a layered sum check, all you need to do is commit to the input to this circuit and the sum check transcript, which, if you follow the literature, essentially that is much, much smaller than the number of wires in the circuit. Okay? And in fact, the commitment in these schemes, all of these modern proof systems use what's called the number theoretic transform. That's an n log n algorithm, and essentially to interpolate polynomials. And that is a bottleneck because the commitment is essentially running NTTs on all of the elements in there. So if you can reduce the amount of data that you commit to, you can actually get beyond the n log n boundary and in fact make the proof system faster. And that all of our empirical evidence essentially for this problem size shows that this works out. So speaking of bottlenecks, one of the other prior bottlenecks to making ZK for legacy credential systems work is essentially making proofs about legacy signature schemes like ECDSA. So prior work that had done this, for example, that work, actually had to do this very laborious thing, which is simulating the map of FQ and FP. Those are related to the particular curve, the ECDSA that we're talking about. They have to simulate that in whatever field they're doing their ZK proof in. And you might ask, why don't they do their ZK proof in exactly the field that the elliptic curve is based on? So P256 is a standardized elliptic curve in the United States. And unfortunately, if you look at the P256 finite field, it does not have roots of unity. So if you know how to look for whether something has roots of unity, that right there equation is a picture proof of this doesn't have it. However, the extension field for this P256 does. So in fact, that was one of our second big tricks, which is if we do the NTT in the extension field, keeping in mind that all of the witness variables are in essentially the base field, and so we actually get a lot of efficiency from that, we can actually run NTTs on exactly the right field. And the other two talks in this session will talk about other methods for essentially achieving this, but I think this is one of the better ones. And it shows you that if you do the right field math, you can actually get an arithmetization of ECDSA verification with roughly 50,000 terms. And again, let me point out this particular fact right there, right? If our system only needs to commit to 1,000 inputs to give a proof about this, and if you just use R1CS or any other system, and you'll see in future talks exactly how many wires they need, again, there's a 50x reduction in the amount of commitment that you need to do if you actually use our recipe. Okay, so what does that mean? Ultimately, we can do a zero-knowledge proof of knowledge for an ECDSA signature in about 60 milliseconds on a single-threaded x86, and we do all of our tests in Pixel as well, and it takes about 80 milliseconds there. These are some numbers from other systems. I think the fifth talk is going to give an updated value, but still, it's about 4 or 5 times slower than our recipe. I also want to give you information about how our system works for SHA. Basically, we can run a proof of pre-image of a SHA with our system in about 11 milliseconds. And if you put that together, okay, so if you put that together, what that means is if you have ECDSA and SHA and parsing, something that I haven't really talked about, but that's in our paper that's on ePrint, you can actually start applying zero knowledge to a legacy protocol like MDoc. MDoc is the ISO protocol for mobile driver's licenses. And as Anya basically mentioned, in the status quo, a relying party will basically say, hey, I want to check if you're over 18. It'll send you this information. And in the current protocol, you essentially send the entire MDoc as well as a pre-image for the salted hash for the attribute you want to show and some signature on a liveness check. And all of this information essentially proves the statement, but it also gives you a tracking cookie. So it gives a relying party a tracking cookie for you. These are the 5 steps that the relying party would actually do to verify this type of thing. And so you can put that into our compiler, all 5 of these steps, and essentially ask for a zero-knowledge statement for all of these particular equations right here. And I'm not going to go through exactly what they are, but I will tell you that the most costly part of it is essentially computing the SHA of the very large mobile driver's license document. And on a Pixel phone, it runs in about 1.2 seconds with a verification time of about 0.6 seconds. And that is actually efficient enough to actually run when user trials for people trying to log in instead of taking a picture of your driver's license and throwing away your data, which you would eventually do if you do that. This type of thing actually is a very suitable solution, and we've implemented it. We can also support something like credential revocation. There's various ways to basically to do that. We can also support pseudonyms. Again, when you have a circuit-based proof system, you can actually add these extra features as they come along very easily, just by adding a little bit of information to the circuit. I also want to say that we can support JOTs, so you can support both MDocs and this JSON Web Token format, or SCJOT, which is another popular identity format. We have circuits for this as well. And the last thing I wanted to comment about is the fiat Shamir attack. So Ron Rothblum, Yael yesterday essentially mentioned something about this, and Ron Rothblum and his co-authors have a very interesting attack on fiat Shamir for certain kinds of GKR protocols, right? And Yael spoke about them, but I want to tell you why our system is very different. Remember, the first important thing is that we don't really care about the theoretical notion of succinctness. Now, of course, it is verifier or succinct, as kind of our numbers kind of show, but if we don't care about exactly meeting the technical definition of that, we can actually do some very simple countermeasures. One of them is that we can essentially we can pick the random oracle function after we have set the circuit. And that's one of the powers that we actually have in our system. And we can actually set the random oracle function to be more complex than F, thus ruling out the possibility of the attack that Ron had pointed out essentially relies on the protocol evaluating or predicting the next output of the random oracle. And by carefully orchestrating things and using this type of assumption, you can essentially eliminate that. Another important thing is that nobody really uses sumcheck to compute a function. We actually all use it to verify. And that's a very subtle distinction that essentially eliminates the type of attacks that Ron has at least currently has. And of course, our goal as cryptographers is to have a more formal understanding of why fiat Shamir basically works, but at least all of the ZK proposals out there use fiat Shamir in one way or another, and there should be some good reasons like these for why these systems don't apply to ours. Now, our open source code will be available, and I wanted to leave about 2 or 3 minutes for questions. I went through my material fast, so I'm happy to go back. Go ahead.
Awesome.
This P52, this P5256 trick is pretty cool. Is that compatible with? Can that be made compatible with pairings? The other and one other observation. You mentioned something about trusted setups. There was a nice talk yesterday that pointed out that trusted setups are not at all a problem for governments because we do these things all the time for DNSSEC. It's not, but also it can be used a bit like a certificate. And I wanted to point out that when you use Gross16, you can use re-randomization, so you get things like anonymous credentials where the prover time is tens of scalar multiplications.
Okay, so you asked like 3 questions, but let me go ahead and say the next talk is going to talk about re-randomizing Gross16. The problem with Gross16 is you still need about 1 gigabyte on your cell phone, and with 400 million European phones, it's hard to say that we should spend about 400 terabytes. You need a very large string. Whether you want to argue that it's 50 megabytes or 100, we all have to agree on a very large parameter, and that doesn't fit on. Google, for example, won't let us deploy something which puts 50 or 100 megabytes on the phone. The other questions you had about, I can hand them all offline. I don't remember them. So ask one, please, and we only have 2 minutes.
So just clarifying, the 1.3 seconds, is that every single time you would prove to the website? Do they give a new nonce and then you have to do a proof with respect to that fresh nonce?
So yes, I have a video to show you essentially, but every time you use this credential, it requires you to use for device binding, it requires you to do a biometric check. You have to actually unlock your secure enclave. And so that requires the thumbprint. So every MDL show, even without zero knowledge, requires a human interaction of a thumbprint. That's why 1 second extra for zero knowledge isn't relevant in this type of user flow, because it can be hidden even though we don't hide it. But the point is a human action has to be taken, which is on the order of seconds anyway. And that's required for the security of device binding.
Last question.
Could you show again what the size of the proof is and the verifier time? And maybe
The size is roughly 400 kilobytes, and the verification time is about 0.6 seconds. And that is because we use SHA-256. That's the post-quantum assumption that we use. If we use elliptic curves, we can use a smaller commitment and actually change those sizes as well.
Okay, awesome. Thanks again, Avi. We got a great intro for the next talk. Greg is from Microsoft Research, has done some really awesome work on anonymous credentials, zero knowledge proofs, and today he's going to be giving us another approach to building stronger privacy for existing credentials. Thanks, Greg.
Hi, thank you for the introduction. I'm going to tell you about our work. This is a joint work with Vamsi and Christian. So you've heard by now that mobile wallets are increasingly being used to store new, long-lived identity credentials in the workplace and in education, as well as the mobile driver's license. And some of these newer credentials do have privacy features, but they generally fall short of unlinkability and falling short of, in particular, what you would get with anonymous credentials. So most of these standards are currently not using anonymous credentials. So our question is, what can be done for privacy with what we have today? So Crescent is our design and implementation for adding strong privacy features to existing credentials. And the main constraint we're working under is that the issuers don't change what they do. So they may not even know that Crescent exists. So there are two issuers on the left here, an employer and the DMV, and they'll issue credentials to a wallet application that will generate zero knowledge proofs and send these to verifiers. So these are screenshots from some samples we put together to sort of illustrate how this might work. In the first case, the user is proving that they work at a specific company in order to get access to an employer-provided benefit. And in the second case, they use their driver's license to prove they're over 18 when opening a new social media account. So to make this concrete, I'll use the workplace example as a running example. And this is what the credential might look like. So you have a list of attributes about the user. And these are all signed with a standard signature algorithm, in this case, RSA. Then for the proof of employment, what we have to do is reveal that the email address ends with the employer's domain and that the expiry date is in the future to show that the credential is not expired. So let's start thinking about this if we were to use Groth 16. So the credential is an input, we generate the proof and send it to the verifier. The circuit for this would have to verify the issuer's signature, decode the information, parse out those attributes, and apply the two predicates we need for our example. So this has been demonstrated in prior work like ZK creds and ZK login. So we know this can be done. And we also know the drawbacks, that generating these proofs is quite slow, can take tens of seconds. And then if a different verifier came along and asked to know something else about the credential, we would either need a very general circuit or multiple circuits which isn't very flexible. So the approach in Crescent is based on this simple observation that a long-lived credential is presented many times, and most of the prover's work in generating the proofs is repeated. So our question is, can we reuse this prover work and maintain unlinkability? In the example, we have about 1.5 million R1CS constraints, and most of that is for the signature verification, which is going to be static over the life of the credential. So we have a two-phase approach where there's a first phase where you take the credential as input and you prepare some user state. And this is done only once, and it may be slow. And then there's the second phase where you run this every time you present the credential, and it's much faster. So we'll need a specific property of Groth16 proofs. So let me introduce just a little bit of notation. The proof is 3 group elements, A, B, C. And then there's this value L, which you can think of essentially as a Peterson commitment to the circuit inputs and outputs. They satisfy the verification equation. And it was shown in the ZK Creds paper that you can re-randomize these proofs and then only pay this is the main idea we'll use to reuse the prover's work. Right, here's an overview of proof generation. So as I just said, we have the prepare step, which starts by creating this Groth16 proof. That's the user state. And now at this point, the proof and this vector of attributes is a lot like a signature on attributes. So it's very similar to BBS in the green section of the overview, except that the attributes are defined by the circuit. Like the one attribute is derived from the email attribute. So now the verifier needs this commitment L, and it will recompute part of it from the public information and also using data from the prover. And the prover will also provide a short sigma proof that what they provided was correct. Next, we can have a set of sub-provers which prove different things about the attributes. Each of them will take a Peterson commitment to one attribute and do their work using that. And so this is a nice flexible architecture, we think, because these sub-provers don't need to know anything about the circuit or the other sub-provers. It's very modular, flexible. So range proofs and selective disclosure are kind of well known. So I'm going to spend more time talking about the sub-prover we use for device-bound credentials. So as you heard, these identity credentials are often device-bound, and this means the credential has a key pair associated to it. The public key is in the credential, and the signing key is stored in hardware, in a TPM or a secure element, for example. And the goal is that if you don't have the device, you can't use the credential, and this is going to help prevent things like credential theft. So we implemented support for device binding with ECDSA, and to update our running example means we would have a public key attribute in the credential as well, something like this. So just at a high level, let's look at how authentication would work if your credential is device bound. So in the non-zero knowledge case, we start with the verifier choosing a random challenge, sending it to the user. The user asks the device, please sign this. And then they return the credential and the signature to the verifier. The verifier gets the public key out of the credential, checks the signature, and then does whatever other checks they would do on the credential. In the Crescent case, things start in the same way, but now the user is not going to return the credential. They'll instead return a Crescent proof, and there'll be a sub-proof, pi2, that proves they have a signature from the device. So the challenges here are that the verifier can't learn the signature or the public key. The device is a standard device. We can only expect it to do standard ECDSA. And we need this proof to be fresh every time we present the credential. Okay, so that's sort of what we want to prove. I'll say a little bit about how we prove it. So we want to choose the proof system we use for ECDSA very carefully. In particular, we want it to have support for arithmetic circuits modulo the P256 prime from ECDSA. So we use Spartan on the T256 curve for this, and then we can prove a scalar multiplication in about 2,700 R1CS constraints. We also have the public key committed in the Gross16 group, and we need to use that in the Spartan group. These are different groups. So at a high level, what we do is have a commitment to the public key in both of these groups, one with Peterson, one with the Poseidon hash function, and then we prove that they're committing, in fact, to the same message. This is done with a small sigma proof and about 2,000 constraints in the circuit. And so this is a general technique. You could use it for other data as well, too, if you had a subprover that you wanted to use. Okay, and then finally, in our paper, we described an alternative way to do this where you can pre-compute a snark that depends only on the device public key. So this is sort of the expensive part. So we can pre-compute it, and then when we use the credential and we have the signature, we only need to finish the proof with a short sigma proof. Okay, our code is available online. It's mostly written in Rust. The circuits are in CIRCOM, and we were able to leverage a lot of great existing code, so we didn't have to start from scratch. Okay, I'll show some benchmarks for this running example of proving employment. I've got BBS estimates here on the slide, but I'll just remind you that BBS doesn't work with existing credentials, so it's not really a direct comparison, but it just sort of gives a little context. So I've also highlighted for Crescent the trade-off that's inherent. So the offline steps are pretty slow, but then the online steps are much faster, and the proofs are quite short, so short enough to fit on a QR code. Now, if we add device binding to the example, the costs increase, but arguably still efficient enough for a lot of practical scenarios. I'll mention one thing for future work. So, it's great that we've reduced the number of times you have to compute this Groth16 proof just to one, but, realistically, there will be devices that just can't manage this. And so we'll probably have to have an option to outsource this proof. And we want that to be secure and private, of course. So for security, we're in good shape because of the device binding. The outsourcing service can't use the credential without the device key, but they might see the attribute data. And so we need a way to keep this private. Confidential computing is, of course, one way to do it, but there are probably other interesting ways as well. Okay, so to conclude, Crescent is a nice combination of mostly known techniques into a complete credential system that doesn't require any new issuers. And we feel the efficiency trade-offs are a good fit for these long-lived identity credentials. And this is an ongoing project, so if you'd like to get involved, just let me know. Thank you.
We have some time for questions.
Hi, Greg. Yeah, nice talk. Actually, more like an observation on the session in general. Almost everyone mentioned hashing as a bottleneck, and most of you guys also mentioned Poseidon. It's not a standard. NIST is not really interested in running a new hashing competition. What should we tell them? Wouldn't it be useful to have something that is standardized and helps deployments?
So for example, using Poseidon to hash the credential, or when signing the credential.
Yeah.
Yeah, I don't know how that would land at NIST, but we could talk to them. I think one challenge with that is that you have to fix also the prime.
Yeah.
So if you wanted one prime for many proof systems, that could be tough, yeah.
So could it help if companies that end up using this a lot or individually write to NIST and ask for standardization?
Sure. Yeah, that sounds like, sounds like a good idea. And I guess in smaller settings, like individual identity providers might choose to do something less standard.
Thanks.
Thank you.
Yeah.
Hi. I just wanted to point out the re-randomization technique from ZK Creds, which was our paper, was exactly meant to be able to do all this work reuse. And I'm pointing it out not in the dickish, please cite us, because I believe you did, but I think that's a paradigm we should run with. And I wanted to ask you, can you compose these techniques with some of the other faster ECDSA signature verification proofs that people are talking about in this session?
Yeah, I've been talking with the authors of the next session's paper, and we're actually using some of their code, some of their techniques. Yeah, so maybe we can discuss that offline. I think, yeah, hopefully there's something we can do there, but.
Because yeah, it seems like we'll converge on this. Somehow you do the proof and then you reuse it a bunch of times.
Right.
Okay, thank you.
Thank you.
Last question.
So if you, okay, so you don't actually have a very large trusted setup here in the first place. If you needed to outsource the GROS16 proof, would the device binding even be possible? Like if you can't, like you have a device, I guess you mean like a card or something that really just can't do that GROS16 proof even given some extended period of time. Can that device even do this device binding at all?
The device binding proof doesn't require large data or a large time to compute. And when you're generating the GROS16 proof, you don't need the device secret at all.
Sure. Okay. All right. Thanks. That's the answer. I was just curious because it seemed like the device binding proof is pretty time sensitive is all I was.
Okay. Yeah. Thank you.
Awesome. Thanks again for the great presentation, Greg. Okay, last but not least, we have Poyoung Anna Wu, who's a master's student at University of Michigan, and Chad Sharp, who is a PhD student at University of Michigan, who will present zero-knowledge proofs for legacy signatures. So welcome on stage.
Hi, everyone. Today, we are going to talk about how to transform existing signatures into his advanced one. And the results come from two papers. One is at Oakland this year, and another one is forthcoming. Signatures is very important in ensuring the trust, authenticity in the modern system, but sometimes we want some advanced guarantees. We might want proof of possession to prove to you that we have a valid signature message pair issued by the signer without reviewing the signature or the message. These advanced signatures enable different applications, but to make these applications practical, we want fast signer, fast verifier, and small signature. One approach is to create tailor-made signatures for this purpose. But so they can be very efficient, but we often have real-world constraints that make it difficult to change the legacy signer. So we want legacy compatibility. The existing solutions are slow in our setting, so we want both efficiency and legacy compatibility. And this is especially difficult for post-quantum signature. We want to maximize the legacy compatibility. With a standard signature, the user can create an advanced signatures, such as proof of possession without accessing to the secret signing key or changing the signer. Our approach is to express the policy of the advanced signatures in the CK-SNAC circuit, and we target a general constraint system like RNCS. CK-SNAC provide privacy and small proof for us, but operations like signature verifications are very expensive to be represented in the CK-SNARK circuit because these involve hashing and elliptic curve operations and so on. So we need to find a way to efficiently represent those operations in the CK-SNARK circuit. So we efficiently represent those operations in the CK-SNARK circuit, and we additionally move the expensive operations outside the CK-SNARK circuit. This led us to have a proof of possession for RSA or ECDSA with 2 kilobyte message in just 3 seconds. And the proof size is less than 0.5 kilobyte, and the verifying time is less than 30 milliseconds. And our techniques can be applied to different legacy signatures. In this talk, we'll focus on how to efficiently represent the modular arithmetic and rejection sampling in the CK-SNARK circuit. And we'll also talk about how to move the expensive operations outside the CK-SNARK circuit. So the signature verifications mainly involve hashing and algebraic operations. We need to efficiently encode both in RNCS. In this talk, we'll focus on the algebraic part, specifically the modular arithmetics. Doing the modular arithmetics is difficult in the CK-SNARK because we need to use the field of RNCS, which is usually what we want to do for the modular arithmetics for. So we either need to use the right field or we emulate the modular arithmetics in a one field. And we'll do both. For the first approach, we use an existing T256 curve to create CK-SNARK with his native field the same as the base field of the P256 arithmetics. We also create a new T25519 curve for the curve 25519 base field arithmetics. And this leads to around 300 times reduction in the R1CS constraint cost. But it is incompatible with some CK-SNARK, and this only works for large prime modulus. So we need some progress on the one field modular arithmetics. So we want to emulate the modular arithmetics in the modular M road. So at a high level, we split each number into limbs to avoid overflow. Then we use mod M operations to do arithmetics and mod P reduction. A very important subtlety here is that we need to check that each limb in input and intermediate values are in the range. And a standard method to do that is the bit decomposition, which costs 1 constraint per bit. And this contributes more than 90% of price state-of-the-art RNCS modular exponentiation. We use a new technical tool called lookup argument to largely improve the performance. And the lookup argument allows us to check the hidden values are in a public table. So we can reduce the range check program into lookup. So we create a table listing all possible values in the range. And then we check that each of the limbs is in the table. It seems that we are done because originally we need 1 constraint per bit, but now we only need 1 constraint per limbs. But to make this practical, we actually need to tackle some of the engineering and technical challenge, which I don't have time to mention here, but we get 4 to 5 times reduction in the R1CS constraint cost. So we have optimizations for modular arithmetics, but there is still, algebraic operations are still expensive in CK-SNARK, such as when we want to do the elliptic curve operations. For ECDSA and add to 5519, the elliptic curve operation, like the prefix base scalar multiplication, is especially expensive, and it costs around 80% of the cost. So we want a new techniques to offload the elliptic curve operations outside the CK-SNARK circuit. So we offload them to a Sigma protocol. But now there are 2 issues. First, we need to ensure that we need to prevent a malicious prover from provide different input to CK-SNAC and the Sigma protocol. And we also need to build a new Sigma protocol that is more efficient than we do the elliptic curve operation in the R1CS. So to tackle the first issue, we use the commit and proof variant inspired by Sigma Bus. And for the second issue, we developed a new Sigma protocol for elliptic curve algebra. So now the expensive subcomponent in the CK-SNAC is replaced by just opening commitment and verifying the prover of the Sigma protocol in the CK-SNAC circuit. So now we can exchange the dynamic-based scalar multiplication in the CK-SNAC circuit for a cheap Sigma protocol outside the CK-SNAC circuit and some SNAC-friendly hashing in the CK-SNAC. So this makes us have 4 times saving in terms of the constraint cost. Now I'll pass the time to Chad.
Hi, everyone. So at first, it might seem a little bit strange to refer to any post-quantum signature as legacy because they're not in widespread use. But what we really mean by legacy post-quantum signatures are signatures that we expect future cryptographic infrastructure to be built on top of. And so to this end, we have implementations for both Falcon and dilithium. Sphinx is a future work. In general, the algebra is easier to encode for the post-quantum signatures on account of the much smaller modulus and the frequent use of linear operations like NTTs, which are more or less free in R1CS. Norm bounds have to be computed for these verifiers, but with lookup arguments, this is almost trivial. Hashing is much harder for these schemes, both because a more expensive hash function is used in the form of Ketchik, but also just more bytes need to be hashed. And finally, whereas in the pre-quantum schemes, getting a ring element out of the hash output is a simple matter of modular reduction, more complicated techniques are used in the post-quantum signatures, such as rejection sampling, or in the case of dilithium specifically, a Fisher-Yates shuffle. So for this talk, I'm going to talk about how we handle rejection sampling, which is common to both Falcon and dilithium. So to refresh, the goal of rejection sampling is given a list of values, which you can think about as coming from a hash. We want to return the first n of them that are less than some cutoff c. And it's crucial that their order remain the same. So in this example, we want to take 3 elements that are less than 25. We would select 28 and 15 in that order. And if you were going to implement this in bare metal, this would involve a lot of dynamic accesses to memory, which would be very inefficient to encode naively in a snark. So our main goal, or our main technique, is to augment the values in the original array with a Boolean that indicates whether it's above or below the cutoff, and this can be computed with efficient range checks, and also its original index in this array. And then we have the prover provide a sorted version of this array where the values are sorted first by the Boolean and ties broken by the index. Then we have to verify that what the prover gave us is actually sorted. And again, with range checks, this is just a matter of checking that the difference between adjacent elements is non-negative. And then we have to verify that what the prover gave us is a permutation of the original array. And we'd use basically a standard technique here where we encode the values as the roots of a polynomial and then do a polynomial identity test. After that, we can just take the first n elements of the sorted version, and that is our solution to rejection sampling. So for 100 16-bit values, this costs about 1,300 R1CS constraints, and considering we're doing this on the output of a very expensive hash, this effectively becomes a rounding error. So as I mentioned, hashing is really, really expensive, and dilithium is a particularly egregious example when it comes to hashing. So on screen, I have a simplified version of the dilithium verifier, and you don't have to understand everything that's going on here. The main point is that what I've highlighted in bold are all calls to Ketchik. And so as you can see, there's quite a lot, and we would like to move as much of this outside the circuit as possible. So let's first consider the proof of possession case. So I've highlighted public inputs in blue and private values in red. And you can see immediately that we can move this expand A call outside of the circuit because its input is public. So instead, we could just take A and T as the input to our verifier. But this is sort of all we can do, or it seems like this is all we can do, because the rest of the hashes here all take private inputs. So proof of possession is going to remain still pretty expensive for dilithium. Okay, let's switch over to the ring signature case. The ring signature case, the verifier is substantially the same, except you also check that the public key is in some public Merkle tree. And if we perform the same coloring exercise, now the public key is private and the message is public. At first blush, it seems like we're in a worse position because every hash involves at least some private input. But okay, I said the public key was was a private input. It is part of the witness for the snark, but we reveal some information about it. We reveal that it's in the ring, of course. And so you could run expand A for every public key in the ring, and then just verify that the expanded public key is in the Merkle tree. So if we do that, we immediately can remove the expand A call, and then we can note this, these hashes that are used to generate mu are, the inputs are either in the Merkle tree or are public. And so we can similarly move that hashing outside of the circuit. And as long as the ring size is not very, very large, this is almost always worth it. But once we've done this, and now we can also get rid of the public key because we don't use it anymore. And now once we've done this, it seems like we're sort of at an impasse because there's this almost circular dependency in the code where C is a hash of C hat and W is some algebra in C, and C hat is then a hash of W. So it's sort of unclear if we can do any better than this or if we're stuck with these two hashes left in the circuit. And as it turns out, we can do better. And the key thing to note is that this high bits function in dilithium is very, very compressing. So for typical security parameters, Z and C are going to have about 18,000 bits of entropy. And because we're only taking a very small number of the high bits of the result, W only has about 6,000 bits. And so this is, W is statistically close to uniformly random. And what this means is that it doesn't reveal any, that the high bits of AZ minus CT don't reveal anything about the public key. And so we can just publish it. And so if we publish it, this breaks the cycle that I mentioned before. Now C hat can be computed outside of the circuit. And because C hat can be computed outside of the circuit, so too can C. And what we're left with is no more SHA-3 inside the circuit. And so what we're left with is just algebra, norm check, and some snark-friendly hashing in the form of Poseidon. So this is very few constraints. In general, we suspect that the same technique would work for any kind of Schnorr-like scheme, as long as the prover's first message, which in dilithium's case is W, doesn't reveal any information about the public key. Okay, on to some results. So we can do a proof of possession for a message length 64 bytes for ECDSA and 82519, both in less than a second, with a proof size that's less than half a kilobyte. 82519 is basically always going to be a little bit more expensive for the prover because it uses SHA-512 instead of SHA-256. For our ring signatures, Falcon and dilithium, for a ring size of 64, the prover time is 1.2 and 6.2 seconds, respectively. Although this first value is entirely hashing the leaves of the Merkle tree, and it's largely due to a pretty unoptimized Poseidon implementation that we're currently using. So we expect this number to come down quite a bit. And in any case, if you're doing many verifications for the same ring, this could be amortized away. Now, so this is with pre-quantum soundness and statistical zero knowledge for the post-quantum schemes. Post-quantum soundness is a work in progress, although because we're targeting R1CS, our techniques generalize to a post-quantum snark for R1CS. So the main takeaways here are legacy-compatible advanced signature primitives are practical or nearly practical for many applications. Efficient range checks are very powerful. They really open the door for sort of non-native field operations. But hashing remains a bottleneck, at least in the cases where we can't remove it from the circuit entirely. Thanks for listening. We're happy to take questions.
Sorry, we have time for just one question.
Do you have a proof that the modification to dilithium to publish W is still secure under the same assumptions?
We have a proof sketch.
Someone can check it.
All right, let's follow up with the coffee break, but let's thank our speakers. And then really quickly, before we break for the coffee break, we have one lightning talk that could not make it into tomorrow's session. I want to welcome Yarkin from NVIDIA on stage just to give us a really quick ask for the cryptography community.
Thank you. I will make it quick. Hi, everyone. My name is Yarkin Doros, and I'm a product manager for crypto libraries at NVIDIA. I wanted to reach out to the crypto and developer community to announce that we recently released a GPU-based cryptographic library named QPQC. We are adding more crypto primitives to improve our functionality to serve you better. We want to hear your thoughts, feedbacks, and feature requests and make our library more useful. You can download the library from developer.nvidia.com/QPQC and feel free to reach out to us. My email is ydoroz@nvidia.com. Thank you.
Awesome, thanks so much. All right, and I think we are good to break for the coffee break.
And Carlos?
You test your mic a little.
Okay, when I speak, I hear nothing. Yeah, okay, great. Let me set up timer. Yep.
Did they give you a clicker?
No, that was an important part.
Oh, over there. Okay.
Okay.
Okay, people, please get seated. And this is the session on post-quantum deployments. And as you are getting seated, here we have Carlos Melchor from Sandbox, who will be giving the talk on post-quantum DNSSEC. We know that DNSSEC is complex enough, and post-quantum, well, I mean, let's hear what he has to say.
Okay, thank you. So, yeah, I have less than 20 minutes for the presentation to leave maybe some time for questions, and 51 slides. So, of course, the full deck is not intended for the presentation. I will just jump to 5 different points in the presentation, but there isn't a paper associated to this work, so I wanted to have enough details for anyone who wants to dig back into slides. There is a lot of details I will go over. I will not show many technical stuff, what were the exact choices, where did we embed keys, and all that part will be hidden. I will mainly be focused on 3 questions. So the first question is whether or not PQC signatures are a problem for DNSSEC, or this is again some FUD about the PQC transition, everything is going to break, et cetera, et cetera, et cetera. So the second question is whether or not there are easy alternatives to PQC signatures in DNSSEC. And the third question is whether the IETF work groups responsible for DNS are going to do something about this, because of course, we know naturally they are very skittish about modifying DNS, which is a very, very sensitive system. So let's do the first jump. Here. So I guess most of you know how DNS works or wouldn't have come to this session, but there are some small details that are important here. So DNS is about transforming a domain name into an IP address. And how does that work? Basically, a client in your computer or in your phone is going to ask someone in the network called a resolver. How does the client know this resolver? It came with basic configuration with DHCP. When the network was configured, your system was told what was the resolver for your network. So your client pings that resolver and say, hey, I want to contact this domain name. I would like to know the IP. And then this resolver goes all around the web to find DNS servers who had that information. Those DNS servers have a file called a zone file that has tons of information like this domain corresponds to this IP. So they have all that information for a given domain they're responsible for. And potentially, they also have signatures of that statement, like this domain corresponds to this IP and associated signature. That's what we call DNSSEC. So if the resolver understands DNSSEC, it will tell that to DNS servers. And the DNS servers, instead of saying, trust me, is this IP that is associated to this domain, they will also send a signature proving that that is true. If the resolver checks the signature and everything works out, he will set a special bit to 1. It's called the AD bit. And say to the client, yeah, I verified all the signatures. They are all right. I won't send them to you because they are big. Just trust me. So this generates potentially a lot of traffic here, especially if the signatures are large. But in here, you don't necessarily have a lot of traffic. So the client can tell the DNS resolver, okay, I trust you, but send me the signatures in case. That's what we call the DNS OK bit or DO bit. So our assumption is that with PQC signatures, this traffic will grow and it will cause problems. If the client sets the DO bits and this traffic grows, maybe it will cause problems too. So we are going to check that. And finally, the client may ask a question for a domain on a resolver for a domain that doesn't exist. If that happens, then these servers can prove that the domain does not exist. They will send a proof of non-existence. There are two possible protocols, NSEC or NSEC3. And we are going to check whether with NSEC or NSEC3, because this traffic grows, then maybe the amount of failures we will observe will also grow. Okay, ready for the next jump? Yeah. So what did we do? We modified the two gold standards for DNS, which are bind and power DNS. One of our co-authors is in the bind team. We use OpenQuantum to be able to use post-quantum cryptography in those programs. And we use the RIPE Atlas network. How much people does know the RIPE Atlas network here? Yeah, quite a few, in fact. So RIPE Atlas is, if you like networking, is a fantastic thing. It's tons of probes, small computers, Raspberry Pis, all around the world, in houses, universities, companies, that you can use to test a protocol, to connect to a server of your choice with that protocol, and see if in those real world networks there is a problem or how your protocol behaves in those networks. So from out of those clients, the protocol is going to traverse in real world networks, middle boxes, firewalls, intrusion detection systems, all sorts of things that may generate problems. So this is what we call that's a real world test in some of our slides. And the other thing we did is we collaborated with a major company that has very large DNS systems and checked how it would work with those very, very, very large DNS zone files. So we had like many probes, many tests, and this is what happened. So basically, if you use DNSSEC with a classic protocol, here, the first two protocols here, you have no problems. Those very 0.1% of problems is probably more instability of the Atlas network problems than real issues with the packet size. As we see, it also can appear even if it's not signed. But then there is a very significant jump, like a factor 10 to 20, when you introduce PQC. Falcon is roughly 100 bytes, 1,500 bytes. So this is one or a few hundred bytes. This is 1,500 bytes. This is 3,700 bytes, 3,700 bytes. This is 80, etc. Those are very big signatures. And what we observe is that problems appear already with Falcon at 1,500 bytes. It's not the end of the world, but it's enough for us to want to address it. Then when you jump to dilithium, well, it's the quantum, post-quantum, Armageddon, etc. Nothing works. I mean, this is very bad. It's not acceptable that you fail in 1 out of 3 or out of 4 DNS queries. So there is a problem. That's the first thing we observed. And our assumption that this would be linked, it would be worse in situations in which there is more traffic, like the DO bit in which the client requests the signatures. Well, yeah, indeed, we pass from 20-something to 30-something. And if we want to prove that something doesn't exist in a DNS server, then with the NSEC protocol or NSEC3 protocol and setting or not setting the DO bit, then we see that we are between 30 or even 40% of errors. So really, the size creates failures. And those failures are really, for anything bigger than Falcon, like very, very significant. Okay, so that's the first answer to the questions I wanted to address. So you can try it yourself. Go there, you can do tests, the DNS server is available, you can have a PQC DNS if you want. Okay, let's jump to the second part of the talk. So what if we think about using something different, slightly different than DNS, than PQC signatures? We don't want to make something very different because we want only to have small changes in DNSSEC. So there is one approach that was proposed by VeriSign, which was using some Merkle tree ladder signatures. There was some IP protection and IP release, all that. I will not dive too much into that part. I want to do something that's simple with known stuff. So what would be very simple with known stuff? So I don't want to go very deep in the details. We are going to use Merkle trees. So Merkle trees is basically hash trees, and you can prove that something belongs with a Merkle tree to a Merkle tree by giving a few hashes. Okay. So this is what we call a proof of inclusion. And basically what we thought is that maybe we can have one single signature in a special register that is generally cached in DNS that will contain the signature that says the zone file is right. And then all DNSSEC servers would have to prove is that a given name to IP relationship was in the zone file. Okay, so you only prove that one of the lines of that zone file is in the zone file. So basically, that's what we would do. We would hash the lines of the zone file, and we will just prove that a given line was in the zone file, and then always just give the signature of the zone file, which means the same signature that can be cached. And you only give proofs of inclusion into that zone file. So basically what you are doing is proving many statements with only one signature. And for every different statement, you just say, yeah, that statement is also on the sign file. So I'm going to jump directly. I'm not going to detail how we did that. There are many potential choices. So this is the first important thing. So if you just send proofs of inclusion with DNSSEC, then even for large zone files, the size of that proof is in the order in between RSA and Falcon. So we are below the danger zone. So let's jump to the test on the Atlas server. How did that work on a realistic normal? Well, it worked very well in some cases, not that well in others. So if we use UDP, the percentage of errors you get is still a little bit high. With TCP, it's very low. It's even it's roughly the same as with Falcon. But basically, the problem we observed is that our test network was like using many different probes for a server and would not cache the information. So every time they would get the zone file signature down. So that's a PQC signature. So we would expect some failures to happen. On the other hand, on TCP, it works very well. Why? Well, you have this situation in which if you are going to get multiple signatures, probably you are going to use TCP. And at that moment, the cache mechanism ensures that you won't get two PQC signatures. You will get one PQC signature and multiple inclusion paths. And then we are like in a much better position because like we are really reducing the size compared to getting multiple signatures. And that's what happened here with TCP. So basically, if you cache things, it works super well. If you don't, it works a little bit, but not as much as we would like. Sorry. So I'm going to jump to the to this example from a real-world DNS zone file. But it's a very large zone file. It has 6 million signatures. It is 200 megabytes, but it's a real zone file. Basically, if you sign it with ECDSA, it becomes a 1.6 gigabyte zone file. If you sign it with Filecon, 7 gigabytes, with the lithium 33 gigabytes. But basically, if you add a Merkle tree to it, the size is really almost as small as unsigned. And in fact, the real extra size that you need to put in that file is only the PQC signature of the tree. You don't have to include the tree. In fact, anyone, when loading the file, can hash the lines, construct the tree. So in fact, in reality, you can go down to this. No, but even if you write down the tree on the file, you get very, very, very small zone files. The time to sign is to renew all the signatures is also much, much more efficient. You create a single tree, and in basically 2 minutes, you can resign a file that is huge. And that happens a lot. There is a lot of DNS providers that would resign their zone files every day, or even some of them every hour. So being able to do that fast is important. And so there is a performance gain there. And I'm going to jump to the so again, there are many details for the ones who want. I want to jump to the conclusion. So the third question. This work was initiated by DSEC, which is an NGO that works on DNSSEC and is very involved at IETF. They came to us, asked us if we could collaborate on this. And so we had a resident, Jason Gordon, that was working already on DNS stuff. And so it was a great fit. But it was really motivational. What we wanted is, shall people be looking into this, no? And especially, shall the IETF be working into this? And I'm very happy because there is a regular side meeting that has been created at the IETF on this subject. There is further tests that have been done recently. People have been trying Hoke, Mayo, because they are in the right zone. How would it behave with it? And there is a lot of thinking about these potential evolutions of DNSSEC. So, of course, there are many things to do. And it will take 10 years probably, because we are speaking of DNS. But there is quite a lot of hope of finding solutions here. Thank you.
Thanks for the great talk. And I see that we have somebody with a question.
Yes, thank you. This is great. 1-2% is already too much failure rate.
Yeah.
Do you know how much it is if you use Mayo?
So I don't have them. I know there have been tests recently. Unfortunately, I could not get the details about those tests. So yeah, I think that's an avenue. But there are other potential credible avenues. I think MTL proposal is credible, and there are some variants of this Merkle tree approach that would also allow to gain a little bit, reduce a bit to below 1% on Falcon usage. But these numbers have to be taken lightly. This is the RIPE Atlas network. I mean, we should really make a large-scale, realistic test on this to be sure of what are those numbers. So I think there is a lot of things to dig. The idea is that this motivated looking into it, no? But now we have to really seriously decide whether Falcon fails at 1% or at 2 or at 0.2 if you do it right, no?
Kind of related to that. Oh, can I ask a question? We have time?
I think we are out of time. So, Barun. So let's thank the speaker again.
So this is a description of how post-quantum affects SSH. What happened to your title slide?
Um, m- my slides are not here.
And as they are getting ready, and so this is a post-quantum cryptanalysis of SSH by Varun Maram of Sandbox, and we will welcome Varun.
Yeah, thanks for the introduction. Hello, everyone. So sorry to disappoint you, but it's not about crypt analyzing SSH. So we're not breaking SSH, but it's like proving that SSH is secure in a post-quantum setting. So I'm Varun, a postdoc at Sandbox AQ, and this is based on joint work with Benjamin Benchina, Ben Dowling, and Keita Kusagawa. So first, before I begin, why analyze SSH in the first place? Well, if you ask ChatGPT, then SSH is the second most important real-world cryptographic protocol after TLS, of course. But it is our belief that, at least compared to TLS, SSH has not received as much attention over the years. For example, if you consider real-world crypto, then across all previous editions, starting from 2012, there were at least 27 talks covering TLS. I had to check in the programs. But SSH, you only have 2 talks. So yeah. Anyways, like all jokes aside, SSH is an important security protocol in its own right. As ChatGPT again says here, it is used to obtain secure remote access to servers. It is widely used for encrypted file transfers, for VPN access, etc. Now, before I discuss our analysis, so let's first see how the protocol works at a very high level. So again, as it's mentioned here, like SSH uses a mixture of public key cryptography and symmetric encryption. So in more detail, an SSH client and an SSH server, they first exchange some messages at the start in a so-called handshake phase. Then they generate some identical session keys using public key cryptography. And then they use these keys to communicate over a secure channel in the so-called application data phase using symmetric encryption. Now, in older versions of SSH, the so-called Diffie-Hellman key exchange was used in the handshake phase. But by now, we know that since it is not secure against attackers having access to large-scale quantum computers, so in current versions of SSH, they adopt the so-called hybrid paradigm. So in hybrid paradigm, you combine this Diffie-Hellman key exchange with a quantum secure key encapsulation mechanism, or KEM. So the basic idea here is that we want the overall hybrid key exchange to be secure as long as one of these red components or green components is secure. So I guess you'll be hearing more about this in the next talk. And actually, SSH is one of the first protocols on the internet to adopt this hybrid paradigm on a large scale. For example, certain implementations such as TinySSH added support for hybrid key exchange even back in 2018, when the NIST PQC process was still at an early stage. And even mainstream implementations such as OpenSSH made this hybrid key exchange to be the default option in 2021. However, if you look at like prior analyses of such post-quantum versions of SSH in the literature, then there are like 2 classes of work. So one class of work, for example, this work by Petcher and Campagna, they only focus on this hybrid key exchange in isolation, and they do not extend their security analysis to capture security of the overall protocol. For example, they don't include application database in their analysis. And on the other class, so the works which attempt to like do an overall protocol level analysis of SSH, they do so in not the right models. For example, this work by Blanchet and Jacom, which was published last year, so they analyze SSH, they model SSH as an so-called authenticated key exchange. But the problem is, in practice, the handshake phase and the application data phases are not as clearly separated as I showed in the previous slides, but they are somehow interleaved. So this interleaving of phases makes it non-trivial or even impossible to analyze SSH in these authenticated key exchange models. Great. So now this brings me to our work. So our first contribution is that we show the current post-quantum versions of SSH as used in practice, such as OpenSSH or TinySSH, are indeed cryptographically secure against quantum attackers. But there's a small caveat here. So we don't include some low-level implementation details in our analysis, which, for example, were used in the so-called regression attack against OpenSSH that came out last year. So at a very high level, this attack worked because of some implementation errors, so which we are not accounting in our analysis. So basically, we provide security guarantees on a structural level of the protocol, and we abstract the implementation level away. But we will revisit this near the final part of my talk. So first, the way we started our analysis is we started with an earlier analysis of SSH by Bergsma et al. In 2014. So the authors, they analyzed SSH not in an authenticated key exchange model, but in a model called Authenticated and Confidential Channel Establishment, or ACSE model. Then they established security of SSH in such a model. ACSE model was also used to analyze TLS 1.2, for example. However, their analysis only covers for the older versions of SSH, which only used Diffie-Hellman key exchange in their handshake case. So essentially, in our work, we extended their analysis to also capture the hybrid key exchange as well. But first, we introduced a post-quantum extension of the ACSE model to account for so-called harvest now, decrypt later attacks. And then we established security of SSH in this in our post-quantum ACSE model. And we also capture forward secrecy in contrast to the prior 2014 paper. In more detail, so our post-quantum ACSE security proof for SSH relies on the underlying primitives satisfying some standard notions of security that I show here. So then we adopt this top-down approach where then we proceed to show that current instantiations of these SSH primitives in practice, they do satisfy these standard notions of security in a post-quantum setting. Good. So now this brings me to the second contribution. So after giving a security proof for post-quantum SSH, we then identified some ways in which we can make the protocol a bit more efficient while having it consume fewer resources. So to understand our second contribution, so let's revisit the work by Blanchet and Jacome, where in their analysis of SSH, they rely on the quantum secure chem to satisfy this notion of in-CCA security. And the authors claim that they required this notion to ensure forward secrecy against quantum attackers. But as I mentioned before, the authors are not using the right model to analyze SSH. So this was kind of like our reaction after reading the paper. Like the authors did use some cool machine-aided techniques in their analysis, but because of their choice of the security model, it led us to believe that perhaps this in-CCA requirement is probably an artifact of their proofs. Fast forward to our analysis of SSH that I showed a few slides ago. Note that we only required the underlying quantum secure chem to be in CPA secure, which is a weaker notion of security. And now we are getting somewhere, because as it turns out that in practice, the quantum secure chems used by SSH, OpenSSH, for example, Streamline NTRU prime, or the current NIST standard MLChem, they are designed to achieve the stronger notion of in CCA security. And they do so via a generic technique in the literature known as the Fujisaki-Okamoto transform. So this transform at a very high level, it converts an in-CPA secure chem to an in-CCA secure one, and it incurs some performance overhead. So our analysis essentially suggests that this effort transform is strictly not needed for the overall post-quantum security of SSH. By doing so, perhaps you can get some improvements in the chem and improvements in the overall protocol. And as you can see here, we were quite excited with the prospect of making SSH more efficient. So we wanted to evaluate what are the concrete performance improvements we get in SSH when we replace the in-CC secure chems with an in-CP secure one. Well, we ran some experiments, but the numbers we got in the end were not great. For example, we did get like a 52% speed up when we replaced the FO transform in MLChem with a simple transform. But this is only when we ran the chem in isolation, but not as part of the overall SSH protocol. And also in a non-hybrid form. For a protocol level improvements for hybrid chems, you can see that the numbers are not great. So expectedly, we were kind of disappointed with these numbers. However, if you go back to our experiments, then you can see that we only measured a single SSH connection. But considering the large number of SSH connections that happen per day worldwide, so these improvements should only add up. So just to give an example, so let's consider the number of hash computations that happen in the quantum secure chem in SSH. So it turns out that if you replace this F4 transform with a simpler transform, then you can reduce the number of hash computations by about 80% in the CAM. And there was a talk at Real World Post-Quantum Crypto Workshop last year by Meta, where they gave their PQC updates. So there it was mentioned that some trivial operations like extra hashing here or an extra hash there, it can cost a lot of money for big organizations. And it also comes with significant power usage and consumption in data centers. So these are the challenges when you have with large-scale deployments. So then we were, again, like shocked by these numbers, because this somehow shows the potential of like using in-CPS secure chems and the potential to like reduce costs significantly in the real world. But then when we described this aspect in our paper, then reviewer number 2 quickly gave us a reality check. So they said that actually it's TLS and not SSH, which is a major workload for Meta or even other big organizations. And it is really a fair point. But shall we now talk about TLS? So note that our paper, our work, we show that in-CPS secure chems suffice for post-quantum security of the overall protocol. But our work follows a couple of recent works that came in the literature, which show something similar, but even for post-quantum TLS too. They say that in our security proofs, you only require in-CPS chems. This brings me to the final part of my talk, which is more about a discussion about should we try to make post-quantum SSH or post-quantum TLS a bit more efficient by trying to replace the in-CPS secure chems with in-CPS secure ones. So I'll be talking about some obstacles towards this change. Okay, I have some time. Okay, so again, as I went back to reviewer number 2's comments, then very interestingly, then there was reviewer number 3 who said that actually maybe cryptographic protocols are not the major workload, but it's current technologies like AI and other heavier machinery. So again, this is not my personal opinion, but it's an opinion shared by someone in our community. So basically, so like crypto costs maybe don't matter as much. So is it worth putting in significant effort to make such changes, and what are the benefits we get out of it? So basically, what's the security benefit trade-off? Another reason why people would rather have in-CCS secure chems over in-CPS secure ones is because such chems, which are supposed to be ephemeral, might not be used as such in implementations because of some implementation errors. So as described in this IETF draft for post-quantum TLS, so the stronger notion of in-CCS security provides guarantees in such scenarios where chem public keys are reused because of possible potential implementation errors. So the question I would like to ask here is that instead of making changes to the protocol at a primitive level, can we somehow make sure that such implementation errors do not happen in the first place at a higher level by using some checks? In this way, we can say, again, we can safely use in-CPS secure chems as also backed up by state-of-the-art security proofs in the literature. But if you take a step back, then note that we are still pretty much talking about implementation details here. And as I mentioned at the start of my talk, we are not covering such details in our analysis. But as it turns out that in practice, sure, you come up with some cool cryptographic security proof, but maybe the proofs don't suffice, and we need to take into account the possibility of implementations going wrong. Well, sure, again, that's a valid point. But then why don't we are cryptographers, right? So why don't we approach this in a more systematic manner? So now why don't we redo our security proofs from scratch, but then we also extend our model to account for adversaries who can mess with the implementations in subtle but adversarial manner. So it's not a new model in the literature. It's called so-called cryptography. And so, yeah, maybe, who knows, maybe if one of you goes and reads all the proofs, it turns out that maybe even in CCA is not sufficient, but you might need something more stronger. Finally, the final obstacle that I'm talking about goes back to a discussion we had with some maintainers of OpenSSH. So after our proof, we were excited and we reached out to Damian Miller, who's a lead maintainer for OpenSSH, saying that, hey, we have this proof. It says that you can replace the in-CCS secure chems in OpenSSH with some more efficient in-CPA ones. Damian's response was he appreciated our analysis, and then he asked, are such in-CPA secure chems FIPS compliant? That was the end of the discussion. So, but then we had to like revisit NIST's original call to standardize post-quantum chems. And there it was mentioned back in the 2016 document that for ephemeral key exchanges, NIST will consider standardizing chems which only satisfy in-CPA security. So for applications such as TLS and SSH which use ephemeral key exchange, should NIST have a separate on-ramp process to standardize such in-CPA secure chems? What do you think? Thanks for your attention.
I think we are basically out of times, so we can take questions offline. And would our next two speakers come on stage? Let's thank the speaker again. So as they are getting ready, and we have Michael Rosenberg and Shannon Veach, who is going to talk to us about alligator-like PQ obfuscation, which is, I mean, let's leave it up to them. Go ahead.
Yeah, so today we're going to talk about tools that are used for protocols which aim to hide metadata. And this might be for protecting user privacy, dissuading protocol fingerprinting, or preventing network ossification. So for example, the TLS 1.3 ECH extension aims to hide target domains. Quick has deliberate anti-ossification properties by preventing or minimizing the wire image. And OBS4 and ShadowSox are censorship circumvention protocols which aim to prevent protocol fingerprinting by encrypting or obfuscating all the traffic on the wire. And in particular, when we're talking about key exchanges, we might call this an obfuscated key exchange. So these tools are also useful for some password authenticated key exchange protocols, which might need to operate over random byte strings. Previously, in particular for key exchanges, Alligator was used for mapping elliptic curve public keys to random byte strings. But for post-quantum protocols, the situation is a bit less clear. So if you're using Saber or FrodoChem, you're basically already good to go because these public keys in ciphertext already look like random byte strings. But the situation is not exactly the same for MLChem. So in this talk, I'll start with introducing our chameleon encoding, which takes MLChem public keys and ciphertext and maps these to random byte strings. Okay, so what do MLChem public keys actually look like? They're polynomials with coefficients modulo some value of q with a random seed appended at the end. So if we look at the frequency of this byte distribution, the y-axis shows the byte values and the x-axis the position in the encapsulation key. And then the color here represents the frequency at which each of these values occurs. So if we zoom in, we can see that the seed appended at the end of this public key is perfectly uniformly distributed, but the same is not true for the coefficients in the public key. So what's happening here is because Q is not a power of 2, every most significant bit of the coefficients in the public key are slightly biased towards 0, meaning that these higher byte values don't occur. So how does the chameleon encoding handle this? Well, we basically accumulate this into one big integer. Now, only the most significant bit is biased towards 0, but we can just do rejection sampling on this bit if it's equal to 1. So now our encoded public keys actually end up being about 2.5% smaller than regular MLChem public keys because of this accumulation. And the rejection rate here for MLChem 768 is about 17%, which is reasonable if you consider the fact that for Alligator, the rejection rate was approximately 50%. So what about ciphertext? You might think it's basically the same thing, but no, life is not that easy. These vectors of polynomials are actually compressed before being returned by encapsulation. And what this compression does is some rounding, where the output space does not evenly divide the input space. So if we look at the distribution of the coefficient values in the ciphertext, certain values of coefficients at a set period will appear more often than others. So to handle this, the chameleon encoding first undoes this compression. So we just decompress and then sort of artificially recover the randomness that was lost in this compression. And then we can use the same rejection sampling technique that we had for public keys. And because we have to decompress, we end up with ciphertexts that are 6 to 15% larger than standard MLChem ciphertexts. So that gives us our chameleon encoding algorithms with rejection sampling, but we also have a variant without rejection by borrowing a technique from the alligator squared algorithm. So here we take our accumulated large integer from before, and we basically pad this by adding a random value so that the output space is some power of 2. And then decoding is pretty simple. We just take the resulting value modulo the size of the original accumulated integer, and then we decode as usual. And because we have to add a little bit extra padding here, we end up with public keys that are about the same size as standard MLChem public keys. But now we no longer have this rejection rate. Okay, so we can take our chameleon encoding and naturally combine this with MLChem by encoding public keys in ciphertext to obtain what we call an obfuscated chem, or an OChem. And the security properties that we care about for OChems are standard in CCA security, SPR CCA, which means strong pseudo-randomness, and this captures indistinguishability of shared secrets and that ciphertexts are random or simulatable. And this implies standard notions of anonymity for chems. And then lastly, ciphertext and public key uniformity, which capture the indistinguishability of these objects from random bit strings. So our MLChem instantiation of this OChem satisfies all of these security properties, where each of these reduce to either a property of the underlying chem or a modular LWE assumption, with some small loss from the rejection rates in each case. So here, notably, these ciphertext and public key uniformity properties rely on a computational assumption modular LWE, whereas with Alligator, these were statistically uniform. Okay, so a couple important things to note if you're using Chameleon in practice. You might want to consider a constant time implementation for the, in particular for the big integer arithmetic, or if you're using the rejection sampling case. And it's important to be careful with how you're using the randomness used in these encodings. If the randomness is revealed, then it's trivial to distinguish the output from random bit strings. And in terms of performance, if we just look at the times for key generation, ML Chameleon key generation is approximately 3 times slower than standard MLChem and 2 times slower than X25519 plus Alligator and Sabre. But these are just rough preliminary estimates for now. So with that, I'll let Michael talk a bit about the hybrid case.
Thanks. So we've seen how to make an obfuscated key encapsulation mechanism that's post-quantum, but sometimes we want to hedge against attacks against new implementations because it's new code, and attacks against the mathematical underpinnings of these new schemes. So we want a hybrid obfuscated key encapsulation mechanism. That is a hybrid OChem that combines the classical hardness of an OChem with the post-quantum hardness of a separate OChem. So how do we do that? So let's look at how existing hybrid chems work. Essentially, every hybrid chem that exists right now is a chem combiner that looks like this. If you disagree, please feel free to CC me on the IETF mailing list. The public key is the concatenation of the 2 underlying public keys. And encapsulation is simply parallel encapsulation to the 2 public keys. And the ciphertext is the concatenation of the 2 underlying ciphertexts. And the final shared secret is the hash of the 2 shared secrets plus some other stuff. It is known that basically everything on the swarm gives you IND CCA security, but we want something more because we're making OChems, not just chems. So we want hybrid obfuscation. You can see that this doesn't have hybrid ciphertext uniformity, for example, because the ciphertexts are simply a concatenation of the 2 underlying ciphertexts. So if you can spot a non-uniformity in one of them, you've spotted a non-uniformity in the entire ciphertext. But maybe we can get some intuition here. It is not a priori necessary to reveal both of these ciphertexts at the same time, right? You might think maybe you can reveal just one of these ciphertexts and use some intermediate keying material to encrypt the other ciphertext, so you only have to reveal one and not the other. In addition, we'll note that sometimes ciphertexts are statistically uniform. That is, they don't rely on any computational assumption for uniformity. This is the case for Diffie-Hellman key exchange with Alligator encoding. So can we use this intuition to build a new chem? We have a combiner called outer encrypts inner nested combiner, or OINC. The public keys are the concatenation of the underlying public keys as before, and the encapsulation goes similarly as before. We have something that we call an outer OChem and an inner OChem. The outer one has unconditionally uniform ciphertext, and the inner one has just some notion of uniformity. It could be computational. So what happens is you do these encapsulations in parallel as before, and then you encrypt the inner ciphertext using the intermediate key from the outer OChem. This encryption is just a one-time pad. Then you concatenate the first ciphertext plain with the encrypted inner ciphertext, and the key is just the hash of everything as before. This gives you IND-CCA because the keys derive basically the same way as before. It's also quite cheap. It only requires a single KDF and an XOR operation. And it also achieves hybrid ciphertext uniformity, and I'll give some intuition for that right now. So suppose the inner OChem is broken. We can imagine the ciphertext and key are just 0, right? In that case, this XOR is still using good randomness from the non-broken outer OChem, and so the inner ciphertext, once it's encrypted, will still appear random. And now consider if the outer OChem is broken. Well, we only said that it's unconditionally uniform. So even when it is broken as broken can be, the ciphertext is still uniform. However, the shared secret might be 0. So in that case, the inner OChem, we assume, is not broken, and so this will still retain uniformity. And even if the key is 0, we have an XOR of a random value with possibly a predicted value, so we still have randomness. So this happens to achieve hybrid SPR-CCA security as well, which we show in our paper. And notably, this does not achieve hybrid public key uniformity because, again, the public keys are just the concatenation of the two underlying public keys. If you can spot a non-uniformity in one of them, you've spotted a non-uniformity in the entire public key. And we believe that this is inherent. It's not clear if you can even make a scheme that has hybrid public key uniformity. So concretely, you can instantiate the outer OChem with just DHChem like HPKE DHChem over the Ristretto prime-order group and Alligator 2 encoding. And this has a property which we define more rigorously in the paper of strong ciphertext uniformity. And the inner OChem can be instantiated with ML Chameleon, as we said before, or Sabre or Photochem.
Okay, so we can build a few applications from this chem combiner. In particular, first we looked at hybrid obfuscated key exchange. So the idea here is that we want all handshake traffic to appear indistinguishable from random. And typically we assume that honest clients know the server's public key and the adversary does not. And so this threat model has applications in censorship circumvention. So in particular, it maps to the threat model of OBS4, which is used as a Tor pluggable transport. And here the idea is that the transcript should appear indistinguishable from random so that it doesn't match any censor block lists. So our previous chem-based protocol required hybrid public key uniformity if it were to be instantiated with a hybrid OChem. And we know that this is difficult to achieve. So what do? Well, we constructed a new protocol which we call Drivel. The idea here is that the base of the protocol is an ephemeral chem encapsulation. So here this is just a regular plain chem plus a static OChem encapsulation. So here C1 in particular has ciphertext uniformity. And then the resulting shared secret is computed from these two input keys. So here, because the ephemeral chem is just a regular chem, we know that PKE and C2 don't have these nice uniformity properties. But what we can do is just derive a key from our intermediate chem key K1 and use this to encrypt the values PKE and C2. And then we no longer need public key uniformity. And actually, we get some nice efficiency improvements because for the ephemeral chem, we only need an int1 CCA secure chem. So this gives us our hybrid obfuscated key exchange protocol.
So this is my favorite part. How do you make a password authenticated key exchange protocol out of this? So let's recall what a PAKE is. It is a protocol wherein two parties have a shared low entropy secret called a password, and they want to use this mutual knowledge to derive a high entropy shared secret. It has two properties. Active attackers are able to guess the password if they are active during the session, and they have one guess at the password. And passive attackers essentially have no advantage at all. So there are plenty of chem-based password authenticated key exchange protocols that have been published recently. We'll focus on Cake, which has been proven in the UC model with adaptive corruptions. It's the only one with adaptive corruptions as far as we know. And if you're familiar with EEC, which is the original PAKE, it kind of has a structure. You can think of this as just an ephemeral chem key exchange, except you're encrypting the public key with the password, and you're also encrypting the ciphertext with the password. So in order to be secure, Cake requires the chem that it uses to have ciphertext and public key uniformity, which means that it is an ideal candidate for an OChem. You can just plug in an OChem and it works. However, like we said, we need hybrid public key uniformity, and we can't get it naturally using our combiner. It basically requires both underlying public keys to be uniform. And so the only way you can get this is by just having statistical uniformity for both of the underlying public keys. So DHChem naturally has statistical public key uniformity. It's just a random group element. But none of the lattice-based ones have this property. They're all based on the LWE or MLWE or LWR assumption. However, this isn't inherent. A lot of these LWE schemes rely on an optimization due to Lindner and Pikert, where instead of having a public key that is uniform and a ciphertext that is an LWE sample, it makes both the public key and the ciphertext LWE samples. So our idea is simply just undo this optimization. So if you do this to Photochem, you get something that we call stat Photochem, and you can use this to instantiate the PAKE. So the final construction is Cake over the OChem that is the combiner of DHChem with Alligator and stat Photochem. So some properties of this is the first hybrid PAKE that has been shown to be secure in the UC model with adaptive corruptions. It is only 2 rounds, whereas the other ones are either 3 rounds or they are 1 round and very inefficient because they use isogeny-based group actions. And this comes at the cost of about a 7.5 times overhead compared to the 3-round PAKE using normal Photochem. It also has a similar increase in computational complexity. It would be interesting to see if we could get something like this working with module-based, with ideal lattice-based schemes, but the leftover hash lemma doesn't quite apply in the same way there, so we leave this to future work. In conclusion, we defined a uniform encoding for MLChem. We used it to construct an obfuscated key encapsulation mechanism based on MLChem, and we designed a combiner that can take 2 OChems and produce a hybrid OChem. We used it to construct a hybrid obfuscated key exchange mechanism and the first hybrid PAKE that is secure with adaptive corruptions. And with that, we'll take questions.
First of all, thank you. This is directly useful for post-quantum Zcash because we need the hybrid encryption that is key private. So for the indistinguishability of the combined public key, it's clear that you can't get that just assuming that either of the schemes are indistinguishable. Can you get it when you pick one scheme in advance, and if that's indistinguishable, then you get the overall property? I guess, yes, if the public key for the the pre-quantum scheme say is indistinguishable?
Sorry, can you repeat the?
So what I'm saying is, it's clear that you can't get indistinguishability of the combined public key just by assuming some property of either scheme, right?
Mhm.
But if you pick one scheme and assume some property of that, then is that sufficient?
Right, then that reduces to the, say one of them is perfectly indistinguishable from uniform, then this reduces to just the indistinguishability of the other one. But that's not what hybrid means, because hybrid means you have to break both.
I understand, yeah.
Yeah.
Yeah, in practice, yeah, you might trust more than one more than the other. Okay, thanks.
Yep.
Let's thank the speaker again. So last talk before lunch is by Andres and Lucas, who is going to talk about using formally verified post-quantum algorithms in large-scale deployments, and we leave it to them.
Hi, I'm Andres, and we're really here to tell you about post-quantum deployment at scale. In particular, we are looking for public key encryption for chems and digital signatures. And the context is the same that you have heard many times over here, where there is a concern from quantum computers. There are standards that mandate post-quantum cryptography to be deployed as soon as by 2026. And we're really focusing on key exchange and signatures. And we're trying to do this in an open source, freely reusable manner, where the implementations we verify and build can be deployed by anyone, by which we mean many different applications and many different social contexts. Now, the motivation for verification is a little bit more subtle. And really, the context in which it makes sense for us is that we're verifying and deploying optimized implementations. They're rather intricate. The experience from elliptic curve cryptography is that there were a number of bugs in highly optimized implementations that were found over, in some cases, years or maybe even decades. And auditing was very challenging. An implementation consists of thousands of lines of code. It is very hard to spot a place for an index that should have been a 1 was a 0, and it's even hard to tell whether it was a conceptual error or a bug. Now, there is an argument that perhaps lattice cryptography is simpler than ECC, and for reference implementations, I buy that. You can write a simple MLChem and not that many lines of code, and it's pretty neat to review. But once you get to optimized implementations, this simplification really doesn't carry over. And there are, again, the subtle things that come up. For ECC, we had carry chains. For PQC, we mostly don't have them, or at least for MLChem, we don't have them. But instead, we have delayed reductions, we have manual vectorization, and bit packing and other low-level programming tasks that, again, are error-prone in, from a far-away perspective in a rather similar manner. And I will now hand this over to Lucas, who will tell you about how we verify those implementations.
Thanks, Andreas. So yeah, let's dive into the technical details. Oh, yeah, working. Yeah, so our target is MLChem, previously known as Kyber or FIPS 203, and we implement and verify the standard. But what did we implement really? So we implemented MLChem in no SCD Rust. So that's around 16K lines of code, and it's optimized for both Intel and ARch64. And there's around 2K lines of code for SIMD optimizations using intrinsics. It's quite easy to integrate and deploy, so you can already today use the libcrux MLChem crate. And as you can see on the table, the code is roughly divided in 4 parts. So the mathematical part with field, polynomial, matrix, low-level formats, 3K lines of code, just as mathematical. The crypto algorithms, like sampling in CPA, in CCA, that's around 6K lines of code. And then, so all of this code is generic. Then we have high-level APIs that provides MLChem with different size. And so that's 4K lines of code. All right, let's see a bit, because we want to implement MLChem, but we really want also to prove it. So this diagram explains a bit how we do for the proof. There is two parallel processes. First, on the left, we start with a NIST specification and write a star specification, a formal specification, which is small, mathematical, and easy to review with respect to the textual specification. On the right-hand side, we start from our Rust optimized implementation and use hacks, our tool chain, to get a functional model in FSTAR. And so now we have those two parts in FSTAR, and so we can conduct a proof of equivalence between those two parts. And with that proof of equivalence, basically what we have as a result is total functional correctness for our implementation of MLChem. We'll also talk about secret independence a bit and panic freedom. But now let's dive into an example of writing cryptocode in Rust. So here we look at Barrett reduction. And in this case, there is three small specificities we have to note. First, we can't use modulo. We need constant time. That's why we use Barrett. And then we use a specific modulo, 3329. So that's something, a prime used in MLChem. The last thing is that we use, as you can see on the slide, 32 signed integer. So it's a signed Barrett reduction. Now, what does that mean to specify correctness and prove correctness for this Barrett function? As you can see here, you have like a contract with a pre and post condition. And here the post condition says that the result modulo 3329 should be basically the same thing as the input modulo 3329. So that is our lemma, our correctness for this function. And in this case, that's pretty nice because FSTAR is able to prove that automatically for us. I haven't talked about the precondition yet, though. So what, as you can see, the input is constrained in a bound. And so what happens if input is not in that bound? So even though Rust is thought of as a safe language, and it is memory safe, right? But that doesn't mean it cannot fail at runtime, panic at runtime. So here we need to make sure that the plus or multiplication doesn't overflow. If input is too big, that will overflow. So with our method in FSTAR, we can prove statically that this will never happen for this precondition. And so that's the proof of panic freedom, as we call it. And this is required for total correctness. Okay, let's look now at another example. So that's about low-level formats. So in MLChem, there is a few places we need to pack and unpack internal data structures as bytes, basically. And so here, the example is about MLChem ciphertexts, which are encoded as 16 unsigned 16 integers. And so, yeah, we can pack two such integers as 3 bytes and vice versa. And the thing is, here in MLChem, there is a lot of different such data structures. Sometimes it's only 12 bits that are relevant, like on this diagram. Sometimes it's different numbers of bits or different architectures. So we have a lot of variants. And here, performance is actually super important. So we need to hand optimize all of those variants by hand. And so that's actually one of the most annoying things that has to be done in MLChem. And so if it's annoying to write as a Rust code, you can imagine that proving this thing is even more annoying, right? So instead, we wrote a tactic. So a tactic is a program that manipulates proof goal. So we wrote a tactic that takes care about proving those things for us. Another thing to look at is secret independence. As we all know, it is very important. And in our implementation of MLChem, we stick to a standard discipline, basically, and we enforce this discipline using Rust types. Note that it's quite a crude discipline. It doesn't prevent compiler-induced leaks or microarchitectural leaks. But even if it's very standard, we actually found a timing issue in our code. And this issue was present in other implementations. So here in detail, that's that we have to divide secret values by the modulus. And the author of the reference implementation were expecting this to be translated as a multiplication, but it's not always the case, right? Like some compilers don't. And that's how we ended up with Kyber slash. Okay, so we've been looking at a few examples and how we prove them, etc. But really here, the issue, as you can see, the Rust code is already quite big. The ECDSA code is even bigger. So here really the key for our success to prove our Rust implementation was automation. So we resorted to multiple automation strategies. First, for mathematical bits, we used SMT-based automation. For more mechanized things like serialization, we could resort to SMT-based tactics. And as we saw just before, for secret independence, we actually just use a light type analysis in Rust. But still, there is a need for manual proofs and manual F-star annotations to tie basically all those proofs together. And as you can see on the table, the proof effort is quite distributed on the code base. All right, so now we have a verified implementation of MLChem. So you may think, oh, it's done, we are done. But actually now we need to bring this to scale. So Andres will...
So at this point, we have highly optimized, verified implementations, and we would like to deploy them at scale. And turns out doing this with a new tool chain comes with challenges that are only tangentially related to verification, but still very important. Luca told you how writing this in hacks and Rust helps the verification process greatly, but it also means we end up with verified Rust code, and many consumers of crypto libraries can only accept C code. So there is an entire third parallel process for how this Rust code gets interpreted and translated to C. The translation itself is very simple, but really the challenge here is supporting C code for all deployments that need it. And it has already been deployed in NSS and OpenSSH and Signal and so on, and we're looking at more deployments still. There are simple challenges, such as if you start with Rust code that is generic over which MLChem variant it implements and is proven generically, you then need to specialize it for C code because C does not have Rust-compatible generics, and this results in code size increases. For the optimist implementation, we saw a 40 kilobyte size increase in the library compared to a naive tiny reference implementation. Then a number of crypto libraries already have MLChem, often reference implementations that use a simple representation for their types. And then if you want to replace the array of uint16s with an array of ABX vectors, you suddenly realize that the alignment requirements are different, and there is software engineering work to be done there. There is also questions with types in C, like strict aliasing. If you have an array declared as one type, can you store in another type in there? And so on. Also, just trying to compile this translated code base with every compiler that our crypto libraries are used with is a lot of work. Some of them only accept C++. You would think that C and C++ are the same language, but no, they're subtly not. If you want to return a struct of unions, initializing that before C++20 is a special incantation. And overall, we support about 100 build configurations, and this is a growing number. I'm intentionally not giving it as exact here. And this includes things like big endian machines and weird Apple architectures with ARM and so on. And we're trying to do this in a manner where this work can be continued and maintained. So we talked about formalizing the specification. This specification would be what crypto library maintainers review, and the code generation would be checked by the proof. Now, to do this in a manner that actually fits into software development life cycles, we would want the proofs to be checked on continuous integration and the implementations to be generated there, and this has been achieved. And the technical side is in a relatively good shape. We were also hoping that Crispin will continue providing long-term support for both the toolchain and the implementations, which means they can survive in the future, perhaps as new variants are added or so on. And even though all these steps, even from a library maintainer's perspective, they're a lot of work, there is a great argument for doing this work, which is that we provide much better performance than reference implementations. It is roughly a ballpark 2x number from our prototype integration into boring SSL. And just to sum up everything we said just now, PQC is coming. Verification is important to get high quality implementations. We demonstrate this with MLChem with a number of deployments already. This verification effort did find a bug in our implementation and others. The steps from a fast verified implementation to a fast verified and widely deployable implementation are a lot of work, and it is especially a lot of work when we're doing it first time for a specific tool chain. but fast code is desirable, people want it, and at scale deployments are happening already. We're looking for more of them. And then once we finish with MLChem, we will look at the MLDSA. For most applications that are not as demanding as the very demanding applications we have looked at, the Rust and C code we produced are already available, and you will likely have a good time using them. Thank you.
Thanks for the very interesting talk. Very, very important work. Very, very cool work. How fast is the generated C compared to Rust? I was wondering if it's like, have you had a chance to benchmark it?
The answer is that we don't know from the top of our head. Based on how the process works, we would not expect significant differences.
Cool, thanks.
Hi, nice talk. And I have a few questions, like what's the challenging part of the Rust implementation compared to the C implementation? Or you just like follow the C implementation paradigm, like use different syntax like the Rust syntax? What's the challenging part? This is the first question.
Thanks for the question. Do you mean in this tool chain that transform Rust into C specifically, or?
No, I mean you mentioned the Rust implementation, some details like Barrett implementation, you put some code of it. I just want to know what's the challenging part, or you just like use a different syntax for MLChem, like using Rust.
So I don't exactly know how to answer your question. Do you have any idea, maybe?
I've seen independent implementations in Rust and in C++ templates of roughly the same logic. And at high level, it is similar. In fact, it would seem that Rust and C++ are both more friendly to MLChem implementation than C.
Okay, I see. And also, I saw the benchmarking results you compared to boring SSL on AVX2 implementation. So do you also compare to the existing AVX2 implementation, like the C, with AVX2 one, yeah.
I would recommend you to look at Crispin's blog. There are numbers there. I don't remember for sure which specific implementations are listed.
Like okay, I see. Thank you.
Hi, thank you for the talk. I'm Nicola Veri from Tampere University. I have one question and one comment. The first one is a question about your line there, next up MLDSA. Do you have a timeline for when you will work on that?
Yeah, so I think the whole project was 6 months. I think, or 6 months of proof, I think, and something similar for implementation, if I'm not mistaken. Maybe I am.
Okay. So it's coming soon?
Oh, well.
For MLDSA, I think work has already started and there is substantial progress. Yes, I think the expectation, I would expect time scale of months here.
Okay. And the other one is something that we might follow up offline, but at Tampere University, we have been working on an integration of actually your MLChem implementation in OpenSSL through our provider, so maybe we can discuss that.
We are currently working on integration into boring SSL. The integration there would hopefully be also usable in OpenSSL, but every time we add a new target, there can be new challenges, so I'm not going to make any strong guesses here.
Okay. Yeah, thank you.
I don't see any. Is there another question? Okay, I don't see anybody else as a mic, but somehow this shows that we have time. One question, which is, what is wrong with having like written high-speed implementations and then verifying them? I understand that Amazon is having a project like that, and might that end up being faster in both code and man hours?
So do you mean, I'm not sure I understand your question. Do you mean like, was Rust, using Rust making us able to have like very good performance, or?
Yeah, I mean, like
you don't mention how fast is this code compared to the current state-of-the-art AVX2 code, but it's presumably not faster. And like, I understand that Amazon has state-of-the-art AVX code, which they verify to be correct. I mean, like, wouldn't that just work equally as well?
I believe there is an additional angle here, which is the software engineering lifecycle management of this code base, where handwritten assembly code tends to be very challenging to maintain. And if we have Rust where proofs are simplified by the fact that safe Rust corresponds to functional programming, it is hoped that future changes there would be easier. I agree this other avenue is valuable, and especially if you're going for the last few % of performance, this might be what one might do.
No more questions. Let's thank Lucas and Andres.
All right, welcome to the session on Web PKI and open source. Our first speaker is Josh Oss, who is the co-founder and executive director of the Internet Security Research Group. And he will be providing a look back at 10 years of Let's Encrypt. Let's welcome Josh.
Hi, thanks for having me. So this is our 10th year anniversary of Let's Encrypt. So I'm going to talk a little bit today about where we are, what we're going to be doing, some principles that have served us well, and some lessons that we've learned. So I'm going to do a very quick overview of the Web PKI. I don't like to make too many assumptions about people who know what's going on here. So certificate authorities like Let's Encrypt issue digital certificates based on demonstrated control of a domain. And control is the key word here. It's not about whether you own the domain or not, it's about whether you control the domain. And when we issue a certificate, the certificate provides a binding for relying parties between domains and public keys. So if you get a certificate and you decide that it's valid, you can use the public key in that certificate to set up a secure cryptographic connection with any of the domains listed in the certificate. So overall, TLS needs encryption and authentication, and certificates provide the authentication part of this equation. So before 2015, when we launched Let's Encrypt, getting and managing certificates was mostly a complex manual process. It was often pretty expensive. And in general, I would say there were just a lot of people who weren't convinced of the necessity of going through this process to enable HTTPS. And the result of that was about 39% of page loads used HTTPS. And that was really concentrated on a small number of big websites that used it. There was a much smaller percentage of overall websites that used it. It was a pretty undermining problem. So I worked on browser networking security before Let's Encrypt. And it wasn't totally pointless, but it felt like it sometimes. So we thought about what we wanted to do, and we wanted a solution that would get the web close to 100% HTTPS within about 5 years. And the reason we were thinking about 5 years is it is basically the fastest amount of time within the realm of possibility. We really wanted to avoid some IPv6 or DNSSEC timelines here. And certificates seem to be the roadblock. You know, turning on TLS in a web server, it's a config change. It's not that hard. If you want to do it, you can do it pretty quickly. But getting and managing the certificate you need, that's the tough part. We thought about a lot of different possible solutions here, and we decided that in the end, we're just going to have to start a new CA. It's the only feasible solution here. The CA is going to have to give away certificates in a way that it's easy to use and also make the certificates free. And a point that I want to make about free certificates is that it's not just about the money. If you're, at a company and you're setting up a website, even if that certificate is 1 cent or 5 cents or whatever, you got to go find a company credit card, get approval to do this. Puts us in an awkward position. If your credit card expires, do we just not renew your cert, potentially take down your site, things like that. The financial transaction part of this is a huge issue for ease of use. So just cutting that out entirely, it's a bigger problem than just how much money we charge people or don't. So by 2013, we had decided to do this, and we really started planning what it would look like. In 2014, we incorporated the nonprofit that hosts Let's Encrypt called ISRG, Internet Security Research Group. We got a bunch of initial sponsors who understood what we were trying to do and were willing to take some risks with some real money. And we started technical development. We moved really quickly, and in 2015, we issued our first certificate. So this is what the graph looks like for issuance from that first certificate back in 2015. Today, this graph is a little bit behind now, but it's about 600 million websites that we serve today. We do that with about 500 million certificates. The reason for that is there can be multiple websites in the same certificate. And then this bottom line here is registered active domains. So a lot of the websites that we serve are subdomains of a registered domain. So the sites we serve are about 150 million registered domains. So I'll talk a little bit about our organizational infrastructure at ISRG. We have about 25 staff total. That includes engineers, fundraising, comms, finance, management. We have 3 projects. Let's Encrypt is our biggest one by far. It's the one most people know about. But we also have a privacy preserving metrics service called Divvy Up. And we also have something called Prosimo, which works on memory safe software. The total budget for this org is about $6.7 million. We get funding from corporate sponsorship, individual donations, grants. So for the CA infrastructure itself at Let's Encrypt, it's operated by about 12 engineers. 3 or 4 at any given time are writing software for the CA, and about 8 or 9 are operating the infrastructure. And to keep these 12 engineers, productive and doing what they need to do, they got a support staff of, fundraising, finance, legal, comms. The physical infrastructure behind Let's Encrypt, it's about 3 racks of hardware across 2 locations. It's HSMs, compute, database, networking. We do use our own hardware. We don't issue certificates with any cloud-based systems at all. One reason for that is that we're required to use our own hardware. But in the end, it has turned out to be very cost effective to just do it ourselves. We know what our load is. We know what we need. We just buy the machines, maintain them, and it's quite cost effective. Physical security is a little bit more intense than a typical data center setup. There's just more layers between the parking lot and the servers, essentially more rules and requirements about who can be where, when, and for how long. We do use the cloud for some ancillary systems, some testing, some log search type stuff, but none of the stuff that's actually involved in issuing a certificate, like I said, none of that stuff is on the cloud. We have a CDN for OCSP and CRLs. Those are revocation mechanisms. And we have some accommodations in the data center for performing key ceremonies. The software stack is, probably roughly what you would imagine. Linux, virtualization, management. MariaDB is what we use primarily for our database these days, although we've been moving a lot of stuff over into Redis. We have our open source CA software. It's called Boulder. It's on GitHub. We write that ourselves, written in Golang. One of the things I want to mention here is that we've been working hard to transition some of our critical components, especially those that are on the network edge. We're trying to get those to memory safe software. So we started off with NTP. That was like a relatively easy thing to do. We, funded the writing of the software through our Prosimo project, got that deployed. It works great. Later this year, we're going to move DNS over to something called Hickory DNS, which is a high performance resolver written in Rust. We'll be moving TLS over to Russell's and eventually a lot of our reverse proxy stuff over to something called River. So here's the output of that system. We issue about 6 million certificates per day on average. Again, that supports almost 600 million websites. For OCSP, we serve about 15,000 requests at the origin and about 140,000 requests per second at the edge at our CDN. We also run CT logs, certificate transparency logs. We run 2 types of those logs. We'll get into that later. And the total cost for Let's Encrypt itself for a year, so not the whole org, but Let's Encrypt is about $4.5 million per year. So I'll talk a bit about what's coming up next. Short-lived certificates are probably the big one for this year. We currently issue 90-day certificates. That's what we've done since we started the past 10 years. We have now issued our first 6-day certs. We've only issued them to ourselves, but we are going to be opening it up to a wider and wider audience and general availability by the end of this year. The shorter lifetimes are better for security. If you have a key compromise, you don't need to worry about janky revocation mechanisms. It expires in 6 days, you get a new cert. If your renewals are automated as they should be, this should not have any impact, but this is optional. You're not going to be forced to 6-day certificates. You can stick with 90 by default, and you can opt into 6-day certs. With 6-day certs, we're going to be adding IP address support. So right now, you can only get certificates for domain names. You're going to be able to set up TLS with IP address soon. That's only going to be available on the 6-day certs. IP addresses tend to be a bit more transient than domain names, so we don't want to issue IP address certs for 90-day validity periods. That'll only be on 6-day certs. We're also in August going to turn off OCSP, so that 140,000 requests per second that we serve, that's going to go away. There are a bunch of privacy problems with that. You know, we don't want to know every time somebody uses a Let's Encrypt cert to visit a website. You know, we currently don't store those logs, but we don't want this traffic at all, really. It's expensive to operate, and because OCSP signing is so much more frequent than the signing of certificates themselves, actually it's something like 75% or more of our HSM capacity is taken up by OCSP signing, and the remainder is the signing of the certificates themselves. So it'll free up a lot of space in HSMs. We're also going to continue to push Acme renewal info hard. And this is a system where you can have your Acme client check with Let's Encrypt every day or every few hours, whatever you feel like. And you can say, should I got a new certificate yet? And often we'll say no, but if we're going to revoke your certificate sometime soon, we might say, yes, get it now before you normally would. That means if we revoke your certificate for some reason halfway through the certificate's lifetime, ARI will signal to you that you should get a new certificate now before we revoke it, and we avoid a lot of downtime. So this is a really important part of improving resiliency for the web PKI. And if anyone here happens to be an Acme client maintainer, we should talk about this after. We're also going to be evolving how we handle transparency logs. So like I said before, we run 2 of those in 2 different styles. The old style, I would say at this point, RFC 6962 logs. We've been running those for a while now. But the goal is to try to make running these logs easier and cheaper and make them more reliable. The problem with RFC 6962 logs is that they essentially require a large and expensive cloud-managed SQL database. Those databases, because they handle dynamic queries, they can be relatively easily overwhelmed. They also suffer from something called max merge delay violations, where we say, we will stick this certain CT log by a certain time, but then if we fail to meet that deadline, the log can be disqualified and things like that. And there are ways to get around that, which I'll get into next. But generally speaking, these logs are just complex to run. They're expensive in terms of cloud costs. They're expensive in terms of staff time. We do run these in the clouds because these are not involved in certificate issuance. So we're going to move to something called tiled logs. And instead of doing dynamic database queries when people want to query the log, we just return really easily cacheable tiles of responses. I think Filippo Veslord is here. He did a lot of work to help make this happen. We're very thankful to him for doing that. It moves a lot of the storage burden to S3. And like I said, we can just use a CDN. We don't need this big managed database. It also gets rid of the max merge delay. We just don't hand out the receipt for the addition to the log until we've already added the cert to the log. So no more max merge delay violations. So the last thing, this isn't something that's coming up, but it's worth noting that it's not coming up. We're not really working on PQ yet. There are a bunch of things that need to happen before it makes practical sense for us to engage with this topic. So the web PKI community is going to have to agree on a plan. The root programs are going to, and the CAB forum, they're going to have to agree on some rules that allow us to do PQ. Right now, even if we wanted to, we can't. And then once we're allowed to, we need HSMs that support PQ algorithms. Now, HSMs are hardware security modules. They do all of the signing for us, and they keep the keys private. For those who don't know, HSMs often have this thing where they support some algorithms in hardware, and those are really fast, and then they support more algorithms in software. At our volume, we need support for PQ algorithms and hardware. An HSM that does like 1,000 signatures per second is not that useful to us. We cannot afford that many HSMs, either in terms of the hardware, the support, or the power budget. We probably need HSMs that can do 10,000 per second, and that means we need HSMs with hardware support. HSMs do not evolve quickly for people who are not familiar with this type of hardware. So this may be the long pole here, and I hope there are people working on this because we need hardware support in HSMs for this to be practical at scale. So I'll talk about some principles that have served us pretty well over time. One of them is simplicity, and this is maybe the biggest one. The web PKI, their requirements and the technologies are pretty complex. They're not easy to implement. They're not easy to use normally. We try to encapsulate as much of that as possible and expose it as simply as possible. It's good for ease of use, it's good for security, and it's pretty good for financial stability as well, sustainability. We're always looking at a way to cut down on things and make them more simple. An example is that we just have one API for getting certificates. There was no other way to do it. We can't even do it another way internally. If we internally want a certificate, we get it the same way everybody else does. So there's only one sort of compliance surface, one attack surface for us. We also applied this principle to our internal database architecture. We have a single instance. We don't shard or cluster. Now because of this, we have very powerful machines. They cut into the 6 digits per machine, and we have a few that we can, more than a few that we can switch between when we want to. There are live replicas. But we could and do run the database on one machine unless we need to switch over for some reason. It has been great for maintenance, right? It's much easier than maintaining a cluster. The hardware is expensive, but it's cheaper overall to do it this way. We might be nearing the end of this strategy. We might have to cluster or shard sometime soon here. But I mentioned before, we've been kicking stuff out of SQL and over into Redis. That's worked out great, and we have a little more headroom on the SQL machines than we thought we would at this point. So maybe it'll last another year or two. We'll see. We have to be efficient. It's our financial reality where we can't just throw a lot of money around and stuff that's not really necessary. It's also the right thing to do. I'm really thankful that people entrust the dollars that they have to us to do our work, and we should do the most good that we can with the public benefit dollars that come our way. An example of this is scaling. So we cannot scale our staff or our hardware, frankly, but mostly our staff with issuance. We can't, that graph earlier that I showed, we can't have a graph like that for staff. Every year we need to be a bit more efficient than we were the last year. So this is just some snapshots in time. We started with 4 engineers. Somewhere in the middle, we got up to 8 or 9 engineers. Today we have 12, but the issuance, the people we served has gone up much faster than that. So I'm proud of the team for getting this done, and we need to continue doing it over time. We make decisions that optimize for staff time a lot. This goes back to what I was talking about with the hardware. It's much cheaper to just buy a big database that will do the work than shard it out and spend a lot more staff time dealing with that. So another principle that's important to us is transparency. An example here, when we started off, I did not know how a CA worked really at all when I decided to build one, nor did my co-founders. We made a bunch of mistakes, and we decided early on, we're just going to be transparent about all of them. Every time it happens, we're going to post, we're going to explain what happened, what we're going to do about it. And some people worried if you start doing this, which wasn't as common back in 2015 as it is now. If you start doing this, people are going to trust you less. But I think quite the opposite happened. The fact that we filed incident reports as we learned and made some mistakes made people trust us more. And it's worked out well for us, and we keep doing that now. We also have open source CA software. Not all, let's say there's 100, publicly trusted certificate authorities out there. I don't know if that's the exact right number, but it's the right ballpark. Not all of them write their own software. It's an expensive undertaking to do that, given how many rules there are on the WebPKI. But this is important to us. We need to do this, and it's open source. People can see exactly how it works. We've had people find bugs preemptively in our issuance just by looking at the open source software. It's worked out really well for us. It also helps Acme client developers. You don't just get to see the Acme spec from the IETF. You can look at exactly what we do by looking at this software. So for some lessons, one of our staff brought up when I was asking about this is that mercifully, Let's Encrypt is not involved in every TLS connection. Our certificates might be, but you don't have to contact us about it, especially if you're not using OCSP, which we're going to get rid of. Well, I think we'll talk more about that later, but yeah, we're not in the hot path. That's great. We should think about this when designing other web scale services, like how can you let the connections happen without the service they depend on being in the middle there. Open standards can help. It's probably not a shocker to a lot of people in this room, but having an open standard has helped us build such a vibrant client ecosystem. It's much better than we could have. People might be surprised to learn that we don't produce any client software or distribute it at all. We worked on this open protocol, we run the server side, but all the client software out there is built by our community. We thought about this early on. We dipped our toes in this a little bit, but there are too many deployment environments out there for us to begin to try to cover much of it. So we really focus on open standards to help get the client ecosystem to be vibrant. We focus on what's important. This is related to some of the earlier stuff we talked about, but you can't do it all and you can't make everyone happy, especially if you want to be efficient. There's all sorts of stuff we don't do. We don't do OV, we don't do EV. We're going to kill off OCSP. There are not too many support options, like you can't call people up at Let's Encrypt and ask them how to get a cert. There's a non-trivial number of people that are disgruntled that we don't do SMIME certs. We can't do everything. We spend a lot of effort doing things that are important. Like I mentioned before, our CA software, like we didn't have to write that ourselves, but that is really important, and we do that. The last one here goes back to something I mentioned earlier. Hardware is cheap. Like, we learned this lesson over and over again. It is just cheaper to buy better hardware and spend less staff time doing stuff. I have an example here. This is what our database servers look like. There are a couple Epic chips, 2 terabytes of RAM, and a big pile of NVMe disks, sort of rated together with OpenZFS. It has always been cheaper to do this. These are over $100,000 machines, but it saves us a ton of money to do it this way. My last lesson here, I think, is around intimidation and uncertainty. When we started Let's Encrypt, we didn't really know if it was going to work. It was sort of intimidating to some of us early on. After we decided to build a CA, I started asking her, like, what's an HSM? Apparently we need those, Don't be intimidated. There's lots of things that need to be improved on the internet. Give it a shot. We had to create legal entities, hire staff, fundraising, get trusted by the browsers. It was a very intimidating project to start with. It worked out fine. I'm sure everybody here is smarter than I am, so figure it out. It wasn't an insurmountable work. It was totally worth it, and billions of people have a safer internet today because of it. Here's some ways to help. Thank you.
We have some time for questions.
Very common attack vector is to try to benefit from typos. So Google with the O's replaced by zeros can lead to a malicious website. Are you providing any help in preventing such mistyped addresses? Or you'll provide a certificate, even if it's obviously close to a famous website?
We do not do that kind of filtering, no. There are other people who are better equipped than that. That kind of stuff generates a lot of false positives, and at our scale, like, we're not prepared to deal with those false positives, and yeah, we do not do that.
Thanks. Hi, thanks for all the work. 2 questions. 1, what 6 days? And then 2, are you guys interested in hosting what kind of privacy-preserving infrastructure like?
Sorry, I can't hear the second one.
Are you guys interested in hosting more privacy-preserving infrastructure like the systems you already have? I'm blanking on the name of it.
Well, to answer the second one first, yes, we do look at other infrastructure that might be helpful to host. So why 6-day certificates? There's a few reasons. One goes back to, like, eventually we're going to be required to. So the way the rules work now, that a short-lived cert is defined temporarily as 10 days. In a few years, the definition is going to drop down to 7 days for compliance purposes. So we don't like to be on the edge of compliance at all, and we don't want to make another switch from, like, if we were targeting 10 days, we would do 9-day certs so that we're not living on the edge. But we don't want to target 10 days because a few years we're going to have to switch down to 7 days. So we picked 6 because it's 1 day less than the compliance of 7. It also is just a nice, I mean, rules aside, it gives you enough time to get a new cert if you have a problem. It's also where doing things like IP address certs becomes reasonable, right? Like IP addresses change a lot, but for the most part, not every 6 days. Yeah. One of the things that I didn't mention about short-lived certs too is that they don't have required revocation mechanisms. So we want something that's pretty short. So if you do have key compromise, you don't need to rely on, it'll wash out of the ecosystem pretty quickly.
Thanks.
So you make a big impact within Let's Encrypt with a rather small team. Do you have any staff turnover? I also understand that as a CA, you have to very much look into any new staff coming into the team. Could you tell us something about that?
We do vet our staff, we do background checks, interviews, things like that. So we definitely vet them. Turnover is not that high. I think people generally enjoy working on things that have impact and are open source. So, I'd like to think it's a nice place to work. We don't have a lot of turnover. Yes, we do check our staff. It's background checks, lots of documents and legal agreements, things like that, maybe a bit more than you would normally have.
Thank you.
Hi, thanks for the talk and the great work. I have a question. So on the slide when you showed the graph of active certificates, so I think between 2023 and 2024, there was like the sharp temporary decrease. So I was kind of curious to like, what's the,
Yeah.
Yes.
Yeah, every once in a while there's a sharp drop. Honestly, the really sharp drop, I think that is an issue with the statistics gathering. It's actually pretty hard to calculate this graph because it's not a simple counter. It's like you have to do a ton of deduplication to figure out what the actual number is. So it requires way more resources than we would expect to produce this. And every once in a while, the way that it collects stats gets messed up. And I think that really sharp drop is just something where it got messed up and we did not fix it entirely properly.
Thank you.
Hi, again, thank you for the talk and your work. I was wondering if you could tell us a bit about your key ceremony and an HSM setup, specifically in order to protect against like single employee weaknesses. I would imagine you're pretty paranoid about exposing the private key of your root CA.
Yeah, so we do key ceremonies. They're done in a room that has a lot of walls between that room and the outside, but it's not against the edge of a building or anything like that. Trying to think of how much I can say about this. We limit the device in the room. We do think about EM radiation, things like that. I think one of the biggest things we've changed over time is that when we did our first key ceremonies, they were not as automated as we would have liked. So our first key ceremonies took longer than they do now. Now they're over in a matter of minutes because the whole thing is like scripted out and checked, that has a bunch of automated checks in place. And, people running the ceremony are mostly like pulling HSMs out of a safe, putting them on a table, verifying that the cables are set up. They get the laptop going, which is like a special secure laptop that doesn't go on the internet. And, they load the script for the ceremony, which is pre-populated with what we want to do. And they're basically just hitting a button and it's over in minutes and we pull the certs off. So I think the speed of the ceremony has probably been the most important for us over time. And the automated stuff is just more reliable. There's less room to make mistakes. But yeah, we do think a lot about who's in the room, where is this room. There are a lot of special safes with special ways of getting into the safe where the offline HSMs are stored. For people who don't know, the root keys at Let's Encrypt, and I would assume /hope at the other CAs, are typically kept offline in tamper bags and special safes, which are themselves inside many other layers of security, and only the intermediate HSMs are online and in a rack. So yeah, does that answer your question well enough?
It does, thank you.
Unfortunately, we're out of time for questions, so please continue the discussion offline. Let's thank the speaker again. Next up, we have Hart Montgomery talking to us about how to properly open source code. Let's welcome Hart.
Awesome. Can everybody hear me? Great. Thanks a lot. Let's get started. I am Hart, and today I'm going to talk about how to properly open source code. This is going to be a little bit different from your typical RWC talk, but I hope it's useful for you on your journey when moving your cryptography into real-world production. So I'm going to start by going over some open source background, and I'm going to talk a little bit about why open source and the Linux Foundation, or really why you should care about my opinion on open source principles. I'm going to go over some basic open source table stakes like software licensing, IP protections, and best security practices. And then I'm going to talk a little bit about open governance and building an open community. I'm going to assume you want people to use your code in the real world. This is RWC after all, and the usual disclaimer, I'm not a lawyer. So let's get started. Why do we open source code? Well, one of the reasons, and one that you all are probably very familiar with, is so that others can examine, verify, and learn from our code. It allows people to trust code, and open sourcing has many benefits for things like software security, which many other speakers have alluded to today. As I say, you wouldn't trust a crypto system without a publicly available paper, so why would you trust cryptographic software without a publicly verifiable implementation? But there are other reasons to open source your code as well, and these typically fall under collaboration. There are many economic efficiencies of open source. I'm not going to go into this today in much detail, but a large ecosystem around a piece of open source ensures that, say, if one organization goes away, development continues. This is very important for things like security. Open source has really won in the modern development ecosystem. So even for closed-sourced applications, typically 90% of an application's code base is open source, and this is due to these economic efficiencies. Again, I'm not going to spend much time on this, but I do want you to know that the Linux Foundation has a lot of market research on this topic. If you need to convince your boss or management or whatever that you should be able to open source your code. And the Linux Foundation focuses on this collaboration. When multiple companies, entities, or individuals want to collaborate on open source software, but don't trust one single party to own the code, they turn to the LF. And I don't want this to turn into an infomercial for the LF, but I do want to present some facts and figures that show you that we generally know what we're talking about when it comes to open source best practices. So at the LF, we're behind some of the most critical projects in the world. You probably know the kernel. We also have things like Kubernetes, most of the world's telecom stack software, things like the Academy Software Foundation, which runs the animation software for movies, RISC-V, Finos, many other things. And here are just some numbers. I'm not going to read these all out, but these are pretty big annual numbers for open source contributions. I will also give some folks here shout outs. We have a fair number of advanced cryptography projects at the Linux Foundation, and I see many familiar faces in the room, so thank you for your contributions. Right, so let's talk about some basic table stakes for open source software. Well, let's start by saying what open source software is. Here's a definition of open source software, which I won't read, but I want to point out the critical word here, which is license. And the license is the legal document that enforces the set of legally allowed things you can do with code. There are three main types of open source licenses. There are business licenses, which are typically very restrictive software licenses that require payments potentially to a developing company for use. There are copyleft licenses like GPL, which means that modifying the software requires you to contribute back any derivative works. And there are permissive licenses, which mean that you can essentially use the software however you like. So I'll start by mentioning business source licenses. These are technically not open source licenses. They're what's called source available licenses. The source code is public, but limited to certain users. It's viewed as a compromise between proprietary software and open source. And I encourage you to use a BSL license for your code if you want to be able to control who uses your code, like it were closed source, but you want people to be able to independently verify and study your code. So think of like a crypto paper review. If we move on to copyleft licenses, these require users to make available all derivative works. I'm not going to define what a derivative work here is, but if you modify the code and you use it in something, you typically have to make the source of that something available for free. I will say these are very hard to use commercially. as this sort of quote from Richard Stallman indicates about the ethos, they're not public domain licenses. We unfortunately see a number of people that use copyleft licenses with the idea that they will increase contributions back to code bases by essentially legally requiring them. The unfortunate reality is people these days are just not likely to use your code if there are any viable alternatives due to the potentially cumbersome legal requirements. And finally, they're permissive licenses. And these are things that let you do whatever you want with the code, basically. Most commercially used open source software and most Linux Foundation projects are licensed with permissive licenses just because it's very easy to use. And we generally recommend you default to permissive licensing unless you have a compelling reason not to do so, because it just maximizes the number of users of your code base. So a couple of common licensing pitfalls that we see, and I don't really have time to go over these, but be careful with code you use. We see a lot of people get, say, an LGPL dependency wrong, so be careful about that. And we also see issues with licenses that don't have IP protections. Be careful around those. Right, so in summary for licenses, pay attention. We generally recommend using Apache 2 because it has explicit patent grants, particularly if you're not trying to directly monetize your code. And if you want to make your proprietary code base visible, you may want to try a BSL license. And that last point sort of leads me to this, which is other legal IP and copyright protections. What happens when contributors to open source software unintentionally or maliciously add code that has some sort of IP protection to your open source project? The effects are usually not pretty good. So when you have a Wikipedia article on a series of lawsuits, that doesn't usually indicate that things went well. This is from the sort of infamous SCO Linux disputes. The DCO policy was created out of this. So we recommend that if you have a project and you allow outside contributors, you use either a developer certificate of origin or a contributor license agreement. A DCO is particularly easy to use. This is the DCO right here. I apologize for the darkness on the screen. It's very easy to set up on GitHub. You can just use commits signed with the -s flag. So yes, we require these kinds of IP protections for all LF projects. You should too if you allow outside contributions. And if you don't, people will be justifiably less likely to use your code. All right, let's move on to security. So I know everyone here is familiar with computer security of many types, and it's important and essential. But I do want to bring up a couple of things that are different for particularly large-scale open source projects. And these are vulnerability disclosures, software bill of materials or SBOMs, and software and artifact authentication. And I will say we have a nice sub-foundation of the Linux Foundation called the OpenSSF, which has answers and guidelines for sort of all of the things you need to be doing for your basic open source software security. I encourage you to check it out for more details. So remember that one advantage of open source software is that community members can find and report bugs. And you want to make this as easy as possible for them. Friction is bad. It doesn't really matter what you do as long as it's easy to find and follow. A lot of our projects have recently adopted the GitHub tooling. And let's talk about the software supply chain. So earlier I mentioned that 90% of code was open source and even closed applications. And it turns out that modern developers typically build in a way that looks like this sort of development hamburger. They typically choose a framework that's open source. They use open source libraries to solve problems, and then they write custom code to kind of connect everything and tie it all together. Of course, this brings to mind the famous XKCD comic that I think several other speakers have already brought up in this conference. Obviously there are a bunch of software supply chain attacks that you all are probably familiar with. And you might think that, hey, this isn't so common. That's not true, actually. So in the latest Black Duck open source security and risk report, which went over something like 1,000 code bases across a bunch of industries, well, the vast majority of these commercial code bases had vulnerabilities. Many of them were high risk, out-of-date components. So it's pretty much a disaster out there. But hopefully your project can avoid some of this by using SBOMs and keeping dependencies up to date. So we encourage everyone to keep track of all the code you pulled in. If there are bugs, you obviously need to fix them and update quickly. Do some due diligence about the dependencies you do have. And we typically find that well-run open source projects are extremely careful with their dependency choices. There are a lot of good tools to help you with this. The OpenSSF has a tool called Guac, which is simple and nice. And finally, I'll say that if you build a popular open source project, people will attempt to impersonate you. This constantly happens to LF projects. I had to deal with somewhat clever NPM impersonation this week even. And there are plenty of tools for this too. If you're not familiar with SigStore, this is a great tool for this kind of thing that you can just use out of the box. Right. So finally, I'd like to talk a little bit about building an open community. So recall our definition of open source software. An important term here, sort of at the very end, is this collaborative public manner term. And what does this mean and why is it important? Well, the freedoms provided by the license allow for large and diverse communities to form around popular open source software. You can think of things like the Linux kernel or the Apache web server or Kubernetes. And when we mean open source, well, we do mean open source, which is just a public repository of code, but we also mean open development. And this is when there's a community actively building open source code in the open. And then even better is open governance, which means that procedures and roles for the community, how decisions and priorities are made for the project, things like the roadmap, are all openly defined and managed. And we typically see that the more open governance a project has, the easier it is for that project to attract contributors and users. And just some examples of open source government we see as we move from the continuum from sort of closed to open. We have some projects, well, we don't have these in the LF, but there are some projects called public demonstrations, which is essentially just a code dump. Then we sort of have open source projects called open products, again, not really in the LF, but this is when a company or entity open sources a piece of software that's a product. It doesn't really allow outside contributions, but it keeps a roadmap, has regular releases, follows best practices, and so forth. Then there are benevolent dictator projects, which is when an organization allows outside contributions, but sort of ultimate authority still belongs to this benevolent org. And then finally, we have true open governance, which is when code with, we have code with transparent documentation, decentralized meritocratic governance. It's hosted under a third-party nonprofit entity, and technical participation and leadership is completely open. And I will say, whatever you choose, document your governance, and I encourage you to have as open governance as possible because it will mean you will likely have more contributors and more users of your project. With that, I'll conclude and thank you for your time, and I'm happy to answer any questions.
Thanks for the very informative talk. I didn't see BSD on your slides. I would put it in the permissive license category. Is that right? What's your take?
Yes. Yeah, I apologize for not listing every license.
Okay, but you're not like, you wouldn't like not recommend it. You like Apache 2 better, but like it's.
Yeah, I mean, most permissive licenses are compatible in the sense that you can relatively easily use code, licenses one in another project or relicense or so forth. We have lots of projects that are MIT licensed, for instance. We and I just like Apache 2 the most because of that explicit patent grant. So yeah.
Thanks.
It's not a question, but it's more a remark for the audience. I'm an open source developer, and I strongly encourage anyone who is doing open source to try to use the GitHub Action best practices because it's amazing.
Yeah, definitely.
One more quick question.
Hi, sorry, thank you for the talk. It was very interesting. Maybe that's a dumb question. You mentioned some copyleft license and license that ask you that if you use this piece of software, then you should be open source and stuff like that. How do you make those licenses apply when you're a small developer or like a small organization? Because, I mean, Yeah, how do you do that?
So how do you enforce license provisions? You have to use the legal system.
Okay.
Yeah,
That-
there's no better answer, unfortunately, but yeah. If someone breaks the law, then you have to use the legal system.
Yeah, okay, but we don't all have access to the same amount of money and the same amount of we can't use the legal system. Like Microsoft does not use the legal system in the same with the same powers. And I don't know, you're a random developer in Nebraska, right?
Oh, I totally agree. But this is a much bigger problem than just software licensing.
Okay, thank you very much.
Let's think hard. Next up, we have John Skank, who will be talking about revocation checking that works. Let's welcome John.
Thank you. So Josh showed that incredible chart from Let's Encrypt, 500 million certificates, valid certificates on the web at any given time. But Let's Encrypt is just one of 100, maybe a little more CAs. And collectively, those CAs have issued 1.1 billion certificates, not ever, but valid certificates at any given time. And in a system that large, you're going to make mistakes. The best CAs make mistakes and subscribers make mistakes. When that happens, you have to be able to revoke certificates. What you might have noticed in Josh's talk also is that he said that revocation mechanisms were janky. And that's the consensus opinion. It has been for as long as I've worked in cryptography. Revocation checking doesn't work. It's broken. So today I want to tell you about some of the work that we're doing at Mozilla to change that. Okay, so starting from where we're at today, there are two mechanisms that are in broad use. Okay, you have certificate revocation lists. These are authoritative lists of revoked certificates that are signed by the issuing authority. The downside to CRLs is that they're quite large. It's a few hundred megabytes if you want to get the complete collection of CRLs for the web PKI. Because clients can't download that much data and CAs don't want to serve it, for the most part, people rely on an online protocol, an online certificate status protocol, or OCSP. And this is a privacy leak. That's a big problem with it. It wasn't as big of a problem when we were not encrypting our DNS queries and when we were not encrypting client hellos, but it's more of a problem today. OCSP is also slow. You're going to block your TLS connection while you go check with another server about the status of the certificate, and that's going to take maybe hundreds of milliseconds. On top of that, the results are allowed to be up to a week out of date, according to the baseline requirements. So it's not clear that it's actually giving you good data. And now a more pressing concern is that it's optional to support. CAs no longer need to provide OCSP. And so there's really no future for this protocol. In response to that, people are trying to move to short validity periods, which is nice because it avoids the revocation problem in some sense, but there are a lot of open questions here, like how short of a validity period do you need before you can really do away with revocation? I'm not sure that I want a certificate around for 5 days after it's been compromised even. And Let's Encrypt might be able to move pretty quickly here, but the entire web PKI will take years to migrate to short validity certs. So the short validity certs are going to be part of the solution. Another part is going to be compact or summarized CRL. So there are two ideas here, and there's a few different proposals for how to do this. Compact CRLs would be compressed representations of CRLs that can be delivered to end users and queried privately, just like CRLs could be in principle. And summarized CRLs would be, you take the list of CRLs and you remove some administrative revocations. Maybe you only publish the key compromise revocations. The pros and cons here will really depend on the mechanism that's chosen, but you're going to want to ask, like, can we really make these things small enough? Can we make them comprehensive enough? And what about, the additional trust assumptions that we're adding to the system by using these things? For Firefox, the fact that OCSP is going away is a bit of a problem because we use it right now. 18% of revocation checks are performed using synchronous OCSP. We also get some OCSP responses from TLS servers at stapled OCSP at 27%. And then we cache both of these types of responses and we're able to use our cache 55% of the time. But that 18% is the real problem for us from a performance perspective, at least. The median request time is 113 milliseconds. So we would like to use something else, and the technology that we've chosen to move forward with is called CR Lite. This comes from a 2017 paper by Larish, Chofnes, Levin, Maggs, Ms. Levin-Wilson that was presented at Oakland in 2017. The idea here is quite simple. It's a very elegant system. So you have one party that's going to play the role of an aggregator and try to get a global view of the web PKI. That aggregator is going to go and get a list of known certificates from certificate transparency logs, and then they're going to get a list of revoked certificates from CRLs. They're going to take all of the revoked certificates and put them in a Bloom filter. And if you know anything about Bloom filters, you know that they have one-sided error. So it's possible that you take a non-revoked certificate, query it against the Bloom filter, and it shows up as revoked. Okay, we don't want that, but we have the list of all known certificates. So we just enumerate all of the false positives and put them in another Bloom filter. Okay, and now, well, you have one-sided error again, but it's in the other direction. So you look at the revoked certificates and see if there are false positives in that collection, and you put those into another Bloom filter. And you keep doing that until you've eliminated all of the exceptions. You can then take that cascade of Bloom filters and ship it to users. Crucially, you have to include metadata about which certificates were known at aggregation time. So Mozilla took note of this and spun up infrastructure for it. And in 2020, we had an implementation and we were prepared to do a rollout. We halted that rollout in early 2021 when it was still in nightly because we found false positives. Sites that were not serving revoked certificates were coming up with revoked statuses. And we realized that it was because of the metadata that we had communicated about which certificates were known to the aggregator. So we fixed that in 2022. We had a revised implementation with better metadata, and we went through the full process of rolling this out to nightly and beta, and eventually to 1% of release users. And that's when we found out that it was going to be too expensive for us to run. At about the same time, in 2022, Mike Hamburg gave a nice talk at RWC with a proposal for doing something like CRLite, but with a different data structure at its core, so replacing the Bloom filters. And so in 2024, when I got some time, I redesigned our CRLite implementation around some of Mike's ideas. The news in 2025 is that we've shipped this. In the last 2 release cycles, we've done a gradual rollout, and there are now over 100 million users checking revocation statuses with CRLite. And it's the default revocation checking mechanism in Firefox 137. Okay, so the story of how we got here is largely the story of a new data structure that we're calling a club card. It's a membership test, that's where the name comes from. This will be presented at IEEE S&P later this year. So these Bloom filters had an inherent 70% overhead with respect to a natural lower bound for encoding a subset of a set. Mike's work improved this to 11% using what are called 2-level cascades of retrieval functions. That's a bit of a mouthful, especially when we start adding more adjectives for domain partitioning and things like that. So we call these things club cards. This domain partitioning is an idea I'll talk about more in a second, but the key point is that these lower bounds from previous work had been assuming that there was a uniform revocation rate across the entire web PKI, which is not the case. Different issuers have different revocation rates, and the revocation rates vary over time. And that variance in revocation rate can be exploited to give you better compression. So that's what we do with club cards. And I can show you what that looks like in practice. The green line here is the size of Bloom filter cascades that we were publishing late last year. And the blue line is the lower bound for an unpartitioned data set. And the fact that there's a downward trend here doesn't really matter, that we're really looking at the difference between the green and the blue lines. That's that 70% overhead that I was talking about. Here are the lower bounds if you partition the web PKI by issuer or by issuer and expiry. Orange is by issuer and red is by issuer and expiry. And then here are the club cards that we actually publish. So we're about 11% off of that issuer partitioned lower bound. And we have code to do the issuer and expiry partitioning as well from a Waterloo undergrad who interned with us last fall, Gavin Wang. So we'll roll that out eventually, and that line will drop further. That's if you want to compress full snapshots of the web PKI, but you don't actually want to do that every day. You also just want to publish Delta updates. And so the green line here are the size of basically Delta CRLs, just lists of issuer serial pairs at about 200 kilobytes. we can encode that same data using our club card data structure and cut it in half to about 100 kilobytes. And you'll notice here that we're still quite far off of the lower bound, that orange line. But that's really because of metadata overhead, and that metadata is compressible. So if we just apply gzip compression, which our CDN does for us, we drop down to about 50 kilobytes. And then if you have a client that already has yesterday's club card, they can use that with a dictionary compression scheme like zstandard or Brotli, and basically remove the overhead for future, remove the metadata overhead for future Delta updates. So you do that and you drop down to 25, 30 kilobytes. So our current deployment, we're shipping all 4 million revocations that are in the WebPKI revocation set, which we gather from about 300 megabytes of CRLs. We encode those in a 4 megabyte snapshot every 45 days, and then we do Delta updates at 12-hour intervals on top of that. And those Delta updates are about 50 kilobytes using this dictionary compression idea. You can compare that with Chrome's CRL sets. They publish essentially all key compromise revocations as issuer serial pairs for about 500 kilobytes once a day. Okay, so we're publishing more than 100 times as many certificates at half the latency for a third the cost. Okay, and with CRLite enabled, we are servicing 95% of revocation checks with CRLite, and only falling back to OCSP for about 5%, 1% are synchronous OCSP requests. We have a plan for getting that 95% up. Largely, it means getting a more up-to-date view of the WebPKI. And as expected, we get an improvement in median TLS handshake time. So as our use of synchronous OCSP has dropped from 18% down to 1 or 2%, our median TLS handshake time has dropped by 30%. Actual impact on top-level page load metrics isn't that great. It's only a 1% improvement or so. TLS is not the most expensive thing that clients do, but it's an improvement nonetheless. Okay, so I called this talk toward revocation checking that works, and that kind of sounds like we have a revocation checking mechanism that works. So what do I mean? There's still 3 changes to the WebPKI that would help us make CRLite sustainable going forward into the future. The first is shortening validity periods, right? So this idea where we publish full snapshots and then Delta updates works well enough, but we don't actually need the full snapshots. If you have, we don't actually need the full snapshots. We could just do Delta updates, right? You can imagine that if you did Delta updates for long enough, all of the certificates in that full snapshot would eventually expire, right? So we publish these full snapshots because they reduce the client-side computational costs of using the system, but we don't really like publishing them because they increase our bandwidth costs. If validity periods were 45 or 90 days, then we know that we could just completely get rid of the full snapshots and reduce our bandwidth costs by a factor of 2. The second thing we need to do is switch to the static CT API. There's 2 improvements that we'll get from that. One is there'll be less rate limiting on our requests, so we'll have a more up-to-date view of the WebPKI at any given time. And the second, more important change is that with a 0 or a very short merge delay, our aggregator will be able to claim that it has seen a higher percentage of the certificates that it's actually seen. And that will hopefully get that 95% coverage up to maybe 98% or higher. Okay, and then the third change that would help us is if we revise revocation reason codes a bit, drawing a clearer line between those reason codes that are security critical and those that are administrative. Thinking there being that maybe there are some revocations that we don't actually need to push to users. We could encourage subscribers to revoke with an administrative reason when they don't need the revocation to be visible to systems like CRLite. Okay, so I have a few more minutes, and I want to talk a little bit about this club card data structure in some more detail. The core technology here is something called a linear algebraic retrieval function. The idea is basically you have a vector valued hash function H, and then you can encode a bit of information B about a document by finding some vector X that has inner product B with H of the document, right? And you can encode one bit of information about many documents by just setting up a linear system like this and solving for X. Motivating use case here would be that B encodes membership in some set. And you can extend this to encode more than one bit of information to create a k-bit retrieval function just by adding more columns to the X and the B terms. The ideal case, you would have some minimal perfect hash function so that after row reduction, your system was diagonal, and you could just write down the values for the X terms. You're not going to have a minimal perfect hash function in practice here, but you can do pretty well by just making sure that that hash function has all of its coefficients in a narrow ribbon. So the matrix looks like this after row reduction. You can solve that very quickly, even when you have matrices that have 100 million rows, as we will. That idea almost works. You do need to have a little bit of extra space in there, some free variables to make sure that the system ends up being solvable. But putting all that together, there's something called a ribbon retrieval function. There's some nice literature on it, and here's some papers that you can look at to learn more. The other thing that we need is Mike Hamburg's two-level cascade construction from that RWC 2022 talk. The idea here is use two retrieval functions. The first one, you find some matrix X so that the hash of any revoked document times X comes up as the k bits of zeros. And that's going to give us factor 2 to the k suppression of false positives for things that are not in the set, right? You take a random value, multiply by X under some heuristics about what X looks like, you will not get 0. 1 minus 2 to the k, 2 to the minus k times. Once we have that X, we can enumerate all of the documents that do come up as 0. So just like we were doing in the Bloom filter case. So we'll have all of the revoked documents and some small fraction of the non-revoked documents. And then we just put those all into a second retrieval function. We solve for some Y. We have a different hash function, G. So we've solved for some Y where G of any document times Y is equal to its actual revocation status. So it's either 0 if it's revoked or 1 if it's not. Okay. And one improvement that we've really made here is we have a new version of ribbon filters, which have a partition of the domain in them. So in addition to putting all of the non-zero coefficients in any row close together, we end up mapping any two elements of the same block to similar starting positions. So their non-zero coefficients will start in a similar place. And what this lets you do is for the WebPKI example, you have you need a different false positive suppression rate in each block, and so you need a different shape. You need like a different number of zeros on the right-hand side of this equation, this purple region that I've drawn here. And so if you have all of the rows from the same block getting mapped, if I have all of the documents from the same block getting mapped to similar rows, then your solution vector has this little staircase-shaped region of entries that you just don't care about, and you can just skip the encoding of those. Okay, so that's the club card data structure. It's a two-level cascade of these stitched ribbon filters with additional intrinsic metadata describing the domain and a partition. And there's also a secondary encoding mechanism that makes sure that the system is always solvable, mostly as a performance improvement for generation time. All that's available as a Rust library, which you can use to make generic club cards. And then we have the instantiation for CR Lite as well. Like I said, this paper will be at SMP and up on ePrint soon. Thanks.
We have 2 minutes for questions.
Thank you for the talk. I was wondering, in the original CRL Lite paper, I remember they have this section about trying to get rid of the audit log by doing some form of aggregate signature with CAs. I was wondering if Mozilla, you had any interaction with CAs that would be interested in doing this.
We don't currently have that set up. I think there are a lot of different opportunities for removing the trust on Mozilla here. It would be nice if maybe CT logs could check that we've properly encoded everything about the known certificates. Also, CA is checking that we've encoded the revocations correctly. All of the data is publicly available for each filter that we publish. So this is in principle possible to do today, but we still need some mechanism to actually, get signatures on documents and make them publicly available.
Thank you.
You said that you withdrew the CR light because you're getting false positives. If it was working as described, would those false positives, would you not be able to remove them? So why did you have to remove it?
Sorry, I'm having trouble hearing the microphone.
So I was asking about the CR light and the fact that you had to withdraw it from service because you were getting false positives.
Mm-hmm.
If it was working as described, you should have been able to negate those false positives in the Bloom filter cascade. Why didn't that work?
Well, we were able to get the system working without false positives using Bloom filter cascades. The issue there was just purely about the metadata that we were publishing about which certificates had been seen by the aggregator. So we did get it working. The reason that we couldn't ship that version was because of the size of the artifacts and what it was going to cost us to serve those.
Okay, thank you.
Let's thank the speaker. Our last talk of the session is about auditing key transparency. The talk will be given by Mari Galliser, Thibault Meunier, and Kevin Louis. Let's welcome them.
Cool. Hey everyone, my name is Mari, and today I am joined with Thibault and Kevin, and we're going to talk about a real-world deployment of an auditor for WhatsApp's key transparency system. But before I get started, I wanted to ask this room of people super excited about cryptography and security. How many of you, when you're using your favorite end-to-end encrypted messaging app like Signal, WhatsApp, or iMessage, use that QR code verification feature or security code verification feature? Can I see a show of hands? Quite a few. And how many of you have gotten a notification, maybe like red notification or something like that, that says that that contact's security code or safety number has changed? Okay. And how many of you just kept on texting your friends anyway? Also, yeah. Cool. So I say that to say that in the real world, getting a user experience for this type of security feature is actually really hard. And when I'm not working on privacy or transparency at Cloudflare, I actually train a lot of activists and journalists on digital security skills. And I can tell you that explaining to them how to do this kind of verification and why to do it is actually really difficult. So today we're going to talk about how we're trying to make it a little bit easier. All right, so Kevin will start us off by talking a little bit about the advancements in key transparency over the past year. Thibault will give us a sort of demo and architecture of our auditor, and then I'll close us out by talking about how this fits into the wider context of transparency and where we're hoping it's going next.
All right, so yeah, let's start off with a quick recap on key transparency. So this is roughly the, if you ever use an end-to-end encrypted messaging app, this is roughly the experience for users when you are trying to start a new conversation with a user. Basically, users find each other through some public identifier. This could be a phone number or a username. There's a server, a centralized server that keeps this mapping from these usernames or phone numbers to public keys. And then users, when they start a conversation, query the server with the identifier to get back a public key for each other. And then now that you have your contact's public key and your public key, you can do a Diffie-Hellman key exchange, get a shared secret. That secret's used to encrypt your message content. Most of us know this. So the thing that scares me about this setup is that we're basically relying on this centralized server to serve this database of identifiers to public keys honestly, right? So in particular, if the server were to be malicious, then it could insert a backdoor public key when you request for a specific user's normal public key. And this would essentially allow the server to execute a man-in-the-middle attack and intercept the messages. And this would be undermining guarantees of end-to-end encryption. So there is a solution to this, and it's basically QR code scanning, right? And the idea behind this is that if you're willing to meet up with your contacts, then you can do this QR code scan. And it's basically a check saying, hey, I got this public key from the server. Let me just make sure that this is actually the public key on your device. And yeah, so this is great, but the main problem is that most people don't really do the QR code scan. I will say that I've met a bunch of you at RWC in this conference, and we added each other on Signal for the first time. I've made a mental note, we never checked our QR codes. So even for us security-minded folks, this doesn't really happen. So key transparency, this is really the motivation behind key transparency. We want to provide some automatic means of checking each other's public keys without having to rely on the QR code scanning method and meeting up in person. So how does key transparency work? Well, at a really high level, the idea is that the server is meant to keep a log of all user key updates for every user, and then periodically is going to batch these key updates and post a public commitment of this log to some publicly available endpoints. And then now, whenever clients get a public key from the server, they can also ask for an inclusion proof to make sure that the key that they just got from the server is also included in this log. And the idea is that this will now make it much more difficult for a server to just like make up a key or add a backdoor key at that time. Now, in a full key transparency solution, it's a little more complicated than this because not only would you ask for the key for your contact, but you would also want to like monitor for updates to your own key. But for the simplicity of this presentation, we're just going to assume that there's a single query made for the client asking for a single inclusion proof for one key. So in WhatsApp, we use a Merkle tree construction called AKD for this log. And the way it works is basically there are a bunch of updates that we batch in every epoch. And each epoch we publish roughly once a minute. And yeah, so we basically add these entries to the Merkle tree, and then this produces a new Merkle root. And the root of this Merkle tree is what we end up posting to an AWS S3 bucket. And this happens every minute. In addition, we also publish something called an append-only proof, which is basically a proof that this log is being maintained in a consistent manner without deleting history. So it basically says that the current iteration of the log is produced by taking the previous iteration and only appending new entries to it, and in particular, not deleting any old entries or modifying history. Cool. And I guess just for high-level numbers, I mentioned that we publish 1 epoch per minute. We've been running this for about almost 2 years. We're up to over 1 million epochs, and our tree has like 90 billion nodes in it. So as I've described so far, with this key transparency deployment, there are some issues. One, we are publishing this root hash to AWS, but then when users ask for public key and an inclusion proof, we also give them a root hash. And there isn't anything currently enforcing that the root hash we give to users in the app is the same as what we're publishing to AWS. And this is kind of a huge problem because this still allows a malicious server to execute a split view attack, right? Like I could, for instance, have some nice looking log that we publish to AWS, a commitment to, but then when I'm actually targeting a specific user, I could serve a different version of the log. So that's issue number one. And issue number two is that these append-only proofs that I mentioned, they're like tens to hundreds of megabytes in length, so we can't really send them down to users feasibly. And so what we end up doing is we post them to the AWS bucket, but it's not clear if anyone is actually verifying them. And that's kind of like a critical component of key transparency, these are verified. So that's basically the motivation for this work, and I'll now pass it over to Thibaut for describing our auditor.
Yes, thanks, Kevin. And so now that like we see the problem, we see that we have already deployed a system, we identify a problem, let's move to the next step. And the next step to like solve this issue is like introducing an auditor. So the auditor is like a trusted third party, which is independent from the log. So the log publishes updates every 30 seconds, but before its updates are trusted by the client, it will actually have to seek a signature from an auditor. So every 30 seconds, it gets the epoch number, it gets the epoch digest, and sends it to the auditor. The auditor will perform some check, so it will like verify that the epochs are monotically increasing, that the epochs are valid, and once this validation is done, it will generate a timestamp, concatenate that with the epoch number and the epoch digest, signs it, and send it back to the log. This means that like now the log has a signature from the auditor and is able to send it back to the client. The client now has a guarantee that its view of the log is globally consistent and similar to the one of the auditor. At a high level, there's like a couple of things that like the auditor is doing. It does some witnessing, meaning that like it ensures that like epochs are unique and in sequential order. It also monitors like the epoch transition to make sure that the tree is correctly constructed, and we do that for every epoch. Finally, I want to mention one thing that like we do not do as an auditor. We do not see any private information. We don't see any name, we don't see any phone number, we don't see public keys. This is because we use a VRF as the leaf for the tree, and basically the auditor is just a trusted third party by WhatsApp client, but anyone can do that. The S3 bucket published by WhatsApp is accessible by everyone. We just like happen to be trusted by clients. Maybe that reminds you of like some of the talks that just happened before. Like this is very similar to what certificate transparency tries to achieve as well. I think the difference is in certificate transparency, you have a lot of CA, you have a lot of logs. And when I'm a website owner, I need to check like all of the log for certain policy to see if like my certificate has been misissued. On the contrary, key transparency takes a different approach in the deployment we've done with WhatsApp in the way that like the log has to seek a signature from the auditor before its updates are trusted by the client. This allows the clients to ensure that as soon as it receives an update, it is trusted. If you try to step back and like understand a bit more how we've built that auditor at Cloudflare, the log publishes an update every 30 seconds to S3, and it sends a request to Cloudflare. We've built this service in Rust, and it runs on a WASM-compatible runtime, which is Workers. We also ensure global uniqueness with a product which we have global object, and this ensures to like have like the unique global uniqueness and the monotonically increasing property. Finally, there's like some of the work which is like a bit latency sensitive and computationally heavy, and this is a verification of the proof. And so for that, we compute that off pass. We take the proof from S3, we back it up in our own storage, which is R2, which allows us to like claim, like verify our claim down the line. We verify it, and we provide a new signature. So we have two signatures in this system. Great, but we're at real world crypto, so probably you want to see something. And so our auditor, like we've built an API, but because you don't want to see any JSON blob on slide, I think it's not readable. Let's just go and like have a demo. I cannot have a GIF, so it's just slides. First of all, we install our client, which makes the API just more pleasant to read. This is Plexi, and we install it. Then we list all the logs that our auditor is editing. The one we're interested in is the last one, which is WhatsApp. And now that we know the log that we want to audit, locally, we can request the signature, the proof. It takes a bit of time, but after some time, we have all the information like Kevin was mentioning, which is the epoch digest, the epoch highs, the signature, and it has been validated locally. Okay, so this is somehow real world, but like real world is that. Like basically, sometimes like, and this was like 2 Fridays ago, our engineers just receive a message because our auditor stops working. And this is not really something which is fun. What happened in this case? So basically we have a metric that's plotted here, which trace the epoch highs as seen by the auditor. And you can see there's a big plateau starting 10:30 to midnight. And this is when our backend for storage stopped responding. What's interesting is we have another metric in which we can see that and like reflect a bit how the auditor is working internally. You see in the middle during the incident, we don't verify anything. So like the latency for the verification is just 0. But when we resume, the latency is just like sharply increased. And this is because during the incident, WhatsApp has accumulated updates. And these updates means that like the epochs that like we have to validate are just bigger, meaning that our latency has increased. We have a couple of like other consideration and incident that we faced. We publish every 30 seconds, so you've seen that. We also have like make sure that like we have global ordering correct. And in practice, this is more difficult than like on academic papers where you assume everything runs on a single machine. And finally, there's the integrity property. We don't want anyone to be corrupt. And this is really something that like so far has stayed, but something we like really take measures to make sure it remains correct. On that, what's next? I leave it to Mari.
Thanks. All right, so obviously, as we've seen in the rest of these awesome sessions in this section, we see the work that we've been doing here within the broader context of the transparency ecosystem. So if we look back to 2013, researchers at Google launched certificate transparency, which detects the misissuance of TLS certs, and this now is a system that is widely deployed and protects billions of people from visiting fraudulent websites every day. Then researchers like this append-only Merkle tree for transparency, say less, we can do more here. So they introduced Connix, which kind of provided the building blocks for a key transparency log that of public key updates where the tree root nodes form the basis of a transparency log. Then some really important advancements were in 2019 and 2023 with Seamless and Parakeet, which provided improvements in the tree traversal mechanism for efficiency and also in the inclusion and consistency proofs, which helped improve privacy. Both of these parts of progress allowed WhatsApp to deploy a key transparency system for a scale of billions of users and millions of key updates every day. So as we've obviously talked about, that led us to, at the end of last year, in partnership with WhatsApp, launch Plexi, which is our open source auditor for key transparency. This does on-path synchronous proof validation for WhatsApp's log. So what's coming next? Well, before we get into that, we actually think that there are three important reasons why there aren't more auditors and also reasons where you could potentially get involved and help us out with this. The first is that key transparency is relatively new. It obviously involves coordination between two different parties, and sometimes that's very difficult in production. The second is that there are a lot of different KT implementations or even transparency implementations out there, whether they're Connix, CT-based, AKD-based. And while we would like to audit all of them, obviously, in practice, it's actually really infeasible for us to build something bespoke every time. That's why we're really excited about the work going on at the IATF Key Transparency Group, and we would love to see more energy and participation there. And then lastly, in the real world, compute and latency is actually hard to get right. So even with the efficiency improvements that the WhatsApp team has made over their tree traversal algorithms, what we've seen is that for synchronous on-path proof verification, we actually exceeded our edge worker CPU limitations really fast, had to move to a different architecture, are still very much improving that architecture as we speak. So you're probably wondering, well, how can we see if proof validation, if these audits are actually working, and what to do when they fail? And the kind of first way to see that is we think that should be built into the messaging apps themselves, as Kevin talked about. The second is that you can actually go to dash.keytransparency.cloudflare.com and check the results with your very own eyes. You can also check our work and actually run Plexi yourself by going to GitHub and downloading our open source CLI. And at the end of the day, what I'd like to close out with is saying that we would love for this to be less of a partnership just between WhatsApp and Cloudflare and more of an ecosystem where there are many transparency logs and many auditors auditing those different transparency logs. So if you are a end-to-end encrypted messaging app or any sort of end-to-end encrypted app that wants to work with us or even extend Plexi for your own auditing purposes, please come talk to us. We think that, at the end of the day, end-to-end encryption is, I think, in Europe and really all around the world under more threat than ever, and that progress towards transparency and auditability is really important for improving the trust, integrity, and security of end-to-end encryption. So thanks for listening.
Unfortunately, we're out of time for questions. So if you have a question, please find Mari, Thibault, or Kevin during the coffee break, and we'll see you back here at 3:25. Let's thank all the speakers again.
think we can start. So this is the fourth session for today and the last one in the afternoon. It's a session on side channels. It's a really cool one, and we do have 6 talks. The first one being Stealing Keys with Weird Gates by Eyal Ronen.
Right. Okay. So thank you very much. And this work is based on 2 papers where it was joint work together with Chichanok Yuval, but most importantly with our students, Daniel Katzman, William Koshak, and Gal Horovich, which of course did all of the heavy lifting, but they decided to graduate and move to other fields. Don't know what is outside academia, but apparently they went there. So I'll be giving a talk. Okay. So in this talk, what we're going to do is we're going to talk a little bit about weird gates on microarchitectural states. We're going to define the logical state of the cache, and then we show how we can do computation on this logical state using what we called weird gates. Afterwards, although this is, for me, a lot of fun and interesting by itself, for some reason, we need to actually motivate our work, except for the fact that it's fun to work on. So we're going to show how we can actually exploit the weird gates, both for fun and for somebody maybe for profit. And we're going to show how we can do more complex computation. And we're going to show how we can use them to overcome coarse-grained timers mitigation for side channel attacks. And how we can reuse them to break SBox-based AES implementations. All right, so we start by defining a logical state of microarchitectural cache. So we're going to start by basically associating a logical Boolean value with each memory address in the physical memory. And the physical memory address is going to be denoted as true if it's currently cached, and false if it's not in the cache. So we can start with the following assignments. We only have 2 addresses in the cache, both of them are true, everything else is false. Afterwards, we can actually set addresses to false by flushing them and evicting them from the cache, then setting the value to false. On the other end, anytime we're trying to access some memory address, it's going to set its value to true. There's a byproduct that we might also set another to false by evicting it from the cache, but this is a byproduct which we can work around. Okay. In order to actually see architecturally what is the value of a memory address, we can measure the access time, and this will observe its value. It will give true if the access time is short and false if the access time is false. As a byproduct, this is going to always set the logical value of this memory address into true. Okay, so we can set values, we can change the values of the logical state, but this might not be very interesting. So the question is, what else can we do? And we're going to talk about conditional access. Yesterday, in the Levchin Prize, we got 2 really nice recommendations for life. First of them was read, read, read. The second one was code, code, code. So we're going to do it, and we're going to read code. So, and we're going to start, and we're going to ask what happens if we run this process. So we have a branch where we access an input address. We check if its value is going to be 0, and if it's 0, we're going to return. Afterwards, we're going to take some pointer to our output address. We're going to do some really silly looking computation, just adding 0, doesn't change the value. And then we're going to actually access this out address. And the question is, what is going to be the cache state of this out address after execution? So of course, if the value of the input address is not 0, then we're going to access output because we're not going to return, and the value is going to be logically set to true. However, we can ask ourselves, what happens if the input address is 0? And then it still might not be very clear. Let's assume the input value is 0, and throughout this talk, every time, all of the values of the memory addresses are always going to be 0. So we're going to assume this. And now, what the CPU needs to do is going to evaluate the branch. And this evaluation can take time because we need to compute. The CPU is efficient. The CPU doesn't want to wait. So what the CPU is going to do is going to predict the future execution. It's going to predict if the branch is going to be true or false. And if the prediction is correct, then great, we win. We don't need to wait for the branch to actually be solved, and we can run much faster. If it's incorrect, then we're a bit sad, but we don't lose by much. We're simply going to roll back the state of the CPU and try again with the correct value. So overall, net gain for humanity. However, the note is that although architecturally, if we mispredict it, we're going to roll back all of the values of the register and the CPU state, the microarchitectural state still remains. We don't roll back this state, including whatever changes were done to the state of the microarchitectural cache. So even if input is equal to 0, this line of code can still be executed speculatively. And this means that the value of the output address will be turned into true. Now we're going to assume that the branch is always mispredicting. It's going to always mispredict because we're going to train it to mispredict. This is something we know how to do. And now we ask ourselves, will the output address be accessed or not? And now we might have two options. What we get is basically some kind of a race condition, because we have the part where we load the input address into a register. We're going to evaluate the branch. And on the other end, we have some delay instruction. This is the out plus equal 0, some not. And those instructions are the output address is dependent on those instructions. So the delay chain, what we call a delay chain, needs to be computed before we can access the outside memory. And then the question, what happened first? Can we get the input value? And if, for example, in is inside the cache, meaning its value, Boolean value is true, then it's going to be relatively short time to get it, short time to evaluate the branch, and then we can actually squash the speculative window and stop the execution before we get to the code line where we access the output address. On the other end, if input address is not in cache, it takes a very long time to access it, then before we are able to evaluate the branch and squash the speculative window, we are already going to run the code line that accesses the out address and change its value to true. Now, if we look at it, we can see that we actually have a truth table that says for every Boolean value of input, what is the Boolean value of output after this gate. And this is actually a NOT gate. So here we can see we can actually do a circuit, a simple electric gate that runs on the microarchitectural state. Now, NOT gate is nice, but might not be that interesting. So we can build some more complex gates. And before that, we need to think about what is this, how is this gate works, how is it built? And what we see was basically, we have two chains that runs, and we have this race condition between them. One chain is the signal chain. This is what actually accesses the output address in the end. And one is what we call the control chain that evaluates the branch. And we have a race condition between the both of them. And we need to have some delay instruction in order to make sure that the race condition is one only if the input address is in cache or not. And we have the probe that actually checks the cache value of the input addresses. So now we can actually combine several such chains. So for example, we can have the following code where we have where we check if the sum of two input values is equal to 0 or not. And now we can use the same view, and we can see that if a single address, input address, is not in cache, then it will take this branch a long time to evaluate, and we will be able to access the out address. Otherwise, if both addresses are in cache, then this will be resolved quickly, and we don't access the output address. And again, we can have the truth table of this gate, and we can see that this is actually an AND gate. It's only return false if both input addresses are true. And the nice thing about an AND gate is that we can use it to actually build any kind of circuit. So this allows us to compute any arbitrary circuit on the microarchitectural state. Now, I lied a little bit because we have an interesting phenomena here. And the thing is that the computation that we do is destructive. because when we run a gate, then we always access the input addresses. And this means that their logical value is going to be set to true afterwards, regardless of the original value. And this means that we can only use an address input once. Afterwards, this is destroyed. So we need ability to build more complex gates where we have a single wire that is an input to several different gates in parallel. And the way that we do it is by increasing what we call the fan-out of the gate. And this is relatively simple. We just access several output addresses in parallel. And this means that we can duplicate the output address. And we can actually build what we call fan-out gates, which take a single value and copy its state into several other addresses. Okay, and although we can use NAND gates to build whatever we want, we sometimes want to have some more complex gates in order to make them more efficiently. So this is a very interesting computation, which is very clear to understand the truth table. And in the end, I will translate it. This is the knot of a majority gate. And the nice thing about this is that this can actually be used to do error correction on our computation. Because we run things on the state of the cache, and this is noisy, we have operating system and other processes, we might want to repeat several computations and then do error correction on the results. And this allows us to do it relatively efficiently inside the microarchitectural state. Okay, so now I told you we can do weird gates. I think this is really cool, but it's not enough to convince the reviewers to get papers accepted, and we need to show them that this can actually be useful for something. So now we can talk about what we can do with circuits. So for example, we can do 4-bit ALU inside the microarchitectural state. We can do SHA-1 computation. This is nice because if you want to do some obfuscated computation that is very hard to debug and understand it, then we can do everything inside the microarchitectural state. But maybe more importantly, we can actually play the game of life. And we can do it for several generations. And this is basically the heat map of the output of the results for several inputs. For me, this is a good enough motivation to do the research, but we work in crypto and security, so we need to have some security implications, which game of life doesn't necessarily have. Okay, so let's talk about flash reload. Everybody knows and loves this attack, square and multiply. You can do it on RSA, Diffie-Hellman, El-Gamal, whatever is your favorite exponentiation algorithm. So this is an example of attack on RSA, I think. And we can see that the difference between the cache hit and miss of this attack that we do is roughly about 40 nanoseconds, which is a relatively short time. We can measure this timing difference when we have access to native code on, for example, Intel x64. However, this was also noticed by, for example, browser developers, and decided that if we want to mitigate this type of microarchitectural attacks and speculative execution attacks, then maybe we just prevent anyone access for high resolution timers. So if we look at Chrome, we can only have access to 0.1 millisecond time resolution. Tor, which should be more secure, has 100 millisecond. And even on native code on Apple M1, we don't have a very high resolution clock. So this makes it much harder to do this type of attacks. And we want to be able to reduce the required time resolution. And actually, we want to be able to measure this photo finish type of timing difference with maybe even a wall clock. And microarchitectural gates can actually allow us to do this. So what we're going to do is basically we're going to amplify the signal. So as a primitive, if we have a NOT gate with a very large fan-out, we can basically take the logical state of a cache address, if it was inside the cache or not, and copy it to 8 output addresses. And this gives us an 8-time factor in the timing difference from 40 nanoseconds to 320 nanoseconds. This might still not be enough, so we can use this tree structure to increase it to 64, 512, 4096. In real life, this even might not be enough, and we have limited space where we can do the amplification because the cache size is limited. So we have a nice hypertree structure, which allows us to basically increase it to arbitrary values. So we can now copy the state of a single cache hit or miss, and do a computation where the timing difference between this cache hit or miss will be 0.1 seconds sometimes, and we can actually go much higher than that. But Now we're able to amplify, but this is only half the job. So now we can differentiate between the single hit and miss. However, we want to attack native code exponentiation, and the time difference that we need to, the temporal resolution of the attack needs to be about 25 microseconds. We can increase the RSA size, maybe we'll use 6,000 bit RSA, it will make it a bit slower, but this is still much faster than what we can do when we do amplification. So what we're going to do is basically allow us to do high resolution prime and probe, sample in a resolution that's much faster than the clock that we have. And the main idea behind it is that if we look at prime and probe, we can see that this is actually a type of a NAND gate applied on the eviction set. Think about it or read the paper, you will see it. So what we're going to do is we're going to repeatedly probe our eviction set, which means just applying a NAND gate, but each time we're going to store the result in a different memory address. And we're not going to measure the result. We don't know when the cache hit or miss what happened, but we're going to store all of this in memory. And after we finish the attack, then we're going to amplify. This decouples the probing from the time measurement itself. Now, this introduces some more complication because we can't actually store all of the samples we need for example, for full RSA or L-Gamal computation, but we can measure large enough chunks of the attack and then stitch them all together. And we were able to attack a square and multiply L-Gamal with a 0.1 millisecond clock. Which again, it's basically the clock time is pretty much the time it takes to run the entire attack. Okay, so this is nice, but this is not all. This raises the natural question of how fast can we probe? What is the fastest resolution for microarchitectural cache attacks that we can do? And so far, the state of the art was with this really, really nice paper called the Priming Scope from CCS 21, and they had something that is almost optimal. They only need one access to L1 cache to see if something is inside the cache or not. However, this access is about 5 cycles, and the resolution is 70 cycles. And ask yourself, where does this overhead comes from? And if we look at it, it's basically, again, the time measurement that we need to do. Measuring the time is order of magnitude larger than the actual thing that we try to measure. So we have the primal store. This is our hammer. Let's try to use it on this nail. So after some optimization and finding a very efficient gate, we can actually improve and get it down to 48 cycles, which is nice. It's better than 70, so we win. But it is still an order of magnitude larger than those 5 cycles that we actually want to get to. So what we do is we're going to use the same idea of gates, but now instead of sampling an input address once inside the speculative gate, we're going to repeatedly sample it over and over again inside the speculative execution. And if all of those load addresses are going to be inside the cache, then we're going to return before any of the delay function returns. However, if somewhere inside if we get a cache miss at some point, then all of the accesses before it are going to be into memory, and we can actually detect which of those loads was the one that gave us the cache miss. We have nice graphs that show that we can actually get a resolution that differentiates between 5 cycles offsets. And we can use it to attack S-box AES, which is a much harder target than the regular T-tables because it's a much smaller table and which we access much more. And we need to distinguish the exact AES round. And we need a very fast sample rate. And PowerWork needs some non-trivial assumptions to do it. We were able to do it by actually measuring the exact round, which we did not by measuring when the computation started, but we actually measured the time difference between accesses to 2 different S-box cache line, which are about 10 to 20 cycles, CPU cycles difference. Okay, and we were able to attack it. Requires about 10,000 traces, and everybody are happy. Okay, so to summarize, microarchitectural weird machines are a thing. It's very fun to work with. It can actually have some security impact. And we think that it's a new emerging area, and there's a lot of work to do in it. So if you're interested, I'll be happy to chat, and I invite you all to have a look at it. Thank you very much.
Okay, maybe one quick question.
So it's a great attack. The question is how to mitigate it.
Right, constant time code, basically. This is the best answer I can give. This is, actually we disclose all of these attacks and everybody said, all of the vendors said, okay, but this is not a vulnerability. This is how the system should work. The vulnerability is in the code. We said, okay, we agree, we can publish faster, everybody happy. If you write secure implementations, then this attack will not matter.
All right, maybe a future paper. Thank you very much. So our second paper in the session will be testing side channel security of cryptographic implementations against future microarchitectures. And the speakers are Chichanok and Marco.
Okay, good afternoon, everybody. Today I'm going to talk you about how you can test whether your cryptographic implementation is secure against microarchitectural optimization from the future. Okay, so let's start. So computer architects and hardware vendors keep coming up with new and new fancy microarchitectural optimization, which is great because, you know, we go fast. But at the same time, we all know that microarchitectural optimizations come with side channels, which is not great in general. And in particularly, even more important, a recent study from Sanchez-Vicarta and others identified that a lot of optimization proposals that the computer architecture have been developing over the years, but are not implemented yet in modern CPUs, are actually security critical. They can be exploited to compromise our cryptographic implementations. And the core question that we're going to answer is, how can we evaluate the security impacts of these optimization proposals? And in particular, how we can do it, you know, early on, potentially before these implementations are implemented in silicon. And what I'm going to present next is a testing-based approach for reasoning about the security of cryptographic implementations for current and future microarchitectural proposals. So let's start with the very high-level pictures with a lot of gray boxes. I'm going to fill in the gray boxes throughout the presentation. So at a very high level, we start from a cryptographic implementation, potentially with some side channel mitigations implemented in it at software level, and a description of the optimization proposal that we want to test. And we're going to produce a list of potential problems indicating leaks. So let's try to refine this a bit. So the first step is, as I said before, we are talking about optimization from the future, so they might actually not be available yet in modern CPUs. So we're going to replace the description of the implementation of the optimization proposal with a leakage model, which is a formal model capturing at high level what information might be leaked through a side channel to a side channel attacker. And for everything that we need here, you can think of a leakage model as something that maps a program execution to a leakage trace, namely a sequence of high-level observations describing what might be visible to a side channel attacker. And and we're taking a program input. So to capture these leakage models, we developed a modeling language called LM-Spec, which I'm going to describe next. So what the user has to provide is this formal leakage model described in terms of a set of prediction clauses and a set of leakage clauses. So what leakage clauses do is they describe what kind of information is visible to a side channel attacker. In practice, they describe what ends up on the leakage trace, and users can formalize these leakage clauses by associating them with a set of high-level events that might happen during program execution. In particular, we support leakage clauses associated with changes to the value of architectural registers, both reads and writes, memory loads and stores, computation of addresses, evaluation of sub-expressions, and changes to the control flow statement. And the leakage clauses will describe, based on these events, how we compute observations. So let me give you a few concrete examples. Let's start with something that we all know, the standard side channel model, the standard constant time model, sorry. So this is how we implement it in our language. We have, we produce observation based on 3 events. So whenever memory load happens, then we are exposing on the trace the address. And we do the same for memory stores. So again, we expose the address to capture leaks through the data cache. Whereas for changes to the control flow, we add to the trace the resulting value, okay, the next program counter in practice, which can be encoded like this. So as I was saying from the beginning, right, the idea here is we can reason about microarchitectural optimizations from the future. So let's look at something that is slightly more interesting, namely, oops, I forgot the thingy. So let's look at something more interesting, namely an optimization proposal called silent store suppression. So the core idea behind this proposal is, there might be, you might actually have some stores that are to a certain extent useless in the sense that they're not gonna change the value of the architectural memory. And computer architects have been coming up with ways of detecting these useless stores early on and suppressing them at the beginning of the CPU pipeline to, speed up computation. And we can model the leaks associated with, and over-approximate the leaks associated with this optimization in our language with the following clause. So we intercept store operations. Whenever the store operation happens, we check if the value of the store operation, if the value that we're writing is the same as the current value of the memory. So the store operation is what is called silent. And if that's the case, we simply record that on the leakage trace because this store might be suppressed and this might result in timing leak. Okay, so the second part of our language allows us to talk about speculatively executed instruction. In particular, we have prediction clauses, which at the very high level capture which mispredicted paths need to be explored during the testing. And we support both control flow and data flow speculation for this. So I'm not going to go too much in the details here. I will just give you a concrete example, namely how we model branch speculation in our language. So we do so with the following clause. Again, we intercept, the event that we intercept is changes to the control flow. So whenever there is a change in the control flow during the execution of our test case, we check if the instruction causing the change is a conditional branch. And if that's the case, we are going to produce a prediction. So we're going to mispredict the value of the program counter to the wrong path, right? So if the condition is satisfied, we're going to take the else branch. If the condition is not satisfied, we're going to take the then branch. And this is high level how we describe it. And I'm going to explain next how we actually use this to do testing, but at a very high level, you can think of it as our leakage model. We just explored the mispredicted path based on this prediction for a fixed number of steps. Okay, so now we know how to model, how to specify these leakage models. What can we do with them? We developed a tool that can be used to test programs and detect leaks based on this leakage model. So the user has to provide the leakage model, the prediction and leakage clauses. And then our tool takes as input a binary program, an x86 program. And importantly, we also need a labeled interface that describes what are the inputs to this program, to our cryptographic implementation, and whether they're public or secret. And what the tool will do is we'll produce a set of violations, namely a set of leaks. So to detect these leaks, what we will do is we will search for pair of executions that are public equivalent, namely the public part of the inputs are the same, but result in different leakage traces for the model. Okay, so this indicates that there is a secret dependent flow of information from the inputs to the leakage traces, which is what the attacker can observe. So how do we do it? Well, we start by generating pairs of inputs that are public equivalent by generating first one random state and then mutating the secret part to obtain a public equivalent state. Then the core part of our approach is an executable semantics for our leakage models. We actually take the prediction and leakage clauses specified by the user, and we compile them down into a set of event hooks for the Unicorn CPU emulator. So the way this works is During the execution, the leakage clauses will be compiled down to these hooks that intercept events and compute leakage observations whenever the condition of the leakage clause is satisfied. Whereas for prediction clauses, whenever there is an event that satisfies the clause, what we will do is we take a checkpoint of the emulation state. We compute the predictions following the what is specified in the model. We update the state based on these predictions. We explore the mispredicted path for a fixed number of steps while collecting the observations produced by the leakage clauses. And at the end, we just discard the computation. We go back to the initial state and we restore the state that we saved at the beginning. Okay, so this allows us to enrich the architectural simulation with additional speculative paths. So we do this twice for the two inputs, and we simply compare the traces produced by the model. So if the traces are different, we detected the leak, which gets reported to the user with additional information about where the leak is located. And otherwise, we just go back, we continue testing by generating a new pair, and we keep running this loop until timeout expires. And I think that's it. And Chichanuk will go on with the case study.
Thank you, Marco. Wrong button. So before I continue with our case studies, I would like to recall our motivation. So Marco has already explained about our tool, and our motivation is that we would like to evaluate security impact on cryptographic implementations due to microarchitectural optimization. So we need to say what microarchitectural optimization that we consider. And in our work, in our evaluation, we consider 18 of them. And these are from 8 main classes of microarchitectural optimization. So the first one is consent time. Second, silent store and register file compression, computation simplification, operand packing, computational reuse, cache line compression, and prefetching. So all these 8 classes. And if we consider their variants as well, then we will get in total 18 microarchitecture optimizations. And this is what Marco referred to leakage clause. And aside from a leakage clause, we need to specify another thing, which is prediction clause. And in our evaluation, we consider 6 execution models. So the first one as a baseline, sequential, or no prediction at all, or no speculation at all. And the rest 5 would be about speculation, which are conditional branch, straight line speculation, store bypass speculation, and return address. And for the return address speculation, we actually model 2 of them. So in total, we have 6. And if we consider these all together, in total, in our work, we consider 108 leakage model. And to the best of our knowledge, when we submitted our paper, this was the largest leakage model to be implemented in a single tool or a single language. And we believe this is still the largest. And aside from leakage clause and prediction clause, of course, we need to specify implementation that we want to test. And as we said that we want to focus on cryptographic implementation, then of course we consider cryptographic primitive. Consider 8 of them, ranged from symmetric to public key cryptography. Other than that, all these cryptographic implementation, they are from 5 popular libraries, which are libsodium, libjade, libnetl, cryptlib, and Rust crypto. So in total, we consider 25 implementations in our evaluation. You might want to see the result. So here is the evaluation result. I know it is pretty small, and I do not expect you to read. What I would like you to see is the overall picture of our evaluation. So I can tell you that each line, these are 25 implementations, and we group them into 5 libraries. So that's the row. And in terms of columns, these are 8 classes of microarchitectural optimizations. So the main 8 ones, and then sub columns would be the variants for each of them. And what you can see here, you can see that there's red in every line. So from our analysis, all analyzed implementation leaked. So that's why in each line, you will see red somewhere. And if we look at memory safe languages, like Rust, for example, so I highlighted there. So that doesn't significantly mitigate the risk. There's still leak even in Rust implementation. And if we consider consent harm programming, there's still leaks. So like in libsodium or in libjade, they not fully prevent the leak. And if we look a little bit further, and this I need to zoom in a little bit, we found that majority of the leak that actually comes without prediction or during sequential. So I zoom in a little bit that we consider 6 execution model and there are 6 diamond shape. And if they all have the same result, we just group them into one. And before the end of this presentation, I would like to give one example, which is leak from consent harm swap. And this is from libsodium, which should be consent harm. So if you look at the code, so I have to say that for this one, we have 2 variables, f and g, in like 5-element array, and we want to either swap or not swap, depending on the Boolean bit or condition bit, and this is secret. So because libsodium, this implementation follow consent harm programming. So as you can see, there's no branches, there's no secret dependent array index. But then the way to do that, so first, the secret bit B is extend to 64 bits in mass, and then F and G, they're XOR together, and then into X, and then X, and with the mass. And mass could be all 0 or 1, depending on the bit. And the last 2 steps, just XOR X with F and G, respectively. And well, the leak, of course, doesn't come from consent harm, but then it comes from something else. So the first part is come from register file compression. Why? Because if mass is 0, then if you end with 0, then the result will be 0. Then it compressed into 0 register. And that's not the end. Then there's another leak come from computation simplification. So if mass is 0, again, XOR with 0, then the value will not change. Then computation can be simplified because that computation doesn't do anything. So XOR can be simplified. And the last one is that if the value of F and G, if they remain unchanged, so if the value are not swapped, then the memory will not be modified. Then again, then silent store comes in. Then if you store the same value, then you don't need to store in the first place because you store the same value. So there's another leak from silent store. And to summarize our work, so first we introduce the language to express this leakage model. And then we have a testing framework, which is automatically detect for the leak. We just let it run and wait for the result. And another thing is that we did extensive evaluation. And we found that if these microarchitectural optimization were in place, then all of these implementation would leak. And I would encourage you to look at our paper, and there will be more detail over there. And with that, we are happy to take questions.
So we have a couple of minutes to take questions. All right, then I'll ask one. Do you intend for this tool in the future to propose some solutions? So like if it highlights code that's at risk, could it propose a replacement code that would not leak?
It can be done. I think for a few of the leakage models that we've been playing with, we have good ideas on how to rewrite leaky snippets. But then it's still something that at the moment is kind of manual, and you need to come up with a smart transformation for each of the leakage models.
I mean, I would like to add a little bit that for this tool, it should be for the vendor as well, or people who try to do optimization. So maybe they could test whether that will be like security impact on some implementations, like for cryptographic implementation. So this meant to be the tool for them, developers and vendors as well.
Okay, yeah. Fantastic. Thanks. All right, 16 seconds. Go for it.
And to what extent are vendors responsive to this, like hardware vendors? Will they not ship a new optimization because it causes leakages?
I mean, I think I've had a chat with folks at Intel, they kind of like having tools to play with, then are they gonna use them or are they gonna do something based on the results? It's unclear.
Yeah.
Okay, then let's thank both speakers again. Right, our third talk is actually a question and maybe an answer. Is your Bluetooth chip leaking secrets via RF signals? And Elena is going to give the talk.
Thank you for the introduction. It's a joint work with my two PhD students, Yaning Zhi and Reisa Wang. The motivation behind this work was to find out whether millions of Bluetooth devices which contain cryptographic accelerators leak secret. And our contribution was that we demonstrate the first attack which extracts secret key from a crypto accelerator. It's advanced encryption standard with 128-bit key for a side channel, which you may not be aware, it's RF signal. So it's actually carrier RF, which we capture using software-defined radio, and we extract side channel from it. I would like to give you some previous work on previous attacks. It's not a popular side channel, but there were some attacks presented. The first one was in CCS 2018, so some years ago. They extracted secret key from a software implementation of advanced encryption standard, which was programmed in Cortex M4. This is a processor which is contained within that chip. It's the same target chip as the one we're using in this attack. And it was a tiny IF implementation, meaning it processes things byte by byte. It's actually easiest to attack. So you can see from this table that they use a template attack as a method. And first attack was on a 10-meter distance in a lab. And then you need to repeat the same encryption 500 times to reduce the noise, increase signal-to-noise ratio. And they needed 1,400 something traces to break it. Then they also did an attack on a closer distance in an office environment, which is clearly more noisy. And then they needed same number of repetitions, about 52K traces. So it's quite massive attack. And then 2 years ago, after that, the same team of people presented a paper in Chess where they repeated template attack on a 15 meters distance in an office environment, much longer, which 1,000 repetitions, you say it's double because the noise is much higher. It's a longer distance. And they needed some enumeration to power 23 and 5K traces for the attack. Same year, we presented an attack which used neural networks to model leakage. And you can see it was in an office environment. What we wanted to achieve is using single repetition of the same encryption, not multiple. And we succeeded to do it with some effort. So we need 341 trace on average to recover the key from a single repetition with no enumeration. But I would like to stress this is a software implementation of advanced encryption standard, tiny IAS, which is very easy to break. It's unprotected. So what the question we had ever since, myself personally at least, can we break an IIS hardware crypto accelerator which is available on the same chip? Because why would you program something in Cortex if you have a hardware accelerator on this chip, crypto accelerator, sorry. But apparently it's very difficult, and the author of the CCS paper, the first time it was published, they say we cannot break it, it doesn't leak, apparently. And we were trying to do it for quite some years. One thing which complicates the attack, previous attacks were in electronic codebook mode, where you have complete control of plain text and ciphertext. And this hardware, this crypto accelerator, which is on this chip, it implements advanced encryption standard in CCS mode of encryption. So you use counters to produce key streams. That's what I will have a diagram in a slide or so. And then also the clock which is used for this crypto accelerator is different from the clock which is used for Cortex. Cortex runs at 64 megahertz. This advanced encryption standard runs at 16 megahertz. So it wasn't very clear whether we get any leakage from this ASIC implementation of advanced encryption standard. So our questions which we wanted to answer is, can we extract encryption key from RF carrier signal on a distance? And one thing which I would like to stress, why it differs from power or EM analysis. Power, you would need to solder in an element, so it leaves tamper evidence. EM, you need to be on a millimeter distance from your target device. Here we're talking about meters from the target device with no tamper evidence left because you don't modify device in any way. This is the way I will try to first explain you, because I assume most of you are not engineers, but cryptographers. Let's discuss why mixed signal circuit may leak secret. What's so special about having a mixed signal circuit? Like, think about two glasses on the same surface on a table. We knock with some stick on one of them, there will be circles on the surface. And we may get circles also on the surface of a second glass, because they share the common surface. They stay in the common surface. And also think the closer they are, probably the more disturbances we will get. The more isolated they are, the less disturbances we will get. And it's similar in mixed signal circuit because we have a digital part where we have this crypto accelerator. We also have Cortex there. And there are a bunch of other elements. And then we have an analog part with some elements. So what happens is that digital noise produced during the computation, key-dependent computation of advanced encryption standard, it propagates to the analog parts. It leaks there through a number of physical phenomena. One of them is substrate coupling. So we get some noise propagating, affecting elements in the analog part. And one element I would like to particularly pay attention, so this is what I said about the substrate coupling, is this VCO, voltage control oscillator, which is actually a block which generates your carrier signal based on the input voltage. So if that digital noise affects that input voltage and the block, that carrier signal may get slightly modulated and then transmitted. So what will happen, that side channels are getting entangled into that transmitted signal. It modulates it by the amplitude. At least we are exploiting the amplitude in our attack. And this is why we can get it on a distance from device by demodulating these RF signals. So here is our attack setup. Our target is Nordic semiconductor chip, NRF 52832 system on a chip. Our measurement setup is we basically have it in an office. You see this large antenna with a target device on 1 meter distance. We could make it larger. In the previous attack, we made it on a 15 meters, but this previous attack was done during COVID time, so nobody was in the office. Now, unfortunately, we cannot afford it. We don't have COVID, so we hijacked one office of a person who is away somewhere for a year, because you will see this attack took us quite some days to do. So we basically put a label, don't go in the office, for anybody not to disturb our measurements. And that's why it's just 1 meter. It could be longer. It actually doesn't matter because it's well-formed signal we are capturing already. So we're using that white box, which you see, it's a software-defined radio. It's actually cost $10,000 US. It's quite expensive equipment. We tried first with the cheaper one, it wasn't working. With this one, we can sample at the frequency of 50 megahertz. So it's roughly 3.1 something points per clock cycle we get, because obviously the more you get, the better. And important question is at which center receiving frequency we are demodulating. So it is the Bluetooth band frequency 2.4 gigahertz plus a multiple of the clock frequency. And well, you can see details, so we can discuss it offline, why and what, but that's basically the center receiving frequency at which we're receiving, demodulating, and we are getting these side channels, which look like normal power or EM near field trace, more or less. It actually looks like a power trace. Key recovery methods are standard, more or less. We try both profiled and not profile attack settings. Profiled is good old correlation analysis. That was the first attack we succeeded. And then we also tried deep learning-based analysis. The reason we tried it later is that you need a lot of time to capture the training set. Months, we're talking about months. So this is a diagram of advanced encryption standard, 10 rounds, 128-bit key. As an attack point, we use SBox input in the last round. And the reason for this, why not in the first, probably you have an idea, it's because it's a counter encryption. So in the counter encryption, we can only control the nonce, which is 8 byte. So even if we recover everything, it would be just 8 byte of a key. There are techniques actually to propagate it, but we noticed that the leakage is not that strong. So the SBox input in the last round was leaking strongest. It was leaking stronger than more traditional leakage model for hardware implementation, which is typically a distance, Hamming distance between ciphertext and SBox input. It also leaks, but it leaks less. This one was leaking stronger. So we had a nice talk yesterday about authenticated encryption. I just included this one slide to remind you. So counter mode, 0 block is used for producing key stream S0, which is used to encrypt the MAC. MAC is produced in the cipherbot blockchaining mode. 32-bit MAC is used. And first block and all others, if you have longer messages, are used for producing key streams which you XOR with the key. So this is why I'm saying that the first round attack is not that easy, because the nonce which counter block 1 contains is 8 bytes only. That's what you can control. So we are attacking, as I said, ciphertext block 1, the output. So sorry, that was too quick. So this was our first successful attacks. We're using 180,000 traces. Each of them is computed as an average of 10,000 repeated encryptions. So in total, it is 1.8 billion single traces. It's a very massive attack. And you see the number of days we need to capture this set. It's a lot. And you can see that we're heroes because we actually try 2 different keys just to make sure that it's a consistent result. We also tried in 2 different settings. So multiply 18.9 by 4 to get the total number of days we were capturing for this table. So with cable means coaxial cable. We connected through coaxial table to device under attack, because coaxial table gives you more or less noise-free environment, more or less free from environmental noise. So if you would clean environmental noise, this is roughly what you would get. So in that column where you see 2, 2, 3, 4, it's the number of key bytes which we are not recovering correctly. And then one can enumerate, because you can get some statistic of how many number of bytes you expect not to be able to enumerate. Then you can take all possible choices, 16 choice K, where K is the number of bytes you expect to fail. And also we noticed that it is a better strategy to not to try to get all the bytes, because there are some tough ones. It's quite different, the difficulty of recovering each byte, completely non-uniform. So there are some tough ones which just we would need to double. And even then we don't recover, in fact. Even if we double, we try doubling. So this was our first successful result. Then we tried deep learning. So we spent months on capturing this training set from 4 different devices, which are certainly different from the ones we used for the attack. And because you want to use different devices for profiling attack, because then you kind of cancel out the effect of manufacturing process variation, which is quite important effect. It's very different what you get. So you see, we actually recover all the bytes for the cable capture traces, and we don't recover 1 in both cases for the antenna capture traces. So then we reduced, we half, we just went by binary search. We half the number of traces, and then here are the results for correlation analysis. We're still fine for cable. We are not fine for antenna because it's too long. You cannot enumerate this. And then with deep learning based analysis, it was still quite good, so that we further halved. This is already like 5 days of capture, getting there maybe another few times to half, and we have a nice working practical attack. So this is the correlation. You see, for 1 key, we can still do it by correlation, but for another one, it's kind of getting a year and a half, a bit too long. Then we cannot get it by antenna. In deep learning, it's still working. And what I didn't say about deep learning, but I'm running out of time, we're using ensemble of 3 models constructed in a different way. We give all the data available so you can see our structures and stuff. And that's why we know which bytes are wrong. In fact, for correlation analysis, we don't. And now mitigation strategies. What do we need with these glasses? Isolate them, put them further apart from each other, maybe change the substrate. And these are the actual mitigation strategy. At the circuit level, engineers are fighting to stop this noise from propagating purely for functional reasons, because functionality wouldn't work, but they are not taking security as a design objective. That's why it's nice to be aware of this type of attacks. Maybe they will try a bit harder to isolate, and there are known techniques in VLSI for this. Algorithm level, we can apply masking, shuffling. There are some other countermeasures like look randomization of duplication. We have a paper on this. It's quite nice. On protocol level, update the key frequently and force fresh nonce. What I mean by force is actually generating a nonce on device. For example, the way we do it in Kyber, encapsulation, 256-bit message is generated at random on device, not left to the user to decide. If we would do it here, this attack would not be possible because we wouldn't be able to average. It would always be a fresh nonce. For each encryption, we notified Nordic Semiconductor, gave them all our scripts and data for independent evaluation. And to conclude, it's the first successful attacks. We need to be aware of this RF side channel. Security implication, you see it's a challenging attack, but we keep improving this. This weekend, we already have a slightly better results. I think we can do it like with 30K traces now, and probably it will keep getting down. It's not limited to Bluetooth, nothing special about that chip. Be aware when you integrate antenna or anything from radio transmission chain in your chip, you may be opening some new ways, new attack vectors. And key takeaway, we need proactive defenses against this type of RF-based attacks before they scale. Thank you for your attention.
Okay, I think this time we don't have time for questions, but please ask questions offline or during the next break or tomorrow morning. All right, our next talk is cache timing leakages in zero-knowledge protocols, something slightly different. And the talk is given by Shibam.
Oh, thanks for the introduction, and thanks for being here. So, cache timing leakages in zero-knowledge protocols. It's a joint work with Christian Reckberger and Markus Schroffnegger. So, okay, that does. Is this a button?
I don't know how that works, but I'm sure somebody does. There's different buttons to try. Can we get some help up here? There's a way of doing it for sure.
It was other way around. Sorry. So yeah, side channels are everywhere. So be it the ancient Greek fire where people tried to decode the chemical formula from the smell and the color, or the 1940s bell mixer EM radiation, or just someone looking into your house at night to see when you go to sleep, or the funny story of the Pentagon pizza order. So looking into these two separate domains of side channel attacks and zero-knowledge protocol, just from the past 2 years, we see there's a lot of activity, both in terms of industry patents and also academic sense. So the question we asked ourselves was, how does it look when these two directions are in a combined set? So to the best of our knowledge, the only work we found was actually by Trama, Bonet, and Peterson, this remote side channel attacks on anonymous transaction, where the side channel leakage actually happens due to the different communication pattern in the protocol level. And we asked ourselves the question, like, okay, is there anywhere else we can look for such side channel leakages in the CK protocol? So digging a bit deeper, we found that, well, field arithmetic libraries are heavily used in the CK protocols. And when we looked into it, we found that a lot of them actually have non-constant type implementation. And 5 of them were actually standard libraries, 2 of them quite popular custom implementations. And of course, the next question is there a part in the ZK protocol which is implemented using this field arithmetic library will also give a catch timing leakage, leaking the secret? And well, we came to the hash functions. Actually, the ZK-friendly hash functions, which are implemented with these field arithmetic libraries. So taking a case study on Poseidon hash, which is one of the case study we did, we came to our work. And just a spoiler or teaser,
in the end, we found 9 ZK companies, products, open source projects which were affected due to this trickling effect. So ZK proof and Merkle trees. So Merkle trees are used in ZK proofs. In our work, we looked into the pairing-based ZK and the Fry-based Fry with ZK protocols. And here the secret or the witness is stored at the leaf of the Merkle tree. And a ZK-friendly hash function, so preferably ZK-friendly hash function, is used for constructing this tree. So key observation was, if the field arithmetic library is leaking, so will also the hash function or the state of the hash function, and we can also leak the secret witness. Also, interestingly, irrespective of the field arithmetic library is leaking or not leaking, a certain family of ZK-friendly hash functions, namely the ones which are based on lookup table in plain for efficiency reason, will also naturally leak the witness. So looking into the ZK-friendly hash functions family, so we classified into LUT-based and non-LUT-based. And so in lookup based, we have reinforced concrete, tip 4, tip 5, and in our work, we took reinforced concrete because it was the first lookup-based ZK-friendly hash function. And of course, here, the leakage is expected, that there will be a leakage if there is a plain lookup. So the non-lookup family is much larger. There are several candidates, and we chose Poseidon because it's widely used in the ZK application. And here it was more interesting because the Poseidon algorithm itself is constant time. However, because of the leakage in the field arithmetic libraries, Poseidon was also leaking, and this was, interesting. So let's talk about the threat model. And we broadly have 2 separate threat models. So first is there is an independent prover who generates a ZK proof, and there is an adversary who runs a catch timing exploit roughly at the same time when the prover is generating the proof, takes the measurements, and learns the secret witness. In the second direction of the threat model, here we have a witness holder. And the witness holder does not generate the proof, but actually sends its witness in plain to the cloud prover who generates the proof. So of course, we can see that there is the witness is in plain. That means the witness holder is trusting the cloud prover with its secrets. And there is an adversary who pretends to be a genuine user of the cloud services, running a catch time exploit, taking measurements, and getting the secret witness. A bit different direction of the same threat model would be that the cloud prover itself is the adversary. In this case, the witness holder will not send a plain witness, but rather encrypted witness. And but here also catch timing exploits are possible, especially when targeting the application processor, and also secure enclave exploits are possible, but we don't cover in this work. So pairing-based proofs use elliptic curves for supporting efficient verification. And so we have the good old Merkle tree. And here there's the prover says, well, I own a coin, which is the secret witness, which is fixed by the Merkle root on the block. And the P proves the correct execution of the hashes. And if there's a leakage in the hash, it leaks the witness. So in our work, we just used quite already well-known prime and probe, flush and reload attacks, and these work perfectly. Interestingly, so these attacks are actually low-resolution attacks. And so we found that these attacks are actually not enough for Fry with ZK protocol, simply because we don't recover enough pre-image bits to reconstruct the witness with the inverse interpolation step that is required. And so here, of course, we can look into higher resolution attacks, like the ones which are at sub-catch line resolution level. And so the broad takeaway can be that the pairing-based ZK is more vulnerable than Fry with ZK, at least for these older attacks. So let's look at the target and the numbers we got. So for the first target is the reinforced concrete. Here we targeted the bars layer, which is the S box with lookup table. And of course, it's we got a leakage, and here we get the mean case and the best case bits leaked in percentage. So percentage is of the state of the hash function, and the mean and best you get, this is depending on where the lookup table is, how the lookup table is aligned in the catch with respect to the catch line, of course. Interestingly enough, the best case actually happens with the quite a high probability. The next target was Poseidon. We attacked the first layer, the add round constant layer, and here it has branching with the modular reduction, and we get these mean and the best case bits leaked. And here the mean and the best, so if the round constant of Poseidon is smaller, is very small or is very large, then we actually get the best case, or we actually get better leakage. So it's nice to be in the random for the round constant. Also, one of the very interesting findings of our work was that we found that all these arithmetic libraries that we looked into, and this is not an exhaustive list, it could be many other. They actually had a clear warning like, hey guys, we don't give you constant time guarantees, not used for production. However, when Poseidon hash function was implemented with these field arithmetic libraries in their respective ZK libraries, to the best of our knowledge, we didn't really find these warnings trickling down so well. Also, interestingly, during our work, so Plonky actually finished its audit and they pressed the ready for production button. So to the best of our knowledge, we looked into the audit report and we didn't find constant time implementation to the part of the threat model. And also there was actually a branching, which the developers acknowledged, and we also independently verified that yes, there is a branching, but it happens with a small probability. So the mitigations, so if we are using older generation of lookup-based hashes like reinforced concrete, where constant time evaluation of the S-box is quite expensive, one can actually switch to the newer generation of lookup-based hashes, ZK-friendly hashes like Monolith and Skyscraper. And these allow constant time evaluation of the S-box while still allowing the lookup feature in ZK. And for Poseidon, it was more surprising, but the fix is quite easy. Just have constant time implementation for the field arithmetic libraries, as these field arithmetic libraries actually are the foundation. We ran some experiments and we saw that, well, we get a 7 to 16% slowdown, which is not too bad. So this was actually one of the most requested thing from the reviewers and also people in general. How practical is an end-to-end attack? And we asked the side channel community, and they were quite, they said it's mostly an engineering problem. We are very optimistic that this will work out. And in December, I was at Encrypt, where I got a chance to talk to one of the side channel OG, and his take was quite interesting, that, yeah, okay, if an attacker is anyway on the victim CPU, why not just buy a system level zero-day exploit, and yeah, that's all. This was quite interesting take as well. And asking the ZK community, they are quite unsure how an practical attack will look like. So our take is that, well, pure research is often bottlenecked with the funding situation. And if there is big money at stake, well, there will be more motivation, more money, more engineers. And so, yeah, and anyway, the mitigations are not expensive, which is not always the case. So key takeaways and future direction. As the ZK use cases mature, side channel protection will be crucial, and several field arithmetic libraries are affected. The mitigation is quite easy, constant time implementation, and it's not expensive. If someone is using the older generation of lookup-based ZK-friendly hashes, like tip 4, tip 5, reinforced concrete, just switch to the newer generation of lookup-based hashes, Skyscraper. Some future direction would be to explore the high-resolution catch timing attacks, maybe like the sub-catch line resolution, power attacks, remote power attacks, and this is actually what we are also looking right now. So any collaboration is always very much appreciated. And yeah, also looking into constant time hardware implementation, doing power analysis on the hardware, this ZK specific hardwares. And yeah, so also would be interesting to see how much of these combining MPC and ZK, also known as CoSNACs, will protect against side channel attacks. And lastly, developing generic side channel countermeasures for the full protocol. And this is more inspired by what we saw that in Fry with ZK protocol, just because of this inverse interpolation step, it's much harder to execute these, or much harder to leak the witness when using these old flush and reload and prime and probe attacks. But it could be that with a high resolution attack, maybe we can actually recover the witness with the inverse interpolation. Thank you very much, and if you have any questions.
Hello. Sensibia is actually lookup based, so it should have been in a different place in the slide. Can you explain what's different about, you mentioned skyscraper that makes attacks less practical even though it's lookup based?
Mm-hmm. Sorry, I actually didn't.
Can you explain
the difference with skyscraper?
The difference with skyscraper.
And the older generation of lookup based hash. Okay, so in the older generation of lookup based hashes, so the idea is that okay, you have the S box, and so you can have a simple lookup of this S box, and this is quite cheap in plain to do, and you can use this lookup feature also in the ZK. And this provides some nice speed up, and it's cool. But the only problem is, since we have lookups in plain with the older generation, it leaks. It naturally will give timing leakage, and with the newer generation skyscraper, so this S box is designed in such a way that you can actually have a constant time evaluation of the nonlinear. Efficient constant time evaluation of the nonlinear layer, and thus you don't need any lookups. You're happy, there is no leakage, and you also still are able to have lookups in ZK, because lookups in ZK does not have this leakage problem. It's only lookups in plain.
Oh, I see. So in that case, Sinsemia is in that category because it's possible to implement it efficiently without lookups.
Yeah, sure. It's in the end, it's also it's just about the efficiency, and yeah.
Thank you.
Thanks.
All right, let's thank our speaker. All right, next talk. I'm actually not quite sure how to pronounce the title. Let me try. EUClick or EUClick?
EUClick, yeah.
EUClick, okay, by Thomas Roche.
Thanks, Elena. Yeah. So EUClick is a side channel attack and secure element from Infineon. And we demonstrated it by cloning YubiKey. So first I will define what I call a secure element. Secure element is a small microcontroller that is dedicated to do cryptography. So it's generating and storing cryptographic keys, and what it does is mainly manipulating them. What it has to do is to be secure against what I call a remote attacker, which is basically an attacker that is able to communicate with the chip. And to do that, the secure element stays simple. It has simple hardware, simple software, and also very simple I/O protocol. And but because the main adversary he has to be secure against is a physical attacker, which is much more powerful because it has actually physical access to the chip while it's running its cryptography. So it can control or observe the environment. And to do so, the secure element embeds dedicated hardware countermeasures and dedicated software countermeasures. And when it's able to be very robust against all kinds of attackers, then the chip maker can try to get a CC certification, a certification from common criteria at the highest level. so above than level 5. To do so, it requires somehow, or it's much simpler to have your certification when your sources are closed, with the secrecy of the implementation as it's taken as a layer of security. There are 4 big players, chip makers that are producing secure elements: NXP, Infineon, ST Microelectronics, and Samsung. And they are actually sharing a large market that might be a little more diverse than you might think. Like there is a smart card industry, the ID, bank cards, but you can find secure element inside hardware wallet and FIDO hardware tokens that we will be talking about, and but also inside smartphones and inside all your computers under the form of TPMs. But in fact, secure elements are everywhere in many IoT devices and any product that you can find on the field and where the adversary has access to it, and that has to secure very sensible information. YoClick is a vulnerability in Infineon secure elements. It targets ECDSA signatures. It's a side channel attack, and we demonstrate it on a YubiKey. So let's get to it. So FIDO hardware token are unique or second factor authentication, and the FIDO protocol is quite simple. When you enroll a security key to your web account, it will generate a ECDSA key pair and keep the private key inside the device. And when you're signing in, then the remote server will send a challenge that the key will sign with the private key. While this product is only doing, or mainly doing cryptography, it's easy to fall inside the adversary hands, so somehow the secure element is the right solution for that. This is a YubiKey 5 CI. This is one of the YubiKey 5 series, the most common FIDO hardware token. And I bet some of you have some YubiKey in your pocket. And here I have opened it, and you can see that there is a single chip inside this product. It's a SLE78, which is an Infineon secure element. Studying this chip inside the FIDO protocol is not that easy, so we found Java card, an open Java card from Phaeton that has the same or a similar SLE78. So when I'm talking about side channel here, I'm talking about physical side channel. So this is the setup. You have a smart card reader, and we have the smart card here, and here is a probe, an electromagnetic probe. On the right side, you have the die of the SLE78, and on top of it, we have the electromagnetic probe that is capturing the radiation of the chip while it's doing ECDSA signatures. And this is a ECDSA signature from the EM radiation point of view. So, well, I guess most of you know what ECDSA is. If you don't, the only thing you have to know is that there is a secret key D, and that will sign a message H. And the first thing this signature does is generating a nonce K. And the secrecy of the nonce is actually as important as the secrecy of the private key. If you know the nonce, and if you know the message and the signature, then you can compute the private key. The nonce is manipulated twice. First in this scalar multiplication, and this is the most expensive part of the ECDSA signature, but also it's modular inversed at the end of the computation. So if we go back to the EM trace, we can see this large computation of the scalar multiplication, and when I zoom at the end of the computation, you have this modular inversion, which is the inversion of the nonce. By studying these side channel traces, we were able to understand how this implementation was done. And in fact, Infineon chose to use the extended Euclidean algorithm to do that. In many products, when the modular inversion is done by the EEA, it's in fact a binary version of the EEA, which is more efficient. But here, Infineon chose to use the classical textbook extended Euclidean algorithm. Certainly because binary version have been shown to be sensible to side channel analysis. So this is the classic algorithm. And we also understood by studying the traces that in fact the nonce before being inverted is blinded with a mask. So it's multiplied by a random, and then it goes through the EEA. However, Infineon chose to select a random that is only 32 bits long, which is an error because if from side channel leakage I can infer the value of K prime, the masked nonce, then I can brute force all the possible masks and test all the possibilities that I have there, and I will find my private key. But we didn't stop that, or we could completely understand how the implementation is done, and mainly how this Euclidean division here is done. And surprisingly enough, Infineon developed their own Euclidean algorithm for the division, and certainly because it doesn't have so many branches. And but however, there was still timing leakage in the execution. So we could find tiny timing leakage that could relate to the values that I highlighted here. And to sum up, we have the timing leakage in the traces. We can infer information about the inner computation of the modular inversion. We have shown that we have seen that the nonce is blinded, but only with the 32-bit mask. So in our work, we have built a new side channel attack that is adapted to the EEA, and shown that the extracted information could actually be enough to recover the masked nonce and then do the attack. We tested the attack on the Phaetian Java card and then showed that we could clone the UBK using this attack. So, yay. But we didn't stop there, and we studied all the families of secure elements of Infineon, and we could show that even though the SLF78 is one of the main families, there is two other families, and for all of them, the cryptolib of Infineon didn't change with respect to the modular inversion. So the vulnerability there for all this implementation. And it had been there for 14 years, and all this product went through about 80 CC certifications. So in conclusion, we have a side channel attack that requires physical access to the chip for a few minutes, and of course it works for Infineon secure elements with the Infineon cryptolib on it, and not for other products. So when we started to study the UBK, we actually take a step back and saw that, in fact, all secure elements from Infineon are vulnerable, and then the attack could be potentially applicable to many, many more applications, for instance, where the ECDSA is used, which is, yeah, pretty wide. The mitigations are pretty simple. So Infineon implemented the logical patch, which is to increase the mask from 32-bit to the size of the electric curve. There are mitigations for your YubiKey if you don't want to change them. And I want to finish with the timeline of the project. It spanned over 2 years, but it represents a few months of work. And 90% of this work was actually the reverse engineering of the implementation. We did a responsible disclosure with YubiKey and Infineon, and during this responsible disclosure, YubiCode changed its cryptolib from Infineon to its own cryptolib, and Infineon patched its own cryptolib. We released a full write-up in last September, and I'm happy to announce that a conference paper about this work will be published at SNP this year. So while Yubico was pretty open about what happened to its product, Infineon didn't do any public statement, and what we have publicly about this vulnerability is just, in fact, the the update of all the CC certificate of the secure element of Infinium. The takeaways we have here is pretty classical, like closed source of the secrecy of implementation is a real security layer. However, you should not rely on it. And its main side effect is that if you have a vulnerability in your code, closed source will make it possible that it will stay in your code for a very long time. Well, that's it for me. If you have any question.
Thank you. Any questions? I see somebody standing up. Is that for a question, maybe?
Thanks, great talk. So if I have devices with still old Infinium chips in there, are they now all essentially vulnerable because they cannot be patched?
Yeah, like they cannot be updated. You have to buy a new device.
Okay, thank you.
You're welcome.
Okay, let's go buy new devices. Another question? Yeah, okay.
I have the RSA module, like the RSA randomness generation on the Ubico, like the return of the coppersmith attack, if I remember correctly. Was that on the same chip line as this one?
You're talking about the prime generation for the
Yeah, that one.
Okay. No, it's not. It's an older version of the secure elements.
Okay, so it's not like they didn't learn anything from, well, the certification entities didn't.
Well, it's very different attacks. The Roca attacks is very specific to Infineon design their own prime generation, and doing so, they did a mistake, obviously, and it ended up in being the Roca attack, which is not a side channel attack. It's not related to how they implemented the stuff. It's just how they designed the stuff.
I would say it is related because those are both mistakes that are made, right?
Yeah, but different mistake though.
Yeah.
Okay.
Are you planning any future work on chips from other manufacturers such as NXP or any of the other ones?
Yeah.
Oh,
why not?
I'm curious about the future results.
Thank you.
Maybe one last question from over here. Did the certification labs react in any way? And did they kind of, have an idea of why this went through and they didn't see it?
Well, they did have a reaction because they had to work a lot to produce all this new certificate. This is the celerity of this certificate production is not something normal in common criteria. And yeah, I wouldn't talk about for them, but I think the problem is the time you have to do the certification and how you do it. So it's the same lab have been doing all the certification for Infineon from the start. So they are looking at the diff from the last version to the new version. So what changes is what they are looking at. So what doesn't change.
Okay, so if they missed it in the first place, then it can
Yeah.
stay in there for.
Yeah, looks like it from my point of view, but again. I don't
Okay,
know.
so use longer random numbers, I guess. Thank you.
Thank you.
All right, so I think this is the last talk of our session and of the day as well. And it goes, I know what your compiler did. Optimization effects on power side channel leakage for RISC-V. And the talk is given by Durba.
Hello, yes. So hello everyone. So the title of my talk is I know what your compiler did, and I hope by the end of the talk you will know too. So I will give a brief overview of how we do a power side channel attack. So far in this session, we saw timing side channel attacks and EM. So in power side channel attacks, particularly for software implementations, we have a software implementation of any cryptographic algorithm, which we build using a compiler and which we flash on a microcontroller or a microprocessor, and then we measure its power consumption traces. So here we have an oscilloscope which captures the net power consumption. We have a trigger signal which ensures where should we start with the power consumption. And then we get these traces, and next these traces are analyzed to see leaks. So now in the first step, which is the compilation, we have, this is basically the command that we see. So first we see the compiler, then it specifies the architecture, followed by the libraries, and followed by a character, which is OS. So this basically specifies the compiler optimization level. So even if we do not specify this level, it takes O0 as the optimization level, which states that the compiler will not make any changes to the binary file. Now, there are other variants. So there is O1, O2, and O3 for higher levels of optimization. So these basically optimize for execution time. And then there is OS, which optimizes for the code size, which is more prevalent for applications such as for like edge applications. So now the question that we want to investigate here is, how do compiler optimizations impact power-based side channel leakage? So first I would like to answer the why. Why do we want to do this, and why RISC in particular? So as we saw in our previous talk, so RISC is an open source instruction set architecture, which makes it customizable, scalar, and cost effective. And it has seen several adoptions in extensions of this instruction set architecture, as well as development of hardware accelerators, which can be paired with the core. And we have also seen the implementations of post-quantum algorithms like Kyber and Lithium. So now coming back to our question. So now we answer these questions, or we rather ask smaller questions to answer our complete question. So first we see what are the effects on the compiled binary. Next we see, can we isolate the compiler-induced effects? And the third question that we ask is, how does it impact power side channel analysis? And do we see these impact or these compiler-induced leaks in real traces? And finally, can we somehow predict these leakages by looking at our data or our binary? So let's start with the first question. So for this, I would like to put this picture in front of you, which basically gives you a snapshot of an execution of an unprotected AES implementation. So here, I would like you to focus on the vertical lines. So here we have 7 colors, each indicating a type of an instruction. So we have load, store, branch instructions. So the lines which appear at the topmost level correspond to the unconditional branch. So they basically indicate where the function calls are in the implementation. And in particular, I would like to focus on this part, which is basically the shift rows operation of AES. So how it is implemented, it is basically implemented with a series of alternating load and store operations, where it loads the address, then the content, and it moves it back to a correct position in the memory, and so on. But now, when we change the optimization, so this is for optimization level O0. Now, when we change the optimization level for OS and O2, we see in particular for the shift rows operation that the number of instructions and the ordering of instructions change completely. So this is one aspect that we observed. Another thing that we observed, that many of these functions are inline. So when we are optimizing for time, it wants to save on the unconditional branch operation. So it inlines a lot of code, which also results in more register usage. Sorry. So here we can clearly see the difference in the shift rows operation. And what it means that when we go from one level to other, the register usage and the allocation pattern is very different. And these are the architectural registers that RISC provides us. And since the register usage pattern is different and we are loading data in a different order, it will leak, or it will lead to changes in the power consumption, or let's say power leakage. So now the next question that we see, we want to answer is, how do we isolate the effects of compiler optimization? So we have a complete power trace. So now this power trace that we get from an oscilloscope comprises of an operation-dependent component, a data-dependent component, a noise, and a constant factor. But now we are basically interested in only the component that comes from these architectural interactions. So how we do that is we can basically segregate, or just for our understanding, segregate the operation-dependent component into two parts, which correspond to the architectural based operations and the microarchitectural based operations, which come from the target device or the ISA implementation. And we say that we can basically just look at the data dependent component and the architectural component. Now, to extract this component, what we do is we call as an architecture level simulation. So for this, we take the ELF file, which we run on the target device. We feed it to an emulation framework, which is chilling in this case, which provides us with an execution trace. So now this is how an execution trace looks like. So it consists of a sequence of assembly instructions that are involved in the execution. Alongside it gives you the state of all the 32 architectural registers after every instruction gets executed. So now this is a small snapshot showing only 10 instructions, but as you may understand that depending on the implementation, we may have thousands of such assembly instructions. So now we apply leakage models, which are Hamming weight, Hamming distance, and identity in our case, to these execution traces, and we get something we call a simulated power trace. So now this is an example of a simulated power trace of a first order masked AES. And here we can clearly see the 10 rounds, and we can also annotate the start and end of individual operations. And if I just zoom in the first round, we can clearly annotate the start and end of each of the individual operations. So now we come to the third question. How do these optimizations impact power side channel leakage? So for this, we use these architectural traces or the simulated traces. So the advantage of these simulated traces is, I will go back. So the advantage of these simulated traces is that the granularity at which we get each point is for every instruction. So now every peak we can associate to one given executed assembly instruction. So now whenever we do correlation analysis or any leakage analysis, we can really go back and attribute it to the cause or which instruction is causing that leak. So now when we want to understand how these optimizations impact power side channel leakage, we are particularly interested in evaluating masked implementations. So what we want to see how effective are masked implementations when we change the compiler optimization levels. So for this, we choose a first order masked AES, and we focus on the shift rows operation of masked AES, because we particularly saw that the ordering of instructions vary for this operation. So now we will go step by step. So we are focused on the first or the second row, which is colored. So now the first step, what the compiler does, it basically loads the first and the fifth byte into two registers. Then it stores the fifth byte into its updated position in the store at index 1. Then it loads byte 9 in the same register A4, which previously had S5. And then it again stores the value of byte 9 into the index 5. And next it loads byte 13. And after this, it loads byte 1 into the shifted position. And again, it stores byte 13 into the shifted position. So now what I want you to focus here is that we see a load, store, and a load interaction. So first we load the masked byte 5, then we store it, then we again load masked byte 9. Now what this does is, if we look at the expression for masked byte 5 and byte 9, so when we so this basically byte 9 overrides byte 5, and what happens effectively is that the mask gets cancelled, and we get an XOR of the unprotected subbytes output. So now we want to validate it using the simulated traces that we have. So we correlate this unprotected XOR value with the simulated power trace, and we see two peaks, one which appears at the shift rows operation and one which appears at the mixed column operation. And this we do over 5,000 randomly chosen traces where we fix plaintext byte 5 and we randomize byte 9. And if we zoom into the assembly instructions which cause these leaks or which correspond to these leaks, we understand that this is the exact instruction which loads byte 9 to A4. So this basically helps us to annotate the leaks with assembly instructions. Now we want to understand, or we want to establish whether these leakages are also propagated in real traces that we measure from the target device. So for this is a snapshot of our experimental setup. So here we have a ASIC implementation of, we have an ASIC implementation of the Pico RV32, which is a RISC-V core with no pipeline. And we have this collection setup where we have the power generator, which supplies a power of 5 volts to the board, and we collect our traces using Chip Whisperer Husky. And then we perform the same correlation analysis using these real traces. And here as well, we see 2 peaks. But I would like to point out here that since we are looking at the trace for the entire AES, with some part involved in setting up the initial bytes, that's why we see that the 2 peaks are very close to each other. So now this confirms our validation that we actually see these these compiler-induced leaks in real traces, despite having noise, the constant factor, and other microarchitectural factors. So we also did this experiment for other optimization levels. And so we can confirm that these architectural level leaks are visible in real traces. So now we come to the last part, or a more interesting part that we are still exploring, is can we predict these compiler-induced leaks just by viewing these data interactions? So for this, I would like to first start with a toy example, where now these are 11 assembly instructions. And now if I focus at the first instruction, which means it loads the content of A5 to A4. So this is where in A4, I load the yellow data, let's say. And then in the second instruction, I load the content of A3 to A1. So at the second instruction, I load the data that we represent with green colors here in A1. And now there are no load operations which can change it. So now here we see, if we observe this register, until and unless some other data writes on this value remains in the registers, which gives us an indication now this becomes more prone to leakage. So this could be any intermediate or sensitive variable that we do not want to see. So this basically we term as remanence, how long a data remains in the architectural registers. So we count this in terms of the number of instructions. And another aspect that we observe here is that sometimes the bytes are overwritten and they reappear whenever they are required for further operations. So this reappearance, we call it as revival of the intermediate, or that the data gets revived. So now we count the remanence and revive for some intermediate. So here I show you the remanence and revive for the plain text bytes. So here each row corresponds to a given optimization level, and each column here specifies each byte of the state matrix or the plain text matrix. So now if we observe for OS, if we look at byte 0, this stays for 15 instructions. But if I look at byte 15, this stays for 450 instructions, almost 30 times. So we can hypothesize that we should be seeing more leakage, or like we should be able to see this value for a longer period of time in our traces as well. So to validate that, we conduct this experiment where we correlate these bytes with the power traces, and we see indeed that when we are looking at byte 0, it appears or it correlates with a high value for only certain number of instructions. However, for byte 15, we see huge spans of time where the byte stays in memory and can, of course, be exploited. So this also tells us that we can track these data flow of the values through the execution to understand or to, so basically give an indication of leakage or maybe the first steps in predicting leakage. So now, just to answer all the questions that we have asked so far. So what are the effects of compiler optimization? So we see on compiled binary, it causes strength reduction where it changes more expensive instructions to more, less expensive instructions. There is instruction reordering and changes in register allocation. Then can we isolate the impact of these optimizations? Yes, using architecture level simulation. And how do these impact power side channel leakage? By introducing unintended interaction between shares. Do these effects propagate to real traces? Yes, we see them in measured traces for masked implementations. And finally, can we predict these leaks? So we say that these are the first steps towards the direction, but we still have a lot of work to do in this. And the takeaway that from this work should be that whenever we are evaluating any cryptographic implementation, the version of the compiler and the optimization level should always be specified. Even if we do not set it explicitly, the compiler sets a default version. So these should be taken into account when we are doing power-based side channel analysis. And thank you. And this is an archive version of the tool that we used to do this analysis. And I would like to take any questions that you may have. Thank you.
But compiler versions would have a similar effect. Have you done any experiments on that?
Compiler versions?
Yes.
Yes, we did some experiments on like 5 different versions of compiler, and we see that we see basically change. So this we did recently. So we observed some changes in the simulated traces, but we are still in the process of collecting data from the real target.
Thank you.
I was wondering, I didn't quite follow if I understand correctly from your analysis, that if the data stays for a long time in the register, that would be bad for leakage? Well, I thought actually the dynamic switching power of the registers is the most leaking thing in power trace analysis.
Yes, so we basically devise 2 metrics. So one is remanence, which can sort of predict value-based leakage, how the value remains in the registers. And for this transition-based leakage, we think we can understand it from revive.
Okay, well, maybe we can ask it talk later also. And that one other question, to what extent do you think this extends to more complex CPUs? Because I think you tested it on a very simple pipeline, right? And I guess it becomes way more complicated the more complex your processor is. What do you think of that?
As per my understanding from this work, these these compiler-induced leakages will still be there because these are all at the architecture level. So even with more complex architectures, maybe the impact we see in real traces reduces, but we cannot say that it completely mitigates the compiler-induced leaks.
Thanks.
I might have missed it in the slide deck. Is there a public repo for this tool?
No, it's a work in progress. So yeah, but we will make it public soon.
Okay, thank you.
All right, fantastic. Well, I think let's thank our last speaker again. Thank you very much. It's been a long session, but we're, having good talks here, great attacks, good stuff. So see y'all tomorrow.